Okay, I'm going to go pull the filter out live here. I'm going to go unwind everything, and you can see after everything's been done the difference as we come back. So stand by.
Okay, 7-3. See you tonight, brother. Glad you made it home safe. NAD today.
All right, we're back. Isn't that wonderful? As that thing drifts back in, we'll be back. So I think we made about a 25 dB difference. And that was putting common mode chokes on a real-world battery charger and what you might be able to expect, along with a filter as well. And I'll show all these things, or I have shown all these things when I do the introduction. So this is W1VLF standing by from the radio bench. Again, thanks to Rich and Charlie for sending me the power supply so I could do these experiments. Oh, one other thing. I'm going to crack this baby open after this battery charger. Wow, I got something going on here with the battery charger power supply thing. But I'm going to crack this open and see just what's inside and where they may have been able to put filtering and just omitted it, or we'll see. Some of these things have circuit boards with no filtering in them, line filtering, with places to put it. So I'm going to just drop this off. I'm going to run into the other room, unplug this so everything falls back to zero again, and that will be the end of this part of the video. So guys, I'm back again for a quick follow-up. I had mentioned that this battery charger is labeled to be as 50 volts, 20 amps. This is for electric bicycle charger. So here's the thing. Right now I'm only drawing 1 amp. And I'm going to go into the other room and I'm going to attach another resistor, and it's probably not realistic that it's delivering 1 amp. It's probably more like 5 to 10 amps. But I'm going to put another another resistor on there so you can see the difference. Here goes. I'll be right back. Okay, so now we're up to minus 80, and look at that noise floor. Unbelievable. So imagine what this would be like living maybe 100 feet away from this. Just wanted to show you that last part. I'll go drop it back to a 1 amp draw, and then I'll finish this off. Okay, I'm back again. I just thought that was worthwhile, showing you just how bad it could get. I don't really have a way to load it to, let's say, 5 or 10 amps, but what you're seeing on the screen right now is the difference between 1 amp, which is currently supplying now, and 2 amps. I would venture to say that this thing is going to be pulling much more current than that on a depleted electric bike cell. Anyway, this is W1VLF 73 signing off from the ham radio bench. You know something, guys? I don't know. This is what you get when you get a guy with ADHD in front of the microphone. Forgot to mention this other thing. I wanted, you know, even when this thing is done charging, this is the battery charger just running at idle. So, you know, after this thing charges, it doesn't stop. It just keeps making this noise. Okay, granted, not at the same level. So this, I promise this will be the last part of this video, but this is this is the battery charger at idle. It's not delivering current to anything. Where am I? There's my mouse. Okay. I'm going to go and I'm going to add a 1 amp load, and then I'm going to add the 2 amp load. But even when the thing is done charging, this is just sitting there on the bench. No load. Here goes. I'm going to go add 1 amp and then 2 amps. Did you see that immediate shift off in frequency? This is why a lot of switching power supplies, when you load them, tend to move around in frequency. And look at the noise floor. It came up too. All right, I'm going to go add 2 amps and see what that looks like. Wish I could go more. Okay, another huge increase in noise, not only in the peaks, but especially across the noise floor. Let that sink in for a little while. And there's going to be more and more electrical vehicles, cars and bikes and scooters and all sorts of stuff like that. So once that gets about halfway down the screen, I'm going to go unplug it. Take the load off first and then unplug it. Okay. There it is, just idling. And look at as it cools down how it starts dropping in frequency. I think the fundamental oscillator in there is running about 50 kilohertz because this one is at 740. Nope, higher than that. 140 to 190. Yeah, about 50 kilohertz. And I'll go unplug it now, and I promise that'll be the end. Okay, back to Mother Nature's noise floor. Thanks a lot for sticking around with me, folks. If you want to see more videos, please subscribe. There's a little button in the lower right-hand corner of the screen that will allow you to hover over it, and then it'll pop up with a subscribe button. You hit that, and then hit all of the notifications, and you'll be subscribed. Nothing fancy here, just sort of real world stuff. 73 from W1VLF here in Harwinton, Connecticut. All right, I'm gonna take this puppy apart, and can you imagine that? It has screws in it. Unbelievable. Before I get this apart, what I'm expecting to see is a circuit board with a whole bunch of components that are missing. Namely the EMI filter. Something like that. That's a really good one. But there should be a bare minimum in here, and I'm guessing that's not in there. A lot of times the circuit board is capable of holding the parts. It's stenciled in, but they don't put them in because that would make it cost another $1 or $2 more expensive. So instead, they just let it spit out noise everywhere. So, oh shoot, that was easy. Okay. So, whoop, doing this backwards. Here's the AC side, right? Follow this in. And, wait a minute. Oh, we can take it right out of there? Yeah, okay. So here's the AC side. And guess what's missing? LF2. You know what LF is? Line filter. And a bunch of capacitors that are typically across the filter to make it look like a low pass filter, so that 60 hertz can come in, and whatever this is running at, I think it's running at like 50 kilohertz, can't go back out. That's a real problem. Let me zoom out just a little bit. Okay. So that's the AC side, and on the DC side, yep, look at that. LF3 is missing. The inductors and the capacitors and a couple other components, it looks like, too. So there it is. It's on the circuit board. And you know what? You probably can't see this very good, so I'm going to take a couple pictures close up, and then I'll narrate over the top of them. So that's where the filtering should go, and guess what? There's just a solid bar of solder from here to here. The holes are there in the circuit board. So basically, what do? You come in, there's one capacitor here, I'm not sure what that is for. They call it, it's an X capacitor, so it's across the line. And the diode stack and a rectifier. And then you chop the heck out of it at 50 kilohertz or so, rectify it again, pass it through the transformer, rectify it again, and send it out the door. But there's a lot of stuff missing on this. And I'm sure that this low-pass filter would have gone a long way. An important thing to remember here is, even though I was able to put a... There it is. I don't do this enough. Even though I was able to put a EMC filter on, it still is on the end of this cord instead of right here at the circuit where you really would like to see it. And the same over here. Alright, I think the best thing to do is to get some pictures of this up close. I'll do that, and I'll talk over those. So, okay, so I guess that's going to, no, that's not going to be it. That's going to be the end of the video, but it's not going to be, the end of the actual video. The rest of it will be some slides and things. So, and some, if you have any questions, give me a yell. Blah, 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 blah. And if you can, subscribe. There's a little button in the lower right hand corner. If you hover over it, it will bring up a subscribe button, and if you hit the subscribe button and then hit the notification all bell, that will get me up to 1,000. I think I'm at like 650 or 640 now. It would be cool to get to 1,000. That's like a goal, maybe before winter. Anyway, thanks again, and 73 from the W1VLF lab. So here's the entire power supply as you see it directly out of the case. I'm going to try to keep these audio clips short and get as much stuff done here as I can. Well, here's where the line filter should have gone. The back side of the circuit board showing the soldered over connections where the filter should be. Oh! And here's the back side of the battery charger. So in the event that you want to get one of your very own, here's the company that manufactures it and all the specs. Here's that Nanolux filter that I was talking about. I'll put a link in the description as to where these can be found. Again, there's this one, which is the AC side, and then there's the other side, which is meant for the ballast, the output of the ballast. Which may or may not be useful. I don't know. I've never tried using that half of it. Here's another EMI filter made by Qualcomm that could be substituted. 3 amps, 120 volts. Essentially, look at the diagram. It just looks like a low-pass filter with some common mode capacitors and a ground connection. And finally, a common mode choke that you could wind yourself. This is on a 2.4-inch core. If you're considering doing this for frequencies in the HF band from a megahertz up to, say, 30 megahertz, the material here would be number 31. I don't like the snap-on cores because you can never get enough turns on the snap-on cores. Remember, the impedance of the common mode choke is a function of the square of the turns ratio, so you get something for nothing. 2 turns is 4 times the impedance of 2 turns of 1 turn, and 4 is 16 times. So the more turns, the better to a certain extent. It's not always true, but it is for all practical purposes. In this case, it is. Thanks a lot, guys. 73 W1 VLF. Hey everybody, I'm back. This is Paul, W1 VLF, and welcome back to the lab. After I finished that other video about the noise with this battery charger here, I went in the infinite parts pile, and I found one of these line filter inductors, and I'll show you some close-up pictures of this. This is not the exact one that fits in this power supply, but it's very similar, and I had a whole bunch of these, so I figured, what the hell. I'll put it in and do a quick test and show you how much difference putting in just the inductor out of this differential low-pass filter makes in the noise level, okay? This one little component here I'll show you better. I don't know what this thing costs, maybe 20 cents? This is just one of those components, and it's just on the input. It's not on the output. So between this and the X and Y capacitors and the output filtering, this probably could be a reasonably quiet power supply. And one other thing, just real, here's what I was using as a load. This is a 100 ohm, 200 watt power resistor, so that was what I was taking the place of my battery at 1 amp. So an amp at 50 volts, it's 50 watts. And I wrecked the Group W bench. So, one thing you got to be careful of is that you don't let your mind drift. So 50 watts over the course of half an hour. I just left it laying on the bench. It was going to be just a quick test. And of course something else came up, totally forgot about it. It melted through, and the little chunks of the Group W bench are here now, and I got a big burn mark. So just be careful when you're messing around with this stuff, or anything. Always keep your mind on what you're doing. By the way, I am not suggesting that anybody goes in and puts this choke in like this. You're dealing with 120 volts. I did it because I'm not as smart as you guys. And anyway, I'll show you the rest of the video. This was only meant to be a really quick update. All right, thanks. See you over at the bench. See you over at the ham shack. Okay, so we're back over here at the Ham Radio Shack computer, and right now if we look over here, sort of the same conditions as yesterday. Basically, what, minus 125 in the middle of the lightning crashes, and there's quite a few of them, so something's brewing up somewhere. Just going to let it run for a few seconds here so you can get a baseline idea of what the noise level is like. Again, running the 6-meter antenna, the very short, obviously, for 40 meters, and that ambient noise level at minus 125 shows that. So I'm going to run into the other room, and then I'll put the power supply on with a 1 amp load and running in the normal way, and then I'm going to insert that choke that I showed you. Only one component of the R5 filter. So here goes nothing. Okay, so we're back. I just turned on the battery charger with the 1 amp supply on it, and you can see how high the noise floor got in between the carriers, as well as in these carrier areas right here. So let me just push this up a little bit. So I'm going to try to get all three of these on the screen at the same time. Be right back. Okay, so I inserted one component, which is that little transformer, excuse me, not transformer, the 2 series chokes that are on the common core. And look at what happened to the noise floor in between and the actual carrier power. That's just one of the components that should have been designed into this on the input side, and then there's a filter as well on the output side. So this power supply could be made quiet if all the right components were installed, but to save a couple of bucks, they didn't. Anyway, thanks a lot for checking this out. Hit the subscribe button if you can. And this is W1VLF signing off.
In today's video, we're going to talk about port extensions on a VNA. We'll talk about what they are, why you might need to use them, and how you set them up on the Nano VNA. This is a bit of a follow-on of video 313 where we talked about user calibration in a VNA. You remember that user calibration corrects for systematic errors in the instrument itself, things like frequency response and tracking, source match, and leakage and crosstalk terms. But the other important thing that the user calibration does is establishes the calibration or measurement plane. And this is essentially the plane, if you will, where you attach your open, short, and load when doing, in this case, say a single port calibration. And what that does is it makes sure that the magnitude and phase of the response is normalized to that point, so that we're only measuring the effect of magnitude and phase of the device connected at this location. But what if the device you're testing doesn't attach the same way as your open, short, and load standards that you use for calibration? Maybe you need some kind of a fixture, or maybe an RF adapter, or even a short length of cable to connect your device under test to the VNA. Well, this actually could present a problem potentially if you want to accurately measure the complex impedance looking into your device. The reason for this is that each of these devices that you add to the VNA port beyond where you made your calibration will add an additional delay or phase shift compared to where that calibration was done. And that is essentially going to alter the impedance that is seen by the VNA. Well, the answer is to use a port extension. This allows you to move the calibration plane or extend it to the end of your fixture, cable, adapter, or whatever it is that you needed to add in order to connect your DUT. Now this can be very handy, but it's not perfect, because this port extension really assumes that the extension or the movement of that plane is simply an extension of the 50 ohm line that was already part of the VNA itself. It doesn't take into account for any impedance discontinuities of the adapter or the fixture. So if you've got some kind of an oddball fixture that's got some impedance bumps in it or something like that, and it's not perfect, or the adapters are a little bit unusual, or you're going to some flying leads on the output of an RF connector, it's not going to account for that impedance change. It's assuming that the extension is just an extension of the 50 ohm line. But for most of what we do in the amateur radio hobby or for other hobby use, it'll work just fine. And in many cases the adapters are all 50 ohms, so it's actually pretty close. One issue with some of the Nano VNAs are that they don't use the same terminology that the RF industry uses for VNAs. For example, this would normally be called port 1 and port 2. The Nano VNA calls it channel 0 and channel 1. And of course, the Nano VNA doesn't call port extensions port extensions. The Nano VNA refers to this as electrical delay. So let's go see how to use that. Let's take a look at the effect an RF adapter would have on the complex impedance observed on the reflection port. Okay, the setup here is a 50 kilohertz to 900 megahertz sweep, freshly calibrated as indicated by the capital C for the calibration here. There's an open sitting here right now. And so since we're only looking at the reflection properties, I just have 3 traces turned on. The log magnitude of the reflection coefficient, or S11, is riding here along the top. Okay, essentially we've got sitting at 0 dB essentially across the whole frequency range, essentially a perfect reflection. I've also got the Smith chart, or complex impedance, shown. Here's the green trace, and that's indicated right here. And you note that we don't see any kind of an arc, which means that over this entire frequency range, this looks like a perfect open. And then the third trace I have is the phase of the impedance of this open across frequency. Again, flat, because that's essentially our calibration plane. Now if I simply add this male-to-male SMA extension or adapter here, you'll notice a couple of changes in the traces. You may have noticed that the phase response has now got a tilt to it. And the reason for that is that at low frequencies, like 50 kilohertz way down here at the end, the length of this is really, really tiny with respect to the wavelength at 50 kilohertz. So it represents, a fraction of a degree of delay. However, as the frequency goes up, this delay now becomes a larger portion, and essentially a measurable delay. We get all the way out to 900 meg, and we're looking at about 50 degrees of delay across that RF adapter at 900 megahertz. Now this is also reflected in the Smith chart. In fact, you can see when I move the marker out to about 900 megahertz, we can see that now, instead of sitting at the open circuit, because we still have an open at the end here, we're now sitting down here on the Smith chart, because we've rotated around here because of that phase shift. Means that looking into this end of the adapter doesn't look like a perfect open anymore. It's got a little bit more of a complex impedance. And since all we really did was extend the 50 ohm line, we can add that electrical length in and effectively extend our calibration plane out to here and do that port extension. So here's how you do that. So we bring up the menu, go to Display, and go to Scale, and this is where we find electrical delay. Now of course you can make some measurements and run some calculations to figure out what the exact number should be, or you can just play with it experimentally. So we got a pretty short little adapter here. Let's just add in, say, 100 picoseconds of electrical delay and see where we wind up. So with 100 picoseconds of delay, we can see we've flattened the phase out. It's not quite back to zero. We're sitting now at about 21 degrees, and you also can see that the arc that we drew out on the Smith chart has now been reduced. So 100 picoseconds got us part of the way there, but not all the way. Okay, 100 picoseconds wasn't enough. Let's add 200 picoseconds instead. So we'll dial in 200 picoseconds, and let's see where we wind up. Well, it looks like it puts the phase at about 10 degrees, and we're drawing an arc up in the opposite direction. So 100 picoseconds wasn't enough. 200 picoseconds is a little too much. I've iterated around a little bit with this, and I think 165 picoseconds is going to be really close. So 165 picoseconds got us to a phase of just about 1 degree at about 900 megahertz. Let's go all the way out to the end there. Yeah, 1.4 degrees, and we're really close. So that's probably close enough. We could probably fine-tune it by another couple of picoseconds. But this is the effect of now adding an electrical delay to effectively do a port extension to now make our reference plane right at the end of this connector. So now whenever we connect here, we can measure the complex impedance of that and now have a proper phase measurement of that impedance because we've extended our calibration plane to here. In this example, I used a fairly wide frequency range for a reason. I wanted to show you the fact that adding these extensions and adapters and things like that generally won't matter much at relatively low frequencies because the wavelength, the length of these adapters is really small with respect to the wavelength of the signal at those low frequencies. But the higher you go in frequency, the more even small little adapters will actually start to matter. So after doing your calibration and hooking up whatever adapters you have to get to your particular device under test, take a look at, on the Smith chart for example, what an open or a short looks like at your device to make sure you're sitting at the 3 o'clock or 9 o'clock position on the Smith chart. If your device, you might be, say, an antenna embedded on a printed circuit board, for example. You might have a way of actually creating an open or a short. You can even go down with the blade of an X-Acto knife right at the input of your antenna, for example, and create a short on the board and see if that winds up showing up at the 9 o'clock position on the Smith chart as it should. If not, then you may be able to apply port extensions to actually find out, to move that reference plane right to that spot on the board, and then make that your new calibration plane so that when you measure the complex impedance, you can measure the complex impedance of that antenna structure, for example, so that you can design a matching network to be placed right there. So by changing that electrical delay parameter, we can effectively affect a port extension on the Nano VNA. So I hope you learned something about what a port extension is, why you might use them, and how you effectively apply it on a device like this. If you liked the video, give me a thumbs up. If you haven't subscribed to the channel already, please do so. And thanks again, as always, for watching.
Hi, I'm Jim W6LG, your YouTube elder for Ham Radio Basics. Welcome to my radio room here in Rockland, California. Today we're going to talk about velocity factor. And what the heck is that about? And why does it matter? And where would you use it? We'll find out more about that right after this.
Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
So let's say you are the lead electron leaving my K3 transceiver, and behind the lead electron are millions and millions and millions of electrons, and they enter a tunnel called route 0.66. Route 0.66 is RG213, and that happens to be about 100 feet long. And then those electrons will enter or be on the surface of some wire that makes up the antenna, and still not quite hit the speed of light. Close. But in my case, the wire that I'm using has a coating on it, and that coating slows down the electrons that are running on the surface of the wire. To give a better example of velocity factor, this coax and this coax have a lot in common. They have the same velocity factor. And this is big stuff. This is 0.875, roughly an inch. This is about 1/8 of an inch. This is 50 ohms. This is 50 ohms. This has about a 95% shield. This has about actually about a 98% shield. This can handle a few hundred watts. This can handle 8 kW. Well, we're talking about coax. I watched a guy's video where he talks about making dipoles and things, and I want to cover some definitions for the parts of coax, and this might be a good piece to use as an example. This outer covering is a jacket. So for purposes of our videos, we're going to call this outer piece, which is PVC, the jacket. This is the shield. The shield can be a braid, as this one is. It can be foil. It can be wrapped wires. But jacket, shield, and then the insulating material that's between the shield and the center conductor is the dielectric. And in this case, the dielectric is polyethylene, I think. Yeah, polyethylene. And then the center conductor, which is not quite a 1/4 of an inch in diameter, and I'll try to get a close-up picture of it, is solid copper. It's tough stuff. By the way, they call this, this coax is called, up the mic, this coax is called flexible. I couldn't bend this if I had to. Now, in a big roll, I can do a 3 or 4, probably 4 or 5 foot radius. In this coax, and again, that's going to be out of focus. I'll do a close-up of it. This has a really good shield. Loss on this stuff is good. It's about, I believe it to be about half of RG213. In the next video, I'm going to test that. Now, with respect to this particular coax, which is the designation is RG218, RG218, not RG213. And I don't have a piece of it handy of 213. 213 is 0.405. This is 0.875. So this is roughly double the diameter. Sometimes you can get this stuff for free, and a good friend of mine, R7KZ Stan, was able to get some rolls of it for me. And in another video, I'll show you how I made coax connectors for it. The coax connectors for this run $150 a piece. The coax is about 15 to 20 bucks a foot. 15, I think, is pretty common. But the coax connectors are outrageously expensive. So I make them, and I'll show you how. In fact, you can make a lot of coax connectors for different sizes of coax if you want to. In many cases, like with RG213 and RG8X, it just isn't worth it. RG8X. Now, there's a little bit of a difference with RG8X. I was testing some of it with my Nano VNA. The dielectric on RG8X is different, and as a result, its velocity factor is about, and this is a piece of that gray stuff that's everywhere, it measured about 0.82 or 0.83. This measured 0.66. What does that mean? Okay, this measured 0.66. This that I can't hold up measured 0.66. There. And this measured 0.66. How's that possible? Dramatically different sizes. They're all the same impedance. What about this coax causes the velocity factor to be the same, even though these are dramatically different pieces of coax? And then RG8X with a foam dielectric is different. The thing that makes these three pieces of coax the same is the dielectric. And if the dielectric, if the electrons are running on the surface of the wire, they're bumping up against this insulating material. And if they're running on the inside of the shield, they're bumping up against, I know, engineers are going crazy with that thought, but let's just say they're rubbing against the polyethylene that makes up the dielectric. So the 0.66 is not related to the size of the coax, but it's related to this material that makes up the dielectric. And if that dielectric gets moisture on it and it's sucked up by the braid, which happened to this, and it starts to discolor the braid, the losses increase and the impedance can change. It can get kind of wacky. That's technical talk. So anyway, the electrons running on the surface and on the inside are slowed by the dielectric. When those electrons got to my wire antenna, which has a black PVC insulating material on it, it slowed them down again. Let's estimate that a copper wire strung out in your backyard has a velocity factor of 0.95. What does that mean? It's running at 0.95 the speed of light. This is running at 0.66 the speed of light. So if you wanted to string up some coax and you wanted to know what's happening at the feed point, you could use a multiple of a half wavelength. But if you cut this stuff to that length, it's not going to work out right because you have to take into effect the velocity factor, which is usually expressed as a decimal point and then two numbers following that. So 0.66, 0.66, from dielectric RG8X, 0.82. The loss on the RG8X is substantially greater than the RG213 and this. So there isn't necessarily a relationship between, there is. This is not as lossy as it could be because it's got a foam dielectric, but size matters. And with respect to coax like this, the larger the diameter, generally speaking, the lower the loss at really high frequencies. This stuff will go up to like a couple of gigahertz. Does that matter at 30 megahertz? Probably not. And that will be the next video. What I've done is I ran 4 lengths of coax out to the tower in the backyard. There's a switch in the room here that has 4 vacuum relays attached to it. I can switch, actually 5. I can switch one of 5 lengths of coax going to the back. There's another relay, series of relays at the tower where I can switch vertical that's attached to the back fence, the beam, and some other things. Or I can go to an open. By having an open, I can look at just the coax, one of the 5 lengths, from point A to point B. Using the nano VNA, I can find the impedance, I can find the loss, and I can find the length. And then from that, maybe we can draw a conclusion as to whether or not is it worth having stuff like this. I'll tell you right now, the answer is no. RG8X, or RG213, or perhaps LMR 400, which are relatively inexpensive, and if you buy a name brand, and name brand coax connectors can be just as good as anything. All right, velocity factor. What does it mean? It's the slowing down of subatomic particles, electrons, because of the material that they're running on and what they're running up against. So in coax, it has to do with the dielectric because it's running on the inside. The electrons are running on the inside of the shield and the outside of the center conductor. In the case of wire, it's running on the surface of the wire. If the wire is coated with some kind of covering, it can slow it down a bit. With respect to coax, the correct terminology is jacket, shield, dielectric, center conductor. And if we stick with those, if we stick with those, it makes good sense. At one point, I was having coax manufactured, so I'm pretty familiar with what manufacturers want to hear. All right, velocity factor. So if you wanted to have a multiple of a half wavelength to, let's say 20 meters, let's just for round numbers say, maybe 33 feet going, a half wavelength is 33 feet. However, it's 0.66. So whatever that works out to, does that work out to 22? Yeah, I think it does. So every 22 feet is another half wavelength. So if you cut the coax at length, that shows you what's happening at that half a wavelength, that half cycle. And if you go multiple, maybe 3 cycles or 4 cycles, you can see what's happening at the antenna. And I'll make that, try to make that more clear in the next video. All right, I'm Jim, W6LG, your YouTube elder for Ham Radio Basics. If you liked or didn't like this video, thumbs up or thumbs down. Please do subscribe, and I'll see you the next time. I'm kind of getting things buttoned up in here and going to be back in the business of doing some YouTube videos. 7-3. Bye-bye. Hi, I'm Jim, W6LG, your YouTube elder for Ham Radio Basics. Welcome to my radio room here in Rockland, California. I did an autopsy on some coax, and what I found is really interesting, and we'll look at that right after this.
Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
In a prior episode, we talked about velocity factor, and there are 4 parts to coax. There's a jacket, shield, dielectric, and center conductor. And that the electrons run on the surface of the center conductor and the inside of the shield. And the dielectric affects the velocity factor and loss of the coax. So if you have a foam dielectric, it can have less loss than a polyethylene dielectric. But what happens if there is some damage to the coax? I had some RG218 that showed some much greater than typical loss when I checked it with a nano VNA. And I thought, instead of just throwing it in the trash, that maybe I could recover the shield from that coax and use it as a ground strap. And here's that shield. This is slightly tarnished, and I've split it open, and you can see that there's been some water here. So the electrons are running on the inside of this. But here's what I found as I dug through this stuff. Now this turned out not to be all that hard to get off the dielectric. The length of coax I was dealing with was about 50 feet. I've got a coil up on the floor because I've got this snake of stuff all over the place. And it's got some little burrs on it. So here's the stuff, and as I started out, I thought, man, this stuff doesn't look so good. And then I got to sections like this, where it looked like a garden hose. It's just black, black with tarnish, and it's black on the inside. So, and it's bunches of it. So the electrons are running on the inside, and it's on my hands now, are running on the inside, and they're not only bumping up against the dielectric, we're going to deal with now the coating on the coax. So likely when I measured the length of that, the velocity factor was probably off, because it's probably greater than 0.66 due to the water intrusion. And the losses, they ended up being fairly large. So that's what happened with that coax. It got water in it. That coax had been laying on the ground out to a tower on Wolf Mountain. Now the other thing is I measured the losses in 4 lengths of coax. So from the radio room out to the tower, I have 4 lengths of coax, and I have vacuum relays in the radio room and mechanical relays at the tower, and I can isolate each of those 4 runs and still connect to them. So I measured the losses with the nano VNA in RG8X, 2 lengths of RG218, and 2 lengths of RG213. Now the lengths of coax varied, and I decided to make them adjust the length. I did some cross multiplication for 100 feet. So the measurement then is 100 feet of coax at 30 megahertz. What are the losses? The RG8X measured about 2 dB loss. The RG218, when adjusted for its length, which was slightly long, measured 0.67, so less than a dB. The sort of crummy looking RG218 that looked like it had been through the war measured 0.8. The used RG213, which is relatively clean, and the jacket looks really clean, measured 1.1 dB, and the new RG213 measured 1.04, roughly 1 dB. Now the efficiency then, to convert the dB to efficiency, the RG8X, 30 megahertz, 100 feet, 63%. So if I put 100 watts into the coax, 63 watts come out the other end. On the 218, at its equivalent length of 100 feet, I'd lose 14 watts, so it's 86% efficient. The beat up RG218 had a loss of about 17%, so it was 83% efficient. The 2 lengths of RG213 measured about 78 or 79% efficient. So the difference in loss between the 0.875 and the 0.405 coax, one's roughly twice the diameter of the other, the difference is not great. But what happens when you get to 440? So the losses are relatively close at 30 megahertz. They're going to be, the separation in losses becomes much greater at 440, and I'm going to bring that up on the screen now. RG8X, 100 feet, 440 megahertz, 15% efficient, 85% loss. RG218, 50% loss. RG213, 68% loss. LMR 400, 46%. If you go to really big coax like 0.875, the loss is 17%, so there's a significant difference. If you go to the really big stuff, as a friend of mine did, the losses then become darn near zero, like 5%. So as you go up in frequency, if you're going to do that and you've got a relatively long run, the larger the diameter of the coax, generally speaking, the smaller the loss. For me, HF 14 megahertz, I'll use the RG218, but in switching between different lengths of coax and doing tests, listening to friends of mine in Europe, I couldn't see or hear any difference. So that's the answer to the question about which coax am I going to use. Was it worth the effort of putting the 4 runs into the, actually 5 runs into the attic? No, it wasn't. But I had them. I decided to go ahead and use them. So while I was up there, I put them all in place. All right. That's today's episode on velocity factor, coax losses. I'm Jim, W6LG, your YouTube Elmer for Ham Radio Basics. Thanks for watching. If you enjoyed the video, thumbs up. If you didn't enjoy the video, thumbs down. Please do subscribe. If I can get from, I'm roughly 30,000 subscribers right now. If I can get to 50,000, I get bonus payments for. Hi, this is Jim, W6LG, your YouTube Elmer for Ham Radio. Welcome to my backyard here in Rockland, California. Tower's up, and I was able to install a 3-element Yagi at the top. It's a homemade Yagi with an 18-foot boom. The Yagi can have a maximum height above ground by county ordinance of 30 feet. The tower is made up of 2 tubes. There's a pulley system that pulls that square tube up and out. The whole assembly sits on top of a thrust bearing, which is on a fixture that holds the tower vertical. I modified the fixture so that it can lean over the tower as needed. The thrust bearing sits above a rotator, which is a Yaesu rotator, and that's what turns the tower. So the whole tower turns with the antenna attached. The tube that extends from the rotating tower to the rotator turned up missing. So I had to fabricate something to make up that gap. So I took some tubing and some concentric pieces and fitted them together and put some through bolts to hold it together. So finally got all that working. So here's what it looks like when you turn the antenna, and I'm going to rotate it about 300 degrees from north around to the west. So here goes. Here's my new rotating 3-element Yagi on an 18-foot boom on 20 meters.
Hey everyone, it's Alan, W2AEW, making a rare appearance in front of the camera this time with an exciting announcement. I've had the honor of being asked to be part of the cast of a weekly online ham radio program hosted by Tom, W5KUB. It's the Amateur Radio Roundtable, and you can catch it online with live streaming video with chat room, and even catch it on international shortwave and WBCQ on 5130. The program happens every Tuesday at 8 p.m. Central, 9 p.m. Eastern Time, which is 0200 UTC. So be sure to check out w5kub.com for all the details, and we'll see you on Tech Tips on the Amateur Radio Roundtable. Hope to see you there.
Hi, I'm Jim, W6LG, your YouTube Elmer for Ham Radio Basics. Welcome to my radio room here in Rockland, California. I need to build a couple of dummy loads, and I already have this guy, and this is a bird dummy load that is good for 500 watts at 30 minutes on, 30 minutes off. It is a brute. Now it says 500 watts. I put way more than 500 watts into it. I put 1500 watts into it. This darn thing must weigh 20 pounds. But where I need to go is outside and test some coax cables. So for my purposes, this dummy load is not going to do the job, but I need a couple more. In the past, I've built dummy loads using resistors like this. These are 5 watt 1000 ohm resistors. There are 20 let's see, these are 1000 ohm. There's 20 in here, and they're 1000 ohms, so 20 into 1000 ohms, they're parallel, is 50 ohms. And in checking it with an ohm meter, it measures about 49.5 ohms. In transmitting into it, it's okay to a certain frequency, and then it gets real reactive. And part of that is due to the wires that I used. There are wires that become a significant portion of a wavelength as you get close to 2 meters, and it gets real reactive. So the box I build during the break will be, the goal will be to have no inductor reactance, no capacitor reactance, to try to eliminate both of those and have it be just a resistive load. So what I'm going to do is take some rods that look like this, like that. They're copper, and then I'll parallel 2 of them like railroad tracks and put the resistors in between. And then I'm going to slap some copper sheets on both ends to try to eliminate the inductance of this rod. I'm going to cover it up. I'm going to solder copper to it. So it'll be pretty ugly looking, but I'm hoping it'll work up to 2 meters. Find out more about that on the Nano VNA right after this break, and during the break, which is going to be for me probably a couple of hours, I'll build the dummy load and we'll see how it works. So stand by. Be right back in just a few seconds, your time, but a couple hours for me.
Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay. The couple of hours that I thought it would take ended up taking a couple of days. And what I ended up doing was building more than one dummy load. As it turned out, the insides of my dummy loads ended up pretty ugly, and I'm hoping that they work well. The first one I built was this one, and it was a box I had, and I've used it on a bunch of projects. It's just simply a box that had a relay in it. It was sold commercially for ham radio operators, and I've acquired a couple of them over the years at garage sales and things. So the resistors are on the inside, kind of in a circle, and I slapped copper on the top and bottom. Now that is just horrific looking, honestly. If you look at the solder connections are good. They're not cold, but they're ugly. And no matter how hard I tried, and I built a couple this way, I couldn't make it look any better. So anyway, I'm hoping that with the copper plate, if I can show that it will remove any inductance, because I've slapped that copper over the top of it. So we'll see how that goes. There are that wasn't supposed to happen. There are 20 resistors, 1000 ohms, parallel. 20 to 1000 is 50. Measuring this with just a plain old ohm meter, it shows 49.3 ohms. So close enough to 50, but we'll see what the reactance does, because the reactance will change that value. This one, yeah, it's a dummy load, and I put a fan on one side. There's an exhaust on the other. Yes, it's got a light bulb on top, and it's got its own little watt meter. So it's a 50 microamp meter. I took a circular ferrite bead, put some wire around it, and went through a 1 in 34 up to this and through a potentiometer. And son of a gun, I calibrated it for 500 watts full scale, and it's really close. The light bulb, I do have a need for that, and I'll demonstrate that here in just a minute. In a subsequent video, I'm going to talk about pulse width modulation, and this seemed like a good way to demonstrate how that happens. So the bulb can be unscrewed and it's out of the circuit, and we'll see how that looks on the VNA. Okay, let's jump over to the VNA and take a look first at the small dummy load, and then last to the larger dummy load with the light bulb. Okay, I've scanned the box from 3 to 30 megahertz. It's virtually flat with an SWR of about 1.05. So that's excellent. Let's see what happens when we go to 2 meters. So I'll put in 148 megahertz and sweep this thing. Again, this is the small box with the copper. That's excellent. So a slight rise around 120, 30 megahertz, but still that's only about 1.15 to 1. That's an excellent SWR curve. So again, it looks like the copper did the trick. Now, getting to 440 megahertz is going to be a whole different situation, because just about anything will react there. So let's sweep it and see what we get. All right. So it's about 1.7 to 1 at the worst. It's not terrible, but it's not going to be good enough for what most of us need to do. Basically, the box is good through about 2 meters, maybe 200 megahertz. There's a dip at 241 megahertz. That whole curve, although it looks a bit high, it's really not. It's about 1.15, 1.12 to 1, so through 250 megahertz. So that's really good. Now let's sweep the big box, and that will have the light bulb disconnected initially, and that will change. When the light bulb is screwed in, because it's cold, it's going to present a very different impedance, a very different resistance. So scanning it with a nano VNA may not tell us much. So let's do that now. Okay, it's better than I thought it would be. Again, it is virtually flat from 3 to 30 megahertz. So for HF, in that fan I've got inside, I've got a 600 watt dummy load. Let's try this with screwing in the light bulb and see what happens with that. Okay, that's with the light bulb. Screwed in but cold, so the reading will be different when it's got power going to it. This particular curve has no value because it won't apply with the light bulb heating up. So here we go. Let's put some light on the subject and see what happens. Okay, there's the filament is lit up. That's 25 watts roughly into the dummy load. I've got the blower going. I know it's making a lot of noise. So I'm going to crank up the power and see what happens. SWR is 1.2 to 1, so that's really good. There's 50 watts. And the filament is actually moving around, so I can show that. Okay, there's the linear amplifiers on. That is just about 100 watts with the linear to take the output of that. Okay, there's 300 watts. So to summarize, I built the dummy loads that I needed. The one with the light bulb for demonstrating pulse width modulation, and the other one for going outside and doing some measurements on some coax cables. Anyway, I hope you've enjoyed this. If you have, please subscribe. If you have, also give a thumbs up. If it didn't work out for you, do a thumbs down and let me know. If you have a question, post that below. We'll do our best to answer it. 7:30 for now. I'm Jim, W6LG, your YouTube Elmer in Rockland, California. 7:3 from smoky Rockland. You can hardly talk. It's so smoky. See you later. Bye. Hi, this is Jim, W6LG, your YouTube Elmer for Ham Radio Basics. Welcome to my radio room here in Rockland, California. A couple of weeks ago, I received an email from Eric Guth, 4Z1UG in Israel, asking if he could do an interview of me for his podcast. And we did that. Eric is incredibly well organized. So far, they've interviewed about 300 ham radio operators from around the world. I think I'm number 320. Those interviews, by the way, are located at QSOtoday.com. And the name of the podcast is QSO Today Amateur Radio Podcast. Anyway, Eric asks a lot of neat questions, and it's not rehearsed, it's not scripted, it happens live, and that's it. Anyway, if you want to hear a little bit more about me, Eric's interview goes into my beginnings in ham radio and some of my experiences. I would encourage you to go to his website at QSOtoday.com and look at the list of ham radio operators. You're going to recognize some of the names. There may be some of your friends on there, and there are some guys that you've heard about, like Riley Hollingsworth. I would encourage you to click on and listen to some of those interviews. And in fact, what I'm doing is I'm just clicking on them randomly of names I don't recognize and listening to the interview. It's certainly entertaining, and I've learned a lot. I get a different perspective on ham radio from these guys. All right, so here goes. Here is the interview of me by 4Z1UG in Israel that was uploaded yesterday to his podcast called QSO Today Amateur Radio Podcast at QSOtoday.com. So here goes.
My QSO today is with Jim Heath, W6LG, who has been a ham for over 56 years. Jim is an Elmer's Elmer with an amazing YouTube channel with over 30,000 subscribers, where he not only reviews the basics of amateur radio, but he makes that content up close and personal, reflecting on his experience as an amateur radio operator. W6LG, this is Eric, 4Z1UG. Are you there, Jim?
I am. 4Z1UG. This is W6LG in Rockland, California.
Jim, thanks for joining me on QSO Today podcast. Before we start the beginning of your ham radio story, where is Rockland, California?
Rockland is a rocky land located east of Sacramento in the Sacramento Valley. We moved here about a year ago from a place called Grass Valley, which was at a higher elevation, about 2,000 feet. This location's at the valley floor, and Rockland, Rocklin, was mostly rock quarries, and it got subdivided through the 80s, 90s, and even currently into large subdivisions. So it's a mix of residential and commercial. So there's shopping centers on almost every major intersection.
Are you HOA there?
We are.
Okay, so we're going to have to talk a little bit, when we get past the beginning of your story, we'll talk a little bit about HOA and how that works for you.
Okay.
So let's start at the beginning of your ham radio story. When and how did it start for you?
In 1964, I got my novice license, and it was with 3 other friends in junior high. One of them had mentioned to me that he was going to take a course in the Sacramento Valley And I went along because it sounded like a lot of fun. And at that time, the novice license was administered usually by a club. And it was a fairly simple exam, except we did not have the questions and answers ahead of time. We had study guides, but not the precise question. And you had to pass 5 words per minute, sending and receiving. At that time, the license was good for 1 year and not renewable. So you either upgraded or you were finished. And so there was this pressure to upgrade, which I do to general.
Let's go back a little bit. Did you have an interest in electronics and radio even before your friend said he was going to take the test?
I sure did. I was the kid who took apart everything he could get his hands on to see how it worked, much to the dismay of my parents who found things broken that I had taken apart. But yes, I did, and I was really curious about how things worked electronically. So I built a shortwave receiver. At that time, there were catalogs, and I would collect those catalogs from Allied and Lafayette and other places and page through them for hours on end, looking at the various parts, and occasionally would build some of the kits. For example, Heathkit was out there, and I built some Heathkit projects. So yeah, I had an interest in it, and still do to this day. I enjoy building a lot.
Was your father also enamored with electronics? Did somehow that run off on you?
No, I was unique in the family in that regard. He worked in the studios and was interested in film, but no interest in ham radio. My brother was an athlete and a good student, and eventually became a judge, as a matter of fact, in LA County. But no, I was the only one that had an interest in it, and they encouraged it. They thought it was a good thing, and it was.
Now, before we started, you said your father worked in the studios. We're talking about the Burbank studios, probably, right? Which was the center of television in the 60s.
He did not. My grandfather worked at Warner's and was a assistant director there on a lot of movies. If you go to imdb.com and type in Frank Southwell Heath, he's got, I think, a couple of hundred credits. My father has quite a few too, but he was mostly at Desilu and worked for Lucy and Desi. In fact, for those who are Trekkie fans, you'll see his name at the end of Star Trek as post-production executive.
Oh, that's pretty amazing. Our paths might have crossed there. How about that?
And how would that be?
So one of my friends at the time, his father was a director of half of the early Star Trek episodes, a guy named Leo Penn.
Oh, yeah, sure. I spent a lot of time at the studio, and Desilu was located in the old RKO studio, and Paramount was on the other side of the wall. And when I would go to the studio, I was usually assigned somebody to keep track of me, like a handler. And I would go to the prop department and go to the microphones and radios. And it was a lot of fun to look at all the old microphones and radios. I spent hours there looking at stuff.
Yeah, I bet they had a lot of great stuff.
They did.
Okay, so you got your novice in 1964. How old were you then?
I was born in 1949, so I would be 15. Actually, would have been prior to my 15th birthday, so 14 years old. And then at that time, you had to take the general class exam or the tech exam at the FCC office in your area. In our case, it was downtown LA.
Right on Flower Street or something like that.
Yeah, it was a federal building, and it was, for a youngster, it was pretty intimidating.
I'm sure. What was your first call sign?
WN6JZC, JZC.
You did upgrade to general class?
I did. As I said, you had to take the test downtown LA, and I failed it the first time. You had to copy 13 words per minute, 65 characters, and it was in a room that I can still smell that room. There were wood desks on rails, one attached to the other, so what you were writing on was relatively small. It was attached to the seat of the guy in front of you, and if he moved, your desk moved. And in this room, and maybe it's necessary, but there was windows down the left side and the forward side. The forward side were the FCC employees The left side was a gallery, a place for people to watch. The room had wood paneling, and it was really echoey, and the guy would start a machine that sent CW, and you had to copy, and they sent, I think, for 5 minutes, and you had to have 65 characters in a row correct. If you had 60 that were correct, you failed. Even if you had 60 and then 60 again, if there was a mistake in the middle, you failed.
It's my understanding, and I think I heard this from Gordon West, that they used to transmit that CW test over some kind of like AC, very low frequency transmitter, and use wireless headsets.
No, when I took it, no, it was large speakers above a machine that played tape. I recall it being like a paper tape of some kind. It was
an instructograph.
Yes, it's what it was. There was 50 to 60 in the room, about half would fail. The receiving part, small percentage would fail. The sending part, that guy was tough. You had to send perfectly with a straight key, and then you took the written exam after that. So it was a 3-step process.
So you finally passed the second time you went in.
I did, yeah.
And your call sign upgraded to WA6?
They were WB6s at that point. There was a huge influx of amateur radio operators at that time.
What was your first rig like?
I was pretty lucky. I had a Johnson Viking Ranger, bought at Henry Radio on Olympic Boulevard in L.A., and I had a Hallicrafters SX-111, which was a pretty darn good station for a novice.
And what did you like working?
At that time, you had no choice. You were crystal controlled. So it was CW, and I was on 40 meters, put up an inverted V, got on the air with that. It wasn't very high, but I sat up on the roof and put together a dipole, and I didn't have an SWR meter, probably didn't even know what one was. Just put it up, hooked up RG58, went on the air.
Well, with a Johnson Viking Ranger, I think you could tune the final and actually probably match the antenna with the output.
Yeah, you could. It had a generous tank circuit, and you could load just about anything and have fun. And we did. We had a lot of fun. At that time, since you were still controlled, you might call CQ on one frequency and then have to tune. We had 7150 to 7200 on 40. So your crystal may be 7152, and the guy that's calling you is 20 or 30 kilohertz higher. You had to tune up and down and look for that guy. And that's what we did. So we were always kind of split. And at that time, not many hams had transceivers, and it was mostly a transmitter and a receiver.
You were living there in the golden age of ham radio clubs, I would think, as well. Did you belong to a ham radio club as a teenager?
I was so lucky in that regard. There was a company in Burbank called Lockheed Aircraft. And they had a huge organization called the Lockheed Employees Recreation Club, Amateur Radio Club. And a guy named Bill Welsh, his call sign was WA6VTL, and his wife Marie was WA6VTM. They moved out from the East Coast and geared up novice classes, and they ran thousands of people through their classes month after month. They were generous with their time and coaching. If you needed something, Bill Welsh was at your front door to help you out. And so there was that radio club with about 120 to maybe 200 members, and they were creating novices by having these classes. And I took the general class course with them, and that's how I passed the test downtown LA.
Did you do your field days with them?
I did, and they were great. They would go to one of the local parks. Burbank had lots of parks. Burbank was good in that they encouraged ham radio. In fact, I was member of the Burbank Civil Defense. I still have the badge. I hung on to that. And they had, I think, 100 ham radio operators as part of their group of responders.
Did ham radio play a part in the choices that you made for your education and career?
I tried, but it did not. I went to Pierce College, and I received an A.S. in business and a B.S. No, it was an A.A. and a B.S. at Cal State Northridge in finance. At that time, I was encouraged not to take engineering courses by the counselors at Cal State Northridge, and their response was that this was 1969 to 1971, that there are no jobs for engineers. So do business, and that's what I did.
That's very interesting because I think I remember that time. That was right after we landed on the moon.
Yeah.
So Southern California was very heavy engineering all the way up into that point, and then all of a sudden the landing on the moon and then engineering was over.
When you said that, it reminded me of where I was at the time. In Burbank, there were 3 stores that sold ham radio equipment. I worked at 2 of them. In Burbank, there were 3 places where you could go and buy something, and one of them was a place called Electronic City, and I was in that store at that time. And we had Collins, Drake, Galaxy, Swan, Hallicrafters. We had the complete Collins S line on display in the console, and it was a neat place to work. And during that time, the landing, I was in the store.
I remember that day as well. I was in Canoga Park watching it on television, so that was really cool.
Yeah, it was amazing. We had pictures. As rough as they were good.
How did you end up pursuing your career then? And did amateur radio play a part in that at all?
It, for the most part, did not up until later in life. I ended up working for a company that was 1% of the gross national product of the country. It was the #1 retailer in the country, and I spent a lot of years at Sears Roebuck and moved from store to store and facility to different facilities. And it was a good place to work. It was a neat company with neat people. After that, I went to work for Los Angeles County as an appraiser, and ultimately we relocated to Grass Valley. I worked for the county, the Grass Valley area called Nevada County. And later in life, due to an accident, and I mean an accident, I ended up manufacturing motorized mobile antennas for about 10 years.
Let's go back a second, if you don't mind. You were working at Sears Roebuck at a time, I think, probably, would you say it was after 1970? So you actually, after you graduated?
Yeah.
And I think they were building stores like crazy in Southern California in those days.
They were. Like I said, it was a good company. Each store was almost a city. In one of the stores I worked at, we had an optometrist, we had a key guy, we had all kinds of, we had tuxedos, you name it. There were all these ancillary things that made money for the store. We had carpenters, security guys. There were probably 1,000 employees in that store. One of them was in Long Beach that I worked at in downtown LA, and El Monte. It was a neat company. Nice folks.
Well, my father was opening May companies in those days.
Ah, yeah.
When you're talking about moving store to store, we were like military brats moving from city to city.
Yeah. A lot of my friends went to work for May Company. In fact, my brother-in-law worked for May Company in Whittier.
Oh, how about that? My father opened Westminster.
Ah, okay. My wife worked at the Westminster Sears.
Yeah, in fact, as I remember, this is a ham radio aside for a second, that Sears was the first department store in Southern California to actually open on Sunday, as I recall.
I believe that to be the case, yeah.
Because I remember going there with my dad once. He was kind of doing some spying for the May Company to see what Sears looked like on a Sunday, whether it was busy. And as I recall, it was quite busy. So I think that's probably set the ground for everyone to be open on Sunday. Now, you talk a little bit about an accident that you had. And I think that it sounded to me like, at least when I read, was that accident was kind of pivotal in terms of the way that you changed your life. Do you want to talk a little bit about that kind of accident and maybe how that could apply to hams?
Well, I guess there actually have been 2 series of events that were life-changing. In 1988, I was working as a self-employed building inspector and expert witness. I would testify in court on construction defects. And it was a rainy day, and I went to look at a building and climbed up the ladder and fell. I fell roughly 14 feet, was knocked unconscious, and broke my neck and a lot of bones. I fell across some steps, and that really brought any kind of building inspection work to a halt. And a local guy had started manufacturing his motorized antennas, and I purchased the rights to his antenna and started manufacturing, and we did really well for about 8 to 10 years doing that. And it was a lot of fun. We traveled to a lot of shows, went to Florida. We did a couple of different shows in Florida. Of course, we went to Dayton.
What was the name of that company?
High Sierra Antennas. And we were at Dayton, the smelly building on the other side of the wall from Bob Heil and Heil Sound. That's where I met folks like Walker Novak from ICOM and other guys who were major players in the ham radio business. Really enjoyed it.
Did you stay in the ham radio business? You were doing the High Sierra antennas for 8 years. Did you close it or did you sell it off and move on?
Well, that was kind of the second accident. Not to dwell on too much, but in November 2nd, 2016, I had gone to emergency rooms during the course of the year prior to that with some complaints, shortness of breath, and other things. And it was blamed on just working too hard. Well, it wasn't. And I suffered massive pulmonary embolisms. We called 911. It was 2 or 3 o'clock in the morning. And it does relate to ham radio, and I'll explain why in a second. I was rushed code 3 to the hospital. They finally gave me the right kind of test. And on that test, if you score higher than 500, you're in trouble. I scored the highest that anybody had scored at that hospital. And by the way, I had worked at that hospital as an accountant for 3 years, in between moving up there and going to work for the county. 12,216. In fact, it was so notable that they wrote it on the whiteboard above me, and doctors came in just to talk to me about it. My lungs literally had filled with blood clots, and I couldn't breathe. So they did a scan after the blood test and found that I had almost no lung capacity left. And Lovenox was applied then several times over the next week. I was in intensive care for a week, and then I was discharged to home. As a result of that episode, I suffered lung damage, lost about 25% of my lung capacity, and heart damage. And subsequent to that, I have been diagnosed with severe osteoporosis. I have the bones of a 9-year-old person. And as a result of all that, I surrendered my driver's license, and we moved from the mountaintop where I had 3 towers up to the valley floor to be in an area that's relatively flat and close to our oldest son and his wife, who can come by here when needed, and they have.
You actually brought this pulmonary embolism up earlier than I was going to ask about it. And the reason I was going to ask about it is you actually did a YouTube video about it. You want to explain how that applies to ham radio? Because I thought that that's really a message that hams should hear, actually.
It does, and it was a difficult video to make. I'm having difficulty talking about it now. We're not sure what caused my lungs to fill up the way they did. It didn't occur overnight. It didn't occur in a week's time. I say a week's time because I'd been in the ER a week prior to that. It occurred over a period of time, and it may be that as a result of sitting at a desk too long, that I was developing blood clots in my legs, and they were working their way into my heart and lungs. And as a result of that, the lungs filled up with the blood clots to the point where I couldn't breathe. And that's where we knew we had to call 911. So for those who operate contests or sit at a desk for a long period of time or chase DX, the word from the doctors is get up and move. Get up and drink lots of water, which I wasn't doing, but move. And they recommend 30 to 45 minutes, get and walk around. So if you are in a contest, you're going to have to get up. If you don't, you run the risk of forming blood clots. And a huge number of people who do that do not make it to the emergency room. Something like 75% die on the way there because you can't exchange oxygen into your blood. So it's critical to move. And that's why I did the video. Get up and move. As I say, we're not sure what caused mine. It may be related to something else. But the damage for me has been done. And there's no fixing it. It's the way it is. But the good news is I survived the event, and a lot of folks don't.
Well, I think that deep vein thrombosis is actually the term for sitting too long and causing the clots in the legs. I know that when you travel internationally, oftentimes they'll tell you that what you should be doing is, every hour or so get up and walk around a little bit to kind of get the circulation back in your legs. But, as a ham radio operator and as a guy that works a desk, it's easy to spend hours and hours at your desk and not moving, and you can have the same deep vein thrombosis in your legs, especially as you get older, if you're sitting too long.
The other side of that is also to drink water, to force feed water, even though you're not thirsty. Keep pushing fluids. It's a serious disease, and it kills a lot of people, and it's not discussed. The fix for that is not a great one either. I won't mention the drugs that I've been on, but they're highly advertised on TV. They have their own, and boy, this is off topic, they have their own set of problems. So, in fact, I'll admit this. doctor entered a new diagnosis on a list of things that's wrong. And the new diagnosis is long-term user of anticoagulants because there's significant issues with doing that. So if you're a ham radio operator and you're operating contests or you're sitting at a desk or whatever you're doing, get up and move. If you have a cell phone, set a timer on for 45 minutes, get up and move, and do that with a glass of water.
Great advice. I've had guests on in the past that have had serious medical conditions that affect ham radio operators. And so I think it's always good that when we can, we should touch on those things. I think that we're like your generation and mine. I'm not far behind you. But I think we're the first generation that is really spending more time in chairs than we do out of chairs, right? And so we've kind of set in motion a new lifestyle that our children are following, and that is that we don't get as much exercise as we used to because we work in chairs instead of, working outside.
Yeah, I think that's true for programmers and other folks. My son is an IT guy and probably sits too long.
Having a standing desk could also be an interesting way to get around that.
Like Rumsfeld did, yeah. Stand up and move around and just even a few minutes of moving and just get up and move.
I'd like to talk about your YouTube channel, but before we do that, let's talk about what the current rig is. It's very impressive on your YouTube channel because you've got a lot of real cool stuff. Could you talk a little bit about what the current rig is? And because you live in an HOA area that you said earlier before, what all that equipment connects to?
When I worked at Mr. Burbank that sold ham radio equipment, I fell in love with Drake stuff and still do to this day. I just think it was neatly designed. The closest, maybe it's a stretch, but the closest equivalent, and maybe folks at Aircraft is Elecraft remind me, it's so well designed. So I really like Elecraft equipment, and I've been fortunate to be able to have a couple K3s. So the current station is a couple of K3s. I have a Yaesu FT450 with a handle on the side. It's a great transceiver to take out and use outside and play with. I have an Elecraft amplifier KPA 500 and an Elecraft antenna tuner. Some Drake antenna tuner, some Drake watt meters. One of the things I have enjoyed doing and plan on doing again soon is I like building things like whether it's antenna switches or more complicated things like linear amplifiers. I've built several over the years, and antennas. Antennas are lots of fun. And you asked about HOAs. The HOA for the subdivision is extinguished for the most part. There is a county general plan, and I live in a city, and the city has adopted the county general plan, and it is pretty strict. To back up just a bit, I did do some time as a county building inspector and at a county tax assessor, deputy building inspector, deputy tax assessor. I also served as a planning commissioner in Nevada County. I was on the fire code board, the building code board, the board of appeals, numerous committees, ARES, RACES, participated in several emergencies. During the fire in Nevada County, I was the head of the communications group, and we had 120 ham radio operators involved in that. So the city of Rockland has a height limit of 30 feet, and they enforce that. So I have spoken to the chief building official, and 30 feet is permissible, 31 is not. So I have constructed an antenna tower that has a maximum height of 30 feet. And I use a little box that I've designed to run up and down because it's a little hard for me to crank the handle, so it has a winch. And in the last few weeks, I've added a device to pulse the motor so it goes up and down smoothly and quietly. Right now, I'm working on a limit to keep it at 30 feet and no higher.
So that antenna goes up when you want to operate, or it's up all the time?
That's what I'm trying to accomplish, is with it all the way down to about 20 feet, and then run it up when I'm on the air, and then bring it down when I'm not. And I'm doing that manually right now. The original motor, which was from a local automotive supply house, at 12 volts was just too noisy and too fast. So I built a power supply with a Variac, which weighed a lot, and I would haul outside and run it up and down while I got smart. And I used a switching supply and pulse width modulation, which I'm going to do a video about, to run it up and down, and it maintains the torque on the motor, but allows me to go very slowly, just crawl as it goes up, so as not to attract neighbors.
And what kind of antenna do you have on top of the tower?
At my old location, I had 3 towers. I had 6.5 acres on the top of Wolf Mountain in Nevada County, and I had phased Yagis on 20. When we moved, I sold off the towers and kept 1, and I brought all the tubing, which was occupying a good portion of the yard, so I've had to put it in various places where it's kind of out of the way. With that tubing, I constructed a 3-element monoband Yagi, or 20 meters, so it's 3 elements on an 18-foot boom, and it's a pretty simple design, but it's just one that I sort of cobbled together out of pieces from other antennas, and it worked great.
And of course, you have wire antennas for the other.
I'm a big fan of wire antennas, especially dipoles. And I talked to a guy yesterday who just got on the air. He's a half mile away, and was encouraging him to build his own dipole. It's simple to do, and string it up and have fun on HF.
Now, in your place, do you actually have other 30-foot poles to hold up the ends of your dipole?
I don't. Right now it's tied to the fence, and the fence is about 8 feet tall. So it's more like an inverted V. Behind the house is open space that belongs to the city. I would love to string an antenna into one of those trees, but I think that would probably not be a good idea. So I'm staying on the property, and I've gone to fence. And even though it's not as high as I would like, it actually works pretty well.
Now, you've got 2 rigs. I also saw what looked like 2 Drake amplifiers on the right side.
You've got good eyes. I do. One is a highly modified Drake L4B with a power supply and higher blade voltage, and some other things. There's some flaws in the L4B, in that the on and off switch will fail, so it's got a device to turn it on with, not the front panel switch, a relay, and some other things. By raising the plate voltage, you had to add some buys. And that's kind of the fun of modifying equipment. What can you do to make it better? The other one is very much a different amplifier on the inside. I have a good friend in Russia, and he provided some Russian tubes, and I put one of those Russian tubes into that amplifier, and it has a power supply that's about 70 or 80 pounds, and it runs 1,500 watts, cool as can be.
Now, are you a contester? I mean, you got 2 K3s parked side by side. Do you operate SO2R or something like that?
No, a couple things. I enjoy DXing. I've worked every country in the world, including North Korea, and that's been a lot of fun. I've had some just phenomenal contacts with guys like JY1, King Hussein, and received a QSL card signed by him. Neat guy. I can still hear his voice. It was a truly fun thing to work with that guy. Father Moran in Nepal, 9N1MN, Mike Moran. A guy in Galapagos Islands, HC8FN, Forrest Nelson. So I enjoy chasing DX and got hooked on that in the early part of my career as a ham radio operator, probably 1967 or so. At that time, of course, there wasn't the internet. And I used to get on the phone with a buddy in the valley, and we would hear something and then call each other and say, there's this DX on this frequency. And we would do that all morning long before we went to school.
Do you have a favorite operating mode?
Yeah, I do. It's not CW, it's sideband. And I think the reason for that is I enjoy chasing DX, but I also enjoy talking to somebody at length. It's amazing the people that you run into. Ham radio, as an aside, ham radio operators, it's an amazing group. It's a diverse group of mostly men, probably 95% men, and 5% women, but they run the gamut, and in many cases their story is fascinating, and I've enjoyed chatting with folks, and in some cases become friends for more than 50 years with some of these guys. And ham radio operators are very generous, nice, for the most part, nice guys.
I get that. I think I believe that as well. After you're going to be number 320 here, so I've had 319, now 320 great conversations. As of this QSO, you have 146 videos and over 30,000 subscribers to your YouTube channel. Why did you start a YouTube channel, and what did you hope to achieve from it?
As I said, in Burbank, and I was lucky in a number of ways. There was a Lockheed Club, but there was almost a ham radio operator on every block. And so if you needed something or needed an explanation on how something worked or getting something going, you didn't have to walk very far because I didn't drive at the time. You could go over to that guy's house, and they were willing to show you and oftentimes give you what you needed to get it going. One guy in particular, I went over to his house, and we became friends until he passed away. His call was W6BQW, Lou DeVilleneuve, and his wife. And in fact, as an aside, their house was on the corner of a street, and across the street from that was the grammar school that I went to. And as kids, one of the dares that one kid would issue to another was to ride your bicycle up their driveway, up Pat Lou's driveway, down their walkway, make the turn, go down the side of their house and down the other driveway. And I did that as a kid, and much to the upset of Pat. I never told him the story, but I rode my bike, and she yelled at me, "Oh, you kids," and and that thing. Well, years later, I was there, almost every day with something or other. And Lou would help me. And Lou had a way of explaining things that was different from a lot of guys. And that was, he could break it down into, he was an engineer at Lockheed, but he could break stuff down into the simplest language and idea, and you could get it. You could understand it. And you could go home and apply it. And I've tried to do that on YouTube. Today we have the expression Elmer, and I've tried to be a YouTube Elmer for basic ham radio things and apply explanations. I'm not an engineer, but I've had a fair amount of experience in explaining why things work the way they do, or why they don't, or in some cases it's as simple as how to set the mic gain on a transceiver, or to build a dipole antenna, or what happens to coax if water gets into it. Any number of things like that. And in fact, as I'm sitting here, I've got 3 or 4 projects in front of me that I intend to record in the next few days. One of them is building an M0ODZ, and how you do that. And in that discussion, talk about inductive reactance and capacitive reactance and how that applies in an M0ODZ. So I'm trying to pay back the guys that helped me. And most of these guys that I knew were from World War II, and really enjoyed helping out the other younger hands in the area. And in my case, one guy in particular, and really became like a second father to me. He was just a great guy. And no matter what I needed or needed to have done, we'd go out to his garage and rummage through stuff and find the parts, and I'd go home and fix it. Or more than once, I put something in a wagon and rolled it over to his house to be fixed.
You received the Elmer Award from the ARRL. What is the Elmer Award, and why did you earn it?
Well, I was thrilled to get it. And a fellow on the East Coast, Mark, on, I'm going to MFB, I'm going to say his call right and wrong, MFB, I think, applied and got it for me based upon my videos and helping him and others out. And I was ecstatic to receive that, because it was validation that I'm helping some folks. The 30,000 subscribers amazes me. One of the videos has had over 400,000 views. And as I move through this part of my life where I'm disabled, it's good that I can do something and pay back. I can't go over and help a local guy put up an antenna. I can't lift anything anymore. But if I can show somebody how to make a dipole or how something works, for me, that's great.
Well, I think that one of the things that impressed me about the videos that you're making is that you're also, I kind of like the world as it is according to Jim. So every once in a while you'll have a ham radio related video, but it's kind of like your worldview on the subject.
There is that. There are some topics, though, that I don't discuss on the air. And when I'm operating on the air, I try to set the example of being the best that I can be. And I have this, I'll explain, I have this fear of us losing frequencies because a big business needs them. And we lose 20 meters. And so I encourage everybody to be respectful on the air, to get along the best we can, to not have arguments. I don't want to have somebody, and this is the thing that I envision, a company gets in front of the FCC panel and says, we want 20 meters, we can use it for X, Y, and Z, whatever it is. And they play a recording of some arguments going on, or some negative things being said to the FCC. And it puts us in a bad light. So I think we should try to be the best we can be. And for 99% of us, that's not a problem. And for those who sort of cross that line, I've done this more than once, is to talk to them on the phone. about their operating habits, or maybe rethink what they're doing. Some folks are not going to change, but some folks you can.
Are you an official observer?
No, I don't even know if that still exists. I'm not. I think they were going to gin that up again, and I don't know where that's gone. I'm a life member of the ARRL. I have been there. We need that organization. We need them to succeed and be influential. We need to support them because they're really the only folks that can help us out if somebody does decide they want to take a portion of a ham radio band.
Yeah, I interviewed in episode 311 Riley Hollingsworth, K4ZDH, and he was talking about that there's actually, through his efforts in the ARRL, there's now an officials observer organization now, at least to monitor what's going on and we self-police.
I will check into that because Riley Hollingsworth is one of the best guys for ham radio ever. So if he's part of it, it's going to be good. There are a number of hams who are outstanding, and he is one of them.
Also a nice guy.
Yeah, he is. He had a difficult job, though. Code enforcement, law enforcement isn't easy, and that's kind of what he was doing. You said the word ham. Do you know where that came from?
Word ham?
Mm-hmm.
You know what? I have my own ideas. Where do you think it came from?
Well, I've done a bunch of research on it. It comes from the days of telegraphy, before there was radio. And a telegrapher who was a poor operator would be referred to as ham-handed, and they had another term for him that was railroad-related, like spur. That may not be the right word, but ham-handed, a guy who was sloppy in the way he sent or didn't know what he was doing. And I couldn't find it in any radio magazine or book through the teens. It appears in the early 1920s as a derogatory comment about guys who were on the air who are not commercial operators. And I confirmed some of that with 6 Delta Phil Keast, who was my neighbor. He was one of the first ham radio operators in California. He first went on the air about 1914. Great guy. And the expression ham was derogatory, but it stuck. And it had nothing to do with kids going in front of Congress with the initials HAM, which has been bandied about. It just was a comment about the way a guy would send and lack of skill.
I'm looking in Merriam-Webster's dictionary, and it says ham-handed or ham-fisted was clumsy, graceless, heavy-handed. So perhaps that's where it came from, huh?
I believe that to be the case, yeah.
Your videos are great because your beautiful ham radio station is behind you. But I notice on the left that you also have some test equipment. What is the most exotic piece of test equipment that you have behind you there?
I'm looking over there now. A lot of that is from surplus stores. The most exotic, probably the pan adapter is from the 1970s, kind of a neat thing. But today, we have equipment like the nano VNA and other things that in the size of a deck of cards can outperform that device. And more things are coming our way, which is really neat. It's an exciting time to be a ham radio operator for many reasons. Digital communications, equipment that in years gone by would have been thousands of dollars now is in the tens, $40, $50 you can buy something that will do amazing things. So as far as exotic equipment goes, probably some of the newer things, I enjoy antennas, so antenna analyzing devices are the things that I enjoy most. I do have bird watt meters and a bird dummy load and stuff from the 1950s and 60s. But the exciting things are the things that are coming our way that are relatively new, that allow us to analyze what we're doing and how things work in a way that wasn't available to us just a couple of years ago.
Do you have a 30-second elevator pitch for ham radio? If you meet somebody on an elevator and they say, "Oh, you're a ham radio operator," do people still do that?
They do, and it's what the question you get is, it still exists? It does. It is, and especially today, as we're recording this conversation, part of California, a good percentage of it is on fire. And in many instances, ham radio is the only means of communications left. Cell towers can be destroyed during fires and earthquakes. We found during the fire in Nevada County, the 40 fire, we lost 300 houses, and it was about 100,000 acres. that the state system became overloaded, which is likely the case today. And ham radio operators stepped up. There was 120 of them, along with guidance from I was volunteering with California Fire Department, CAL FIRE. A guy ran an amateur radio group, Charlie Jacobs, KC6LKC, and he had us organized to participate in fires, and we did several. And we provided backup communication. So ham radio, elevator pitch, ham radio is diverse. Just about anything that you can think of, you can do in a ham radio, whether it's building, experimenting, digital communications, send pictures, setting it on, sending a signal from here to the other side of the planet to talk to a guy in Nepal or somebody in India or Pakistan, or just chatting with friends on the other side of the planet. I have friends in countries, some near you. One is an Air Force general. So if you want to just talk with somebody, if you want to experiment, if you want to get involved in computers, digital communications, even photography, there are facets of that in amateur radio. Talking to the space station, communicating through it. There are so many things you can do with amateur radio. It's absolutely amazing. Another thing I'd like to emphasize. Oftentimes, and it's true, someone will say, ham radio or amateur radio is a great hobby. It is. It really is. It's amazing. And I've been at it for 56 years. But it's also a licensed radio service, and I underline the word service. And ham radio operators are good at providing service. And in many cases, it's done quietly. During the 40 under fire, for example, many ham radio operators were best in the service. Their job was to be a quiet walkie-talkie in a way, and that they provided a second means of communications for the fire captain that they were assigned to. They didn't chat with the fire captain. They merely, when something came through that needed to be sent to that fire captain, provided that information in plain language. I emphasize plain language because that's the way it should be done. So we are a licensed radio service, which is one of the things that I mentioned to the city when I was talking to them. It's not just a hobby. First and foremost, it's a federally licensed radio service, and we provide a service in many instances that is absolutely needed. And I would say in California right now, in many locations, it is being used to provide secondary communications, and it may be simple things, and it may be complex. It may be tracking the fire. It may be somebody assigned to a lookout tower where he or she is reporting the location of the fire. All those things go on quietly in the background and don't always end up on the 6 o'clock news.
Well, like one of the things that also people may not realize that in all those areas where those fires are, all of that infrastructure is above ground, right? All that fiber, all that copper, everything that supplied, high-speed internet service to all of those residents up there, that infrastructure is now completely gone. So ham radio could be playing a role for some time until that infrastructure is replaced with microwave cell towers or whatever else that needs to go into those places. But it seems to me that amateur radio operators will play a role for some time in these areas.
They will, and they will do it without compensation, and they will do it with a smile on their face, and they will do it for as long as they're needed. Ham radio operators are really good folks. I've benefited from that in ways that I haven't explained, but when I've needed help with something, you don't have to look very far. There's a guy in town who will help you. Oh, not necessarily just town. It's a quick story. I'm recovering from the pulmonary embolism thing, and I'm in a special chair in the living room, and the phone rings. And it's a Dr. on the coast. He looked my phone number up, got it, called, and left a message as I was sitting there to the effect that he was a doctor. If I needed any help understanding what was going on, that he was an expert in the field, and he would be happy to help me. Now, here's a guy who's, by the way, he is a world-renowned doctor since retired, who took the initiative to contact me to say, "May I help you?" And that's an example of how nice ham radio operators can be when needed. They're generous.
Is he a ham radio operator?
Yes, he is. He has a phenomenal collection of gear, and we become very friendly, and we chat once in a while. I'm not giving his name and call sign, but he is well known.
I actually may know him.
Okay.
But I won't say anything.
Yeah, neat guy. But just an example of I did pick up the phone. You know, it's happened here during a recording. We get phone calls all day long, people trying to sell you something, or you know, home loan or whatever. And so I tend not to answer the phone. And I was blown away by this guy. And you become skeptical initially, but in talking to him on the phone, what a neat guy. He had to take time out of his day to offer help.
Right.
To somebody he really didn't know.
Amazing.
Yeah, it is.
I think that's what I found with ham radio mostly attracts very generous people who are generous with their time, and they like to teach, like mentor, they like to learn. I think maybe that's one of the great things about ham radio. It's a great hobby to learn. As you said earlier, you can learn anything and connect ham radio to it in some way. Do you have advice for new or returning hams?
Yeah, I do. Have fun. I have a different approach to getting the license, and some may not agree, and that's okay. Pass the test. And in some cases, it may be as simple as memorize the question and the correct answer and let it go at that, just to pass the test. You will learn as you do things. We have a resource today that's phenomenal, and you have to be careful about who you watch and listen to on YouTube, but the ARL and other organizations, there's a whole bunch of information. So get on the air, especially HF. Get on HF and have fun. Communicate with people. I've said this many times, we're not broadcasters, we're communicators. Engage in a conversation. Ask them. There are some topics I don't discuss. I don't discuss religion, and I don't discuss politics, but everything else maybe is okay. You'll find connections with people that when you started out, you had no idea was there. So you'll find niche industry. There are so many different ways that you, for example, you mentioned a HOA. Let's say you're in an HOA where antennas are absolutely forbidden. You can still get on the air, and you can still work the world. And I worked a guy in Mozambique doing this. Do digital communications. The guy that's coming up with these schemes for digital communications is amazing. And you can have headphones on or a speaker running and hear nothing, but your equipment is decoding that guy's signal from the other side of the planet or from the other side of the country. And it's doing it 100% of the time. So there are lots of ways to get on the air and have fun and enjoy it. It is a thrill to talk to somebody either digitally or CW or whatever means that you want, satellites. It's just a whole bunch of fun and enjoy it. And as you experiment and build things, you'll learn. So you may not understand what SWR means or how to set the mic gain, but you'll get it figured out. And that comes after you pass the test. Pass the test, get on fun. Get to know people in your area if you can. Get to know the local ham radio guys. Get them to help you if need be. Understand how things work, but have fun. That's my advice.
Yeah, usually all you have to do is ask.
Yeah.
You shouldn't be afraid of asking. You shouldn't be afraid of knocking on the door of the guy that has the antenna and asking for help.
And that's what I did, and became a 50-year friendship with the guy on the corner across the street from the school.
Right.
Yeah.
Well, Jim, I want to thank you so much for joining me on QRCode podcast. I really appreciate your taking the time and sharing for all those people that
Greg's going to show us how to set up an amateur radio station, and the first thing we need to do is identify all these items of equipment. So let's start with the heavy one.
Thank you, Bob.
PSU.
Power supply unit. That provides the electricity, the 13.8 volts DC required for the radio.
And that plugs into the mains.
And that plugs into the mains.
All right, we'll work out all the connections in a minute, but let's just look at the individual items. This?
The radio or transceiver.
Transceiver?
Yes, transmitter, receiver.
Oh, well, so it does what it says on the tin. It does the transmitting and it does the receiving.
Yes.
What about these two boxes on the end, Greg?
We have here the ATU or AMU and the SWR meter.
Oh, ATU and AMU?
Is the antenna tuning unit, or also known as the antenna matching unit.
What does that do?
This we use to ensure the antenna is on a resonant frequency by pretending it's either shorter or longer than it actually is.
I see. So what that does is it fools the transceiver into thinking it does have a resonant antenna.
Absolutely, that's exactly what it does.
SWR.
Yes, standing wave ratio.
A standing wave ratio, all right. So what's one of those when it's at home?
When you transmit to an antenna, we want all the power to go out of the antenna into the outside world. Unfortunately, if the antenna isn't quite resonant, some of that power will actually come back down the cable, back into the radio, as low as possible.
Oh, I see. So if you have a resonant antenna, then the SWR would be low by definition.
Absolutely.
If it's non-resonant, we can use that box to bring the standing wave ratio down.
Yes, that's correct.
Got it. Okay. So now all we've got to do is connect them together.
Let's connect them together.
We start then, Greg, with the power supply, the PSU.
Yeah, the power supply, which as mentioned provides 13.8 volts, has connectors, these, which fasten onto these poles here. One thing we have to make sure of is that the power is switched off before we start connecting. As you can see, we've got a red and a black wire. So red to red. Ensure it's finger tight, and black to black.
We've now got a power lead connected to our power supply, but we've got to plug it into the radio next.
We do that using this connector here, which connects directly like that, pushing until you hear the click.
And there's a number of other connectors on the back, but as with all radios, it's a particular shape. You can't accidentally plug it in to the wrong socket. We have power to our transceiver, and the next bit, it's quite important that we get the sequence the right way round.
The first connection from here is going into the SWR meter, and we're taking that from the transceiver port X, and we'll use a patch lead for that. In this case, it's PL259 to PL259. So we'll put it in and twist until the connector is finger tight. And the same on the transceiver end. Again, finger tight. And now we'll be taking it from the SWR, the antenna socket, which is just there. In this case, another PL259 patch lead, going from the antenna port to the AMU, to the transmitter port. Again, ensuring it's finger tight. And finally, we have the important part, the antenna cable. So again, we'll connect that into the antenna port and screw until it's hand tight.
When you're setting up your amateur radio station for the first time, that's quite a lot to take in. So let's just do a quick recap of the connections. We've started the power supply, the PSU, connected to the mains and giving us the 13.8 volts out that comes through this cable to our transceiver. Then from the antenna socket of the receiver, we've connected into the SWR meter here. The SWR meter is connected into the back of our ATU or AMU into the transmit socket. And then, of course, the important one, the antenna is plugged in here on this ATU. It's into coax 1. There's two sockets here, and you can select two different aerials from the front of the ATU. So those are our connections, and we're ready to go.
Okay, so we're going to demonstrate the use of an antenna matching unit to get the station ready to make a contact on 20 meters. Some radios, like this IC7300, do have an internal antenna matching unit, but that might not be suitable for the full range of antennas that you want to use. In this case, we're going to use an external one. You can get manual models, like this, or an automatic model. Similarly, some of them have an internal SWR meter, or you can add one external. Here we'll use the single needle external SWR meter. So we'll switch the radio on, and set it up on the 20 meter band. First of all, we'll make sure that we find a frequency that nobody else is using. We are going to be transmitting a carrier while we tune the antenna, and so we don't want to be interrupting anyone else. That sounds clear. We're going to need to transmit a carrier constantly, so I'll change to the FM mode and also reduce my power level to about 10 watts. You don't want to be transmitting any more power than you really need. There we go. We're now ready to start setting up the antenna matching unit. So I'll start transmitting. I'm going to use this external SWR meter. We'll start off by changing the function to the calibrate position and using the cal knob to set the needle to the calibrate mark on the right hand side of the scale. I'll then switch to the SWR position and we can read off our SWR on the top scale, which is about 4.5 to 1. That's not what we want. We're trying to get it down to as close to 1 to 1 or the far left hand side of the display as we can. I'm now going to start matching the antenna. I'm going to use these three different controls and the roller inductor. And I'm going to need to use each of those in turn to try and minimize our SWR. We're aiming for 1 to 1, which is on the far left of the screen. I'm now going to go to the first control and try and adjust that to see. So I've got the lowest value I can using these two controls. Now I'll come on to the third control. You can see that slowly coming down. Oh, and now if I carry on, it goes back up. So I'll look for the lowest point, and then come back to my first two controls. Each time I'm cycling through the three controls to get the lowest value I can. And here, you can see if I switch to cal, we're still at the right-hand side at the calibration mark. Switch back to SWR, and I'm now at an SWR of 1 to 1. This is now ready to make my contact on 20 meters. Now we're going to SSB QSO on HF. Here's my station, and I'm set up here on 20 meters. I've already matched my antenna, but we're going to find a frequency that's clear. That sounds good. We now need to set up the radio correctly. So I'll make sure the power is appropriate for this contact, about 10 watts here, and then adjust the microphone gain. At the moment it's at 0%, which means none of my audio will go out. For the 7300, I need to get the meter and compare check that my mic gain is about right. You should check the manual for your radio. So on a clear frequency, I'm watching this meter here. I'll start off at 0% and then turn it up gradually until the 2 meters read in the appropriate segments. This is Mike 0 Victor Foxtrot Charlie, testing 1, 2, 3, 4, 5, M0VFC, Mike 0 Victor Foxtrot Charlie. So you can see the ALC meter was in the appropriate segment and we had just a little bit of compression. If the mic gain's too high, your signal will be very distorted. If it's too low, then you won't be heard. Now we're going to check that nobody else is using the frequency as well as having listened, and then we're ready to start CQ. I've picked my frequency here by looking at the band plan. That's at rsgb.org/bandplans, and I can see here for the 20 meter band, for a single sideband contact that sits in the all mode section, and we can operate between 14.125 and 14.350. So this is a suitable frequency here at about 14.224. Is this frequency in use? We're not hearing any replies, which is what we expect. I'm now going to call CQ and see if anyone responds. CQ, this is Mike 0 Victor Foxtrot Charlie, M0VFC. Mike 0 Victor Foxtrot Charlie, CQ and listening.
Mike 0 Bravo Lima Foxtrot.
Mike 0 Bravo Lima Foxtrot, Mike 0 Victor Foxtrot Charlie, good afternoon.
Name is Rob, Romeo Oscar Bravo, and the location Bletchley. You're 5 and 9, M0BLF, M0VFC.
M0BLF, thanks for the information, Rob.
Nice to meet you. Name here is Dom, Delta, Oscar, Mike, and the QTH just down the road from you in Milton Keynes. And you are a good 5-9 signal here. Mike 0 Victor Foxtrot Charlie from Mike 0 Bravo Lima Foxtrot.
And Mike 0 Bravo Lima Foxtrot from Mike 0 Victor Foxtrot Charlie. Nice to meet you, Dom, and thank you for the nice report as well. Equipment this end is an ICOM IC7300 and running about 10 watts to a doublet antenna. Weather here at Bletchley, absolutely gorgeous sunshine. M0BLF, M0VFC.
Mike 0 Victor Foxtrot Charlie from Mike 0 Bravo Lima Foxtrot. Thanks, Rob. And yeah, running here an Elecraft KX2 with about 3 watts to a dipole antenna. So back to you, Mike 0 Victor Foxtrot Charlie.
And 7-3, and good luck with the exercises. Mike 0 Bravo Lima Foxtrot clear.
And there we have it, a simple QSO on HF single sideband.
What we're going to do now is demonstrate with Dan a very important principle of radio communication. What's that, Dan?
So that principle is that the length at which an antenna works best or is resonant at depends...
That we're going to be tight.
What is the software that we're using then, Dom?
This is some software called FLDG. It's free and it runs on most operating systems and it's really good for data modes.
It does RTTY, which is what we're going to use it for now, but it does do a bunch of other data modes as well.
Absolutely, there's a whole long list of modes that it supports. Some of them very popular, some of them not so much used. But yes, it supports most things.
Pretty good then, considering that it's a free piece of software. Just talk us through the screen, because there's different bits up there. How are we using and what are we using on that screen?
Okay, so the main bits are the yellow bit at the top, which is showing us what signal that we've received, everything that it's decoded. The blue bit at the bottom is where I'll be typing a message, what it's going to send.
And the black bit, that big black bit at the bottom?
So the big black bit at the bottom is called the waterfall. Nothing's happening there at the moment because there's no signals around, but when the other person starts transmitting, you should see their audio tones. Hopefully they will line up with the red bars because that's where it's listening.
Ah, because it's two tones, so that's why we can see those two lines.
Exactly.
Okay, let's give it a go. CQ and see what come back to us.
Okay.
You'll notice you put a K at the end of the sentence. That means
over.
What? Ah, right, so that means I've finished typing, your turn now.
Exactly. So M0VFC is coming back. He's now put KN on the end, which means over to the person I'm talking to only, rather than being general invitation. So I can now type back to him, go into transmit mode.
There's a possibility, I suppose, when we're using this kind of communication with RTTY, that part of your message might be lost if there's interference or fake. Actually, twice. Is that the reason? Just because that's an important bit of information.
Exactly. You'll notice I put the signal report twice, the call times twice, my name twice, but actually twice means if there's a little bit of fading on the band, you're still going to get hopefully the message.
And it's finished SK.
Yes. So it's another abbreviation. It derives from Morse code. It means the end of transmission. I've got nothing more to say.
So that's explained how we do a straightforward, simple data QSO. Dom, thanks very much.
We're going to take a look at Morse code. Now, Morse code isn't a requirement for the amateur radio license anymore, but a lot of operators still get a great deal of enjoyment from making contacts using Morse code. You can get some amazing distances with really low power and simple equipment. We send Morse code using a short dot or longer. So, for example, if I wanted to send the letter A, it's dot dash, or Q. And like that, I can send any letters or numbers that I want to. As well as the straight key here, which sends all the time I hold it down. You might also find people using a Morse paddle. This has two levers. The right-hand side sends dashes, and the left-hand side sends dots. And in the same way, I can use that to send any letters, for example, CQ. Now, I'm here at the National Radio Centre, so I'll send their call sign, Golf Bravo 3, Romeo Sierra. G, B, 3, R, S. And you use this to have contacts just like you would on voice or data. I'll just call CQ. And there we go. That's a quick introduction to Morse code.
Hello and welcome. In this video, we're going to demonstrate the different elements that would usually be covered in the Foundation Radio License assessments. We'll also include some extra things you might find useful as you put together your station and make your first contact. We're going to begin by setting up the station.
Greg is going to show us how to set up our basic amateur radio station, and the first thing we need to do is identify all these items of equipment. So let's start with the heavy one at the end here. Greg, what's this?
Yep, that's the PSU, Bob.
PSU.
Power supply unit. That provides the electricity, the 13.8 volts DC that's required for the radio.
And that plugs into the mains.
And that plugs into the mains.
All right, we'll work out all the codes in a minute, but let's just look at the individual items. This?
The radio, the transceiver.
Transceiver?
Yes, transmitter, receiver.
That does what it says on the tin. It does the transmitting and it does the receiving.
Yes.
What about these two boxes on the end, Greg?
We have here the ATU or AMU. and the SWR meter.
Oh, well, hang on then. ATU and AMU?
Is the antenna tuning unit, or also known as the antenna matching unit.
What does that do?
This is used to ensure the antenna is on a resonant frequency by pretending it's either shorter or longer than it actually is.
I see. So what that does is it fools the transceiver into thinking it does have a resonant antenna.
Absolutely, that's exactly what it does.
SWR.
Yes, standing wave ratio.
A standing wave ratio, all right. So what's one of those when it's at home?
When you transmit to an antenna, we want all the power to go out of the antenna into the outside world. Unfortunately, if the antenna isn't quite resonant, some of that power will actually come back down the cable, back into the radio. We want that as low as possible.
Oh, I see. So if you have a resonant antenna, then the SWR would be low by definition.
Absolutely.
If it's non-resonant, we can use that box to bring the standing wave ratio down.
Yes, that's correct.
Got it. Okay. So now what we've got to do is connect them together.
Let's connect them together.
We start then, Greg, with the power supply, the PSU.
Yeah, the power supply, which as mentioned provides the 13.8 volts, has connectors, these which fasten onto these poles here. One thing we have to make sure of is that the power is switched off before we start connecting. As you can see, we've got a red and a black wire. So red to red. Ensure it's finger tight. And black to black.
We've now got a power lead connected to our power supply, but we've got to plug it into the radio next.
We do that using this connector here, which connects directly like that, pushing until you hear the click.
And there's a number of other connectors on the back, but as with all radios, it's a particular shape. You can't accidentally plug it in to the wrong socket. We have power to our transceiver, and the next bit, it's quite important that we get the sequence the right way around.
The first connection from here is going into the SWR meter, and we're taking that from the transceiver port, TX. We'll use a patch lead for that. In this case, it's PL259 to PL259. So we'll put it in and twist until the connector is finger tight. And the same on the transceiver end. Again, finger tight. Now we'll be taking it from the SWR, the antenna socket, which is just there. In this case, another PL259 patch lead, going from the antenna port to the AMU, to the transmitter port. Again, ensuring it's finger tight. And finally, we have the important part, the antenna cable. So again, we'll connect that into the antenna port and screw until it's hand tight.
When you're setting your amateur radio station for the first time, that's quite a lot to take in. So let's just do a quick recap of the connections. We've started with the power supply, the PSU, connected to the mains and giving us the 13.8 volts out that comes through this cable to our transceiver. Then from the antenna socket of the transceiver, we're connected into the SWR meter here. The SWR meter is connected into the back of our ATU or AMU into the transmit socket. And then, of course, the important one, the antenna is plugged in here on this ATU. It's into coax 1. There's two sockets here, and you can select two different aerials from the front of the ATU. So those are our connections, and we're ready to go.
Okay, so we're going to demonstrate the use of an antenna matching unit to get this station ready to make a contact on the meters. Some radios, like this IC7300, do have an internal antenna matching unit, but that might not be suitable for the full range of antennas that you want to use. In this case, we're going to use an external one. You can get manual models, like this, or light model. Similarly, some of them have an internal SWR meter, or you can add one externally. Here we'll use the single needle external SWR meter. So we'll switch the radio on, and set it up on the 20 meter band. First of all, we'll make sure that we find the frequency that nobody else is using. We are going to be transmitting a carrier while we tune the antenna, and so we don't want to be interrupting anyone else's contact. That sounds clear. We're going to need to transmit a carrier constantly, so I'll change to the FM mode and also reduce my power level to about 10 watts. You don't want to be transmitting any more power than you really need. So I'll start transmitting. I'm going to use this external SWR meter. We'll start into the calibrate position and use the cal knob to set the needle to the calibrate mark on the right hand side of the cell. I'll then switch to the SWR position and we can read off our SWR on the top scale, which is about 4.5 to 1. That's not what we want. We're trying to get it down to as close to 1 to 1, or the far left hand side of the display as we can. I'm now going to start matching the antenna, and I'm going to use these three different controls: transmitter, antenna, and interrupter. And I'm going to need to use each of those in turn to minimize our SWR. We're aiming for 1 to 1, which is on the far left of the screen. I'm now going to go to the first control and try and adjust that to see a dip. So I've got the lowest value I can using these two controls. Now I'll come on to the third control. You can see that slowly coming down. Oh, and now if I carry on, it goes back up. So I'll look for the lowest point, and then come back to my first two controls. Each time I'm cycling through the three controls to get the lowest value I can. And here, you can see if I switch to cal, we're still at the right hand side at the calibration mark. Switch back to SWR, and I'm now at an SWR of 1 to 1. This is now ready to my contact on 20 meters. Now we're going to have an SSB QSO on HF. Here's my station, and I'm set up here on 20 meters. I've already matched my antenna, but we're going to find a frequency that's clear. That sounds good. We now need to set up the radio correctly. So I'll make sure the power is appropriate for this contact, about 10 watts here, and then adjust the microphone gain. At the moment it's at 0%, which means none of it. For the 7300, I need to use the ALC meter and the compression meter here to check that my mic gain is about right. You should check the manual for your frequency. I'm watching this meter here. I'll start off at 0% and then turn it up gradually until the 2 meters in segments. This is Mike 0 Victor Foxtrot Charlie, testing 1, 2, 3, 4, 5. M0 VFC, Mike 0 Victor Foxtrot Charlie. So you can see the ALC meter was in the appropriate segment and we had just a little bit of compression. If the mic gain's too high, your signal will be very distorted. If it's too low, then you won't be heard. Now we're going to check that nobody else is using the frequency as well as having listened, and then we're ready to start calling CQ. I've picked my frequency here by looking at the band plan. That's at rsgb.org/bandplans, and I can see here for the 20 meter band, for a single sideband contact, that sits in the all modes section, and we can operate between 14.125 and 14.350. So this is a scoring here at about 14.224. Is this frequency in use, please? Mike 0 Victor Foxtrot Charlie. We're not hearing any replies, which is what we expect. I'm now going to call CQ and see if anyone responds. CQ, this is Mike 0 Victor Foxtrot Charlie, M0 VFC. Mike 0 Victor Foxtrot Charlie, CQ and listening.
Mike 0 Bravo Lima Foxtrot.
Mike 0 Bravo Lima Foxtrot, Mike 0 Victor Foxtrot Charlie, good afternoon.
Name is Rob, Romeo Oscar Bravo, and the location Bletchley. You're 5 and 9, M0 BLF, M0 VFC.
M0 BLF, thanks for the information, Rob.
Nice to meet you. Name here is Dom, Delta, Oscar, Mike, and the QTH just down the road from you in Milton Keynes. And you are a good 5-line signal here. Mike 0 Victor Foxtrot Charlie from Mike 0 Bravo Lima Foxtrot.
And Mike 0 Bravo Lima Foxtrot from Mike 0 Victor Foxtrot Charlie. Nice to meet you, Dom, and thank you for the nice reports as well. Equipment this end is an ICOM IC7300 and running about 10 watts to a doublet antenna. Weather here at Bletchley, absolutely gorgeous sunshine. M0 BLF, M0 VFC.
Mike 0 Victor Foxtrot, Mike 0 Bravo Lima Foxtrot, thanks Rob. And yeah, running here an Elecraft KX2 with about 3 watts to a dipole antenna. So back to you.
And 7-3, and good luck with the exercises. Mike 0 Bravo Lima Foxtrot clear.
And there we have it, a simple QSO on HF single sideband.
What we're going to do now is demonstrate with Dan a very important principle of radio communication. What's that, Dan?
So that principle is that the length at which an antenna works best or is resonant at depends on the physical length of that antenna. So what we are going to do here is measure the SWR of an antenna and then see what happens as we increase or decrease the length of the antenna and try and tune it up for our chosen band.
So you've got your dipole antenna there. We also have this. What's this?
So this is an SWR meter, so it measures our forward power and our SWR.
And I've got the transmitter here to provide us with some RF for our test, so we're ready to go.
Correct.
What do we need to do first, Dan?
So the first thing we need to do is we need to adjust the SWR meter such that the power coming out of your transmitter shows us 100% on this forward power meter to allow SWR to be correctly calculated.
So shall I give it a little bit of a blast of RF and see where we are now?
Sounds good.
The power meter is not showing all the way to the end, simply without getting accurate SWR.
Yes, so we need to adjust the dial in the middle such that the power meter shows 100%.
Oops, that's a little fiddly. With my thumb, there we go.
Good.
And the SWR doesn't look so brilliant though, does it?
No.
Because we've got end stop on that, and the object of the exercise is to get that as low as possible.
Yes, so the ideal SWR is a value of 1.
Okay.
So a dipole antenna should be about half a wavelength long, a 1 meter total, and this is clearly too short. So what we're going to do is we're going to lengthen the two arms, making sure they're the same length, and the VSWR should decrease as we get closer and closer to our antenna working best on 2 meters.
Can I transmit while we're doing the adjustments?
No, we really shouldn't. The actual elements themselves shouldn't be touched, but this metal box in the middle is safe to do so.
Okay, so pull those elements out then and we'll do another test.
If I lengthen them both an amount, using a tape measure to check. So each arm is about 44 centimetres, so we should be close, not quite there yet.
So let's see what happens
And if we retransmit.
Now we can see that because you've made an adjustment, the calibration is off again, so I need to just tweak that so that the power meter is reading all the way to the end, then that SWR is accurate, still not good enough.
No, so let's extend our antenna some more and see if we can do better.
Okay.
that should be hopefully fairly bang on.
Right, let's give it a little burst of RF. Oh, look at that. That's pretty much
there?
Yeah.
Should we go try for a little
go
bit better?
a tiny little tweak.
Tiny little tweak.
Okay, I'm not transmitting.
Okay.
Oh, that's gone up now. So you were nearly there before.
Yes, so the antenna will not work if it is too long or too short, and we have overshot now. So if we decrease this a bit, and check again. Okay.
The moment of truth. And look at that, we have a perfect SWR of 1. That's our 2-metre dipole, perfectly tuned. We've demonstrated the principle. And of course, if you had a commercially available antenna like this mag mount to go in your car, it would be trimmed up already to be basically spot on for the band that you're on. But once you actually put it on the car, you can, using the Allen keys here, adjust the length of the element up and down very slightly to get a perfect SWR. And some people like to cut their own antennas for their mobile use, for example. So you can mount a quarter wave that you've made yourself onto the car, and you would perhaps trim the length of that whilst measuring the SWR. As per the principles that we've demonstrated here. And of course, it's not just a 2-metre or a 70-centimetre small antenna like this that these principles apply to, it also applies to HF.
If the SWR on your dipole is such that it needs shortening, then measure a section from each end, cut, and recheck as we've demonstrated. Oh, and make sure that you cut small lengths equally off each side of the dipole until the SWR is as low as possible for the band you're transmitting on.
When you've got that new amateur radio license, the most exciting thing is having that first QSO. And a great place to start would be with a simplex QSO on FM, perhaps some handheld. So we're going to do that, Greg, and we're going to do it on 2 meters and just show everybody the basic route through having a simple FM simplex QSO.
Yeah, absolutely.
So where do we start?
Well, we start by tuning to the calling frequency, which on 2 meters is 145.500, 145.5 megahertz, and we'll go on there and call CQ, which is asking for someone else to respond to us.
And what do we mean by the calling frequency?
The calling frequency is where people will listen, expecting other radio users to transmit and ask to make contact.
And I'd imagine that as the channel is used for calling, there shouldn't be too much activity on there, in the sense that once people have hooked up, got somebody to have a QSO with, they move off to another channel. So rustle up some activity.
Okay. This is Mike 0 Oscar Delta Zulu, Mike 0 Oscar Delta Zulu, calling CQ and standing by.
Mike 0, Whiskey Uniform Tango.
Mike 0 Whiskey Uniform Tango, this is Mike 0 Oscar Delta Zulu. Please stand by while I find a free frequency.
So what you're going to do is check that the channel you want to move to is also clear, and then you'll go back to him and tell him where to move to.
Yeah, he'll stay on the calling frequency until I return. So I shall go find a free frequency. This is Mike 0 Oscar Delta Zulu. Is this frequency in use, please? Now we'll just wait for a few seconds to see if we hear anything. And nothing heard, so we'll go back to the calling frequency. This is Mike 0 Oscar Delta Zulu for Mike 0 Whiskey Uniform Tango. Would you please QSY to 145525?
Roger, QSY 145.525.
That's great, so he knows now which channel you're going to actually go and have your conversation on.
The frequency in use, please, is the frequency in use.
Ah, so he's checking as well from his end to make sure that nobody in range of him is already having a conversation on this channel.
So I'll respond and say I've heard nothing. This is Mike 0 Oscar Delta Zulu. Nothing heard my end. Back to you.
Mike 0, Oscar Delta Zulu from Mike 0 Whiskey Uniform Tango. Nothing heard here either.
Mike 0 Whiskey Uniform Tango. The name this end is Greg. Greg, Golf, Roger, Echo, Golf. The equipment this end is a Baofeng UV5R running on the lowest power setting.
Yeah, Roger, Greg. Thank you very much for all the information. And I'm going to say thank you for the contact. And 7-3, Mike 0 Whiskey Uniform Tango. Back to you for finals.
Mike 0 Whiskey Uniform Tango from Mike 0 Oscar Delta Zulu. Thank you so much for taking the time to have a QSO with me today. I hope you have a great rest of your day. 7-3, this is Mike 0 Oscar Delta Zulu, clearing the frequency.
So that was interesting, following the etiquette through, because also at the end there, you made it quite clear to any other users of that channel that you had both finished and that channel was now free for use again.
You may find someone else might want to come in and have another chat. He would have come in the slight pause after doing 7-3 and before the clearing the frequency.
So if somebody went, oh, get a seg, I haven't got to issues, they could have joined us actually. So you can build up quite a net of any number of people who could join in just by calling in when there's a gap and waiting till they're acknowledged. But then it does get a little bit more complicated in the etiquette of passing it around the sessions. But that's all part of the fun. So there we are. That's our first simplex QSO. And of course, your next stage after that would probably be to try a QSO through a repeater, where the principles are going to be basically the same, except one thing to remember is you don't call CQ through a repeater. You just put your call sign and then you listen and see if anybody calls you. But after that, I think the procedure for the QSO is going to be the same, except you haven't got to check other frequencies because you're going to have your QSO entirely on the repeater channel. Dominic, we're going to demonstrate now the ability to make a QSO or a contact using a mode other than telephony. So that could be a data mode, or it could be Morse code, which we'll get to later. But let's start with the data. What are we going to use to make this demonstration contact?
Okay, we're going to be using radio teletype, or RTTY, it's also known as. It's one of the earliest digital modes. It dates from well before the 1940s. It was used during the war. And kind of like Morse code, where you've got dots and dashes which represent the letters, with radio teletype you've got two different audio tones which represent the letters.
But we don't have to remember how to do that. It's machine generated. And what are you using equipment-wise to do this?
Okay, so we're going to be using a computer. Back in the day they might have used a radio teletype machine, a bit like a typewriter, but from our perspective these days, just type on the keyboard, keyboard's connected to the computer, that's going to do all the work to convert in audio tones coming out onto the radio's microphone socket, and then it gets transmitted like any other signal.
So as we're connected into the microphone socket of the radio, I guess one of the first things we've got to do, as we do if we're using a microphone to the radio for the first time, is to set up the audio level.
So I should say first of all that there are some radios which will have a dedicated socket for data modes. If you've got one, they'll probably use it. In our case we're on the microphone socket, so yes, we're going to need to set the ALC set gain to make sure we're doing the right thing. So if I just set the radio to transmit a continuous tone, I've listened to the frequency, made sure it's clear. So I'm going to set it to a tone, and then we need to move the mic knob until we've got the right level. At the moment I'm transmitting too little, it's not even moving the meter at all. If I bring it up, I can make it massively overshoot, which means it's going to be transmitting too much, it's going to be distorting. So bring it back a bit into the middle of this thick blue bar for the ALC. That'll be good for the transmitting, and then I can stop the transmitter again.
You mentioned that you checked that the frequency was clear, and of course, with different modes, there is a band plan. So the idea is that we don't just pop up wherever we like using whatever mode we like.
No, absolutely. And in fact, on some modes, there are discrete frequencies, so you have to be on exactly the right frequency for that mode. So yeah, check the band plan first.
And so for 40 meters, which is where we are, 7 megs, the frequency we're using is
7.060, which is kind of the right place for radio teletype.
So how do we initiate our contact then?
Well, so all we do is, just like we might do with any other contact, we're going to call CQ. Someone's hopefully going to come back to us. We'll exchange name, signal report, location, just like any other contact, except we're going to be typing it.
What is the software that we're using then, Dom?
So this is some software called FLDG. It's free, and it runs on most operating systems, and it's really good for data modes.
It does RTTY, which is what we're going to use it for now, but it does do a bunch of other data modes.
Absolutely, there's a whole long list of modes that it supports. Some of them very popular, some of them not so much used, but yes, it supports most things.
Pretty good then, considering that it's a free piece of software. Just talk us through the screen, because there's different bits up there. How are we using, or what are we using on that screen?
Okay, so the main bits are the yellow bit at the top, which is showing us what signal that we've received, everything that it's decoded. The blue bit at the bottom is where I'll be typing my message, what it's going to send.
And the black bit, that big black bit at the bottom?
So the big black bit at the bottom is called the waterfall. Nothing's happening there at the moment because there's no signals around, but when the other person starts transmitting, you should see their audio tones. Hopefully they will line up with the red bars because that's where it's listening.
Ah, because it's two tones, so that's why we can see those two lines.
Exactly.
Okay, let's give it a go. CQ and see if somebody comes back to us.
Okay.
And notice you put a K, that means
over.
What? Ah, right, so that means I've finished typing, your turn now.
Exactly, so M0VFC is coming back. He's now put KN on the end, which means only the person I'm talking to only, rather than being a general invitation, so I can now type back to him, go into transmit mode.
There's a possibility, I suppose, when we're using this communication with RTTY, that part of your message might be lost if there's interference. So notice you typed Bletchley twice. Is that the reason? Just because that's an important bit of information.
Exactly. You'll notice I put the signal report twice, the call signs twice, my name twice, Bletchley twice. Means if there's a little bit of fading on the band, you're still going to hopefully get the message.
And he's finished SK.
Yes. So this is another abbreviation. It derives from Morse code. It means the end of transmission. I've got nothing more to say.
So that explains how we do a straightforward, simple data QSO. Dom, thanks very much.
We're going to take a look now at Morse code. Morse code isn't a requirement for the amateur radio license anymore, but a lot of operators still get a great deal of enjoyment from making contacts using Morse code. You can get some amazing distances with really low power and simple equipment. We send Morse code using a series of short dots or longer dashes. So for example, if I wanted to send the letter A, it's dot dash, or Q. And like that, I can send any letters or numbers that I want to. As well as the straight key here, which sends all the time I hold it down. You might also find people using a Morse paddle. This has two levers. The right-hand side sends dashes, and the left-hand side sends dots. And in the same way, I can use that to send any letters, for example, CQ. Now, I'm here at the National Radio Centre, so I'll send their call sign, Golf Bravo 3, Romeo Sierra. G, B, 3, R, S. And you can use this to have contacts just like you would a voice operator. I'll just call CQ. And there we go. That's a quick introduction to Morse code.
We've created this video to help the thousands of people who've joined amateur radio recently by taking the foundation license, but during the current COVID situation, they've been unable to take the practical assessments. We're really conscious that lots of groups and clubs and individuals have produced training material and have been supporting amateurs as they've joined amateur radio, but we just wanted to add something to that pool of resources. We're going to chop the video into the individual segments so you can go back to just one session, or you can watch the whole video if that helps you. We're really, really pleased to welcome you to amateur radio, and we hope this resource helps.
One of the questions I asked a lot about the VNAs is, are they good enough to measure and adjust an antenna duplexer, like that might be used in a VHF or UHF repeater system? So it's a good question, and my initial gut feeling says probably not, and mainly because of the limitations of dynamic range in these little nano VNAs compared to a professional unit. So let's go take a quick look at a comparison between two different nano VNAs and a professional VNA here measuring this duplexer. For those who might not be familiar, a duplexer is really a set of filters that allows a repeater to simultaneously receive a signal on one frequency and transmit it out on another frequency. And the filters ensure that the receiver doesn't get overloaded by the high-power transmitter. Now, most repeater systems use duplexers that are composed of bandpass, band reject filters, where each path from the antenna to, say, the transmit and receive has a bandpass characteristic to give low loss for the desired frequency in that direction, and a band reject filter to reject the frequency that you don't want to go in that direction. And the frequency assignments are reversed for the other side. I didn't have access to a bandpass, band reject filter set, so this duplexer is just a set of band reject filters, essentially a set of rejection frequency on one side and the other. They don't have quite as good of a rejection of adjacent signals and things like that, but it'll certainly work well for this demonstration. The antenna is here, and we've got essentially our low side and high side, a little over 464 megahertz, a little over 469 megahertz. So what that means is on the low side we'll have a high rejection of 469, and on this side we'll have a high rejection of 464. So we have the VNA hooked up between the antenna and the low side. So if we look at S21, or the insertion loss, or the transmission coefficient, we should see a deep notch right at this, around that 469 megahertz range. Okay, so here's the S11, S22 curves for the low side path. S11 is just the reflection coefficient, and we're seeing about minus 10 or 12 dB around the pass frequency of 464. It's not bad. But the curve we're really interested in is S21, which is the transmission coefficient. And we can see that we've got good transmission for our low path or low frequency. Therefore, if we look down around the 469, we're down around 100 or minus 110 dB of attenuation. So that means that the transmit signal is going to be attenuated by 100 dB or more on the receive port of this duplexer. That's really what you want. I mean, most repeaters will have an attenuation goal of 90 dB or better. So it's 100, 110, times 20. I think we're just looking right down into the noise floor of this particular VNA. But you can see why you really need a large dynamic range to measure something 100 dB down or more in order to see this rejection. So let's take a look at what we see when we look at this on the nano VNAs. One of the things I should have mentioned at the outset is that for each of the measurements I've shown you and the ones I'm going to show you, I've already taken the time to carefully calibrate each of the VNAs over this 460 to 475 megahertz frequency range. Okay, so here's the nano VNA H4 that you've seen in some of my other videos. Over the same 460 to 475 megahertz frequency range, the same 10 dB per division that I'm showing here. On the professional VNA, I set it for 12 divisions because there was enough dynamic range to see down nearly 120 dB, so I had to do that. Here I don't have, I've got only 8 divisions, not 12. So we can see that the input return loss, or input deflection coefficient I should say, is about the same. But I'm really more concerned with the band reject characteristic, because that's the thing we'd be tuning. And we can see that if I adjust the marker to about that same frequency range, we're sitting down about minus 60, minus 60, 63 dB. And we were seeing close to 100 or 110 dB down on the professional VNA. So that means there's another 4 dB or so of rejection that this duplexer is offering that can be seen on the nano VNA, or at least the nano VNA H4. And also you might think that the actual notch is down here because that's a little bit lower. But I'm not sure exactly why that's happening, because we know that from the professional unit that the notch is actually very close to where I've got the marker here. And I think what's happening is we're in noise floor here off a fairly steep edge of the filter. And as we're coming up here, the filter isn't quite as deep, so it's incorrectly showing you that the notch is actually down in this area when it's really here. So I think you could do a basic check of the duplexer with now VNA H4. If you want to measure and adjust to get a rejection that's more than 60 dB down, you part of it with this unit. Some of you sharp-eyed viewers might say, display looks a little bit different from the other Nano VNA H4 videos that I've done. Now, I'm not confirmer on here. This one is some enhancements, including some enhanced dynamic range. This is even better than I was getting before I updated the firmware. This one is by a developer called Bislord and offers actually 401 points in suite instead of 101 that we've talked about in previous videos, and also offers me the ability to adjust the measurement bandwidth. So instead of being several kilohertz, that's by default with the Nano VNA H4, I'm using a measurement bandwidth here of 1. Looked that I was using a 5 kilohertz measurement bandwidth on the professional unit. So in theory, if everything was equal, this would actually show me better results. But I think, again, just the lower noise floor, lower dynamic range of this unit just means that, again, it's going to have limited use for really adjusting and validating the settings on a duplexer. Now, a few weeks ago, I decided to pull the trigger on this unit. You may have heard me talk about the SAA2, which is another Nano VNA, but with a little bit different hardware design and designed to go up to 3 gigahertz. This is a variant of that has about a 4-inch screen and end connectors and a nice metal case. So I saw it became available and figured, again, it's pretty inexpensive, so let's go take a look at how this one performs. Now, as with the 2 previous VNAs, I've also carefully calibrated this over the same 460 to 475 megahertz frequency range. And you can see that if we look at the return loss here, it's actually hitting the bottom of the screen. So I'm going to change the scale for this display to give me, let's say, 12 dB per vision instead of 10. So I'm kind of see how far down the S21 curve goes. If we move the marker down there, we can see that this guy is getting down around minus 70, minus 75, minus 80 dB. So a lot better than the Nano VNA H4, at least 10 dB better, maybe even a little bit more than that. So I think we're getting closer with the SA2, in this case the SAA2N. But again, I think it would be good to use this VNA to do a check on a duplexer just to be sure things aren't grossly off. But in terms of fine-tuning that notch, I still don't think these Nano VNAs are going to have enough dynamic range to really let you optimize the maximum amount of loss in each of those paths. Now, overall, I say that the is a really nice improvement in performance over the original Nano VNA H and H4. I like the metal case. I like the end connectors available in this version, but neither of them are really going to have the necessary dynamic range of, say, a professional VNA like this TEC TR500 series in order to do a proper job on calibrating or measuring and adjusting high rejection duplexers. But that being said, I think the VNAs are a tremendous value for the average electronic hobbyist that dabbles in RF, amateur radio operators and things like that, for doing things like we typically do, designing filters, maybe looking at insertion loss of various devices, as a really nice antenna analyzer for analyzing the input impedance of antennas and having matching networks and things like that. These Nano VNAs are really incredible value for well under $100, which is orders of magnitude less expensive than a professional unit. So other than this one particular job, I'm still a big fan of Nano VNAs. I just don't think they're up to the job for looking at duplexers. So I hope you enjoyed the video, learned a little something. If you liked it, please give me a thumbs up. If you haven't subscribed to the channel already, please do so. And thanks again, as always, for watching. Take care. In today's video, we'll take a look at how to measure some crystal parameters. Look at a couple of different methods, including using the NanoVNA and a couple of other tools. A crystal can be modeled with this fairly simple circuit. The motional resistance, motional inductance, and motional capacitance really determine the series resonant point of the crystal and the Q of that crystal. And then those components along with the holder capacitance really determine the parallel resonant point of the crystal. At the series resonant frequency, the crystal exhibits its lowest impedance from one end to the other. At the parallel resonant frequency point, the terminal impedance of the crystal is very high. And generally each of these parameters, particularly the motional inductance capacitance and holder capacitance, are needed when you're going to design filters, oscillators, and circuits like that. So in this video we're going to take a look at how to measure parameters. My reference for making this video is the paper called Crystal Motion Parameters, a Comparison of Measurement Procedures, that was written by Jack Smith, KAZOA. In this paper, Mr. Smith uses a reference that's very precisely characterized for all of its motional properties, and compares more than different techniques to see how close each of them comes to the actual value of that crystal. Now, of course, I don't have access to a precisely characterized reference crystal or a lot of the specialized equipment that Mr. Smith used for this paper. So what we're going to do is just take a look at 5 or 6 different measurement techniques using NanoVNA and a couple of other tools, and just compare those results to each other based on just a crystal that I pulled out of the box. So the equipment we'll use in this video are my NanoVNA H4 with Dislord version 1.0.39 firmware, which gives me 401 measurement points, which is hopefully get a more precise measurement at the series and parallel resonant frequency points. I'm also going to measure the holder capacitance 2 ways, one using my almost all digital electronics LC meter, and I'm going to back up that measurement using my E5 meter. One of the measurement techniques actually needs a frequency counter, and that's called the G3UUR test method. So I've got a custom built G3UUR test circuit, and we use that with the Tektronix frequency counter and the 12-volt power supply. And then for all the VNA measurements, I got a homemade through test fixture, which will allow me to put the crystal in series with port 1 and port 2 of the VNA. We'll take a look at a couple of ways of measuring the holder capacitance. We'll also measure the motional resistance using the NanoVNA. And then we'll take a look at 4 different methods for measuring the motional inductance capacitance: the G3UUR method, shift method, the -3dB method, and the series parallel method. The first one we use counter, the latter 3 we'll use the NanoVNA. A couple of tips when using the NanoVNA when measuring crystals. You'll probably run some initial through scans, S21 scans, to determine the series and parallel resonant frequency points, and then calibrate a span that covers the series and parallel resonant frequencies, and store that one, so we're going to use that later. That's an hour span that just covers the series frequency resonant point, maybe just a 5 or 10 kilohertz surrounding that series resonant point to get very good frequency resolution. We'll need that for some of the later calculations as well. So you have those 2 stored calibration points. And if you have the choice, use the highest number of sweep points available to give the best resolution and frequency to measure these particular resonant points. So first we'll measure the holder capacitance, C0. Now it's called holder capacitance because way back in the day, before you buy crystals that are nicely packaged like these, guys oftentimes cut and file and grind their own crystals and mount them in a holder like this. If we took these screws off, you'd find a couple of metal plates and a little spring, and eventually put your crystal or your quartz wafer between, and then close it down in here and use this in your radio circuits and things like that. And this was simply called a crystal holder. So even though we don't use crystals in holders like this and grind our own crystals anymore, the capacitance of the housing is still called the holder capacitance. We'll measure that holder capacitance typically using a test frequency that's well below the crystal frequency, and that's so that the motional properties of the crystal don't really interfere with just measuring essentially the capacitance of this mechanical holder. So to start off with my LC meter from ADE, we'll turn it on, let it do its quick little calibration. So you want to measure capacitance. Now I've got a fixture in here that makes it easier for me to plug in my crystal, so I'm just going to zero out the capacitance of my little fixture here. We stick the crystal in there, and we're looking at 3.69 to 3.7 picofarads. Looks like it's spending more time on 3.69, so that's what we'll call it. Now with the DE5000, we'll turn it on. Now the highest measurement frequency we can use with this meter is 100 kilohertz, so let's set that since we're measuring a fairly low capacitance here. We'll stick this in the test socket here, and we'll see we're measuring about 3.75 picofarads. Now with the NanoVNA, I calibrated a frequency region that's about 4 megahertz wide around where the resonant frequency is this crystal, so I can make a capacitance measurement about 2 megahertz below that. If we look carefully, I can see I got about 160, 170, 180 femtofarads of capacitance on the S11. So when we add the crystal to this, we should see that jump up, and so we're measuring, let's see, about 3.98 picofarads of holder capacitance. So we'll take that 3.98 minus, we'll call it 180 femtofarads. So that gives me just about 3.8 picofarads measured with a NanoVNA. Now the nice thing is that all these results are really pretty close. If we average together, we wind up with 3.747 picofarads for the holder capacitance C0. And for the remainder of any of the VNA-based crystal measurements, I'm just using this little universal series fixture that I built. A couple of SMA connectors with an open between them. Got a couple of pin sockets connected to the center pins of the SMA connectors. One end goes to channel 0 or port 1, the other end going down through this coax to channel 1 or port 2. And we'll be looking primarily on our S21 measurements. Now, in the paper by Mr. Smith, he also describes making a low impedance fixture where you've got a couple of resistive attenuators at either end, so that the crystal, instead of seeing 50 ohms, sees 12.5 ohms. And that should give you better results for measuring sort of low impedance values like the promotional resistance. But I built it, I did some experiments with it, and I found that particularly when trying to measure the parallel resonant frequency, the nano VNA didn't have enough dynamic range because of the attenuation through that fixture. So I found I got pretty decent results with this simple 50 ohm through fixture, so that's what we're going to use. I ran a couple of wideband scans on this 18.73 megahertz crystal to determine, kind of where the series and parallel resonant frequencies were, and then set up, in this case, about 100 kilohertz wide to kind of spread them out a little bit, get a more precise measurement at those 2 points. So what we're looking at here on S21, the blue trace here, is the insertion or transmission coefficient, which is very close to 0 at the series resonant point, indicating that the crystal has very low impedance, and it's very, very high impedance, meaning blocking almost all that signal coming through at the parallel resonant frequency point. The purple trace is the phase of S21, which we can see is plus 90 degrees at low frequencies, crosses through 0 degrees right at our series resonant point, then goes down to minus 90 degrees, and then we rocket back up again right at the parallel resonant frequency point. We're also showing the reflection properties, or S11. Log magnitude is the yellow trace. That's, I would see we've got about 0 dB, which means I'm reflecting most of the energy back off of that crystal because it has a high impedance, and that's a resonant point that's allowing that signal to pass through, and then come back up again. And also looking at complex impedance with the Smith chart here. And to measure the resistance, or the motional resistance, we're essentially going to measure S21 over a narrow span right around the series resonant frequency. We'll call it FS, sometimes we'll see it called FR. And we do that over a much narrower span, typically 10 kilohertz. So for this series through method, we're just going to measure through the crystal again, record the S21 at the 0 degree phase point, which should correspond pretty closely, if not exactly, to the minimum S21 value, but also record the series resonant frequency at that same 0 degree phase point. Now that I can see both the series and parallel resonant frequency points, I have another setup here that is just looking at centered around the series resonant point. It's about a 10 kilohertz span. And we can carefully move the marker back and forth to look for the minimum S2. I'm seeing about minus 0.6 dB, and it looks like if I get close to that 0 degree point here, we're at about 18.723225 megahertz. Now, this is a calculation to go from the S21 value to our emotional resistance. We essentially take the S21 value and negate it, so we're essentially going to remove the negative sign. So we'll have 0.6 divided by 20, subtract 1 from that, and then multiply 2 times the load resistance seen on either side of the crystal. So the crystal sees 50 ohms in our 50 ohm fixture, so we're going to essentially multiply by 100. And if you run through that calculation, we compute the emotional resistance to be 7.152 ohms. You could also run a shunt through measurement, where you actually have the crystal in shunt instead of measuring straight through with the crystal shunting to ground, and still measure S21. And then the calculation is this one here. This calculation is a little more involved, so I didn't bother going through it here, but I found that the series through measurement seems to work pretty well. So that takes care of measuring the modal resistance of the crystal. And now let's focus on our couple of different methods that we have for looking at the motional capacitance and motional inductance. Now, this first method for measuring the motional capacitance and inductance is called the G3UUR method, and it uses a simple crystal Colpitts oscillator and measures the frequency coming out of this oscillator under 2 conditions, with the crystal grounded and with the crystal going through a small value capacitor. And this small value capacitor is typically anywhere between 30 and 60 picofarads. It shows a 47 picofarad capacitor that I carefully measured before putting it in the circuit. So here's a little test oscillator circuit that I built. In fact, I've got a video on this I'll link down below. And so I've got the crystal in a position where I'm connecting it up directly to ground. And we go take a look at the frequency counter. All right, we can see that it's measuring about 18.72384 megahertz. So now move the crystal so that it inserts the 47 picofarad capacitor. Well, we're measuring 18.72661 megahertz. So we take our 2 measured frequencies. The difference between those is 2.7 kilohertz. We push our capacitance using 47 picofarads and a 3.747 picofarad C0 that we earlier, and that delta F, and we wind up with a motional capacitance of 15.02 femtofarads. And then enter that into this equation here, 2 pi times this frequency squared multiplied by the emotional capacitance, and we get a emotional inductance of 4.81 millihenries. The next 3 methods use the nano VNA, and the first one is called the phase shift method. And here we're going to again set up a span of 5 to 10 kilohertz around the series resonant frequency. And particularly want to look at S21 log magnitude and S21 phase. So what we're going to measure is essentially our S21. Okay, find our series resonant frequency essentially at the 0 degree point. And then we're going to move the marker back until we see a plus 45 degree phase shift and measure that frequency. We'll call it FL. And we'll move the marker the other way and measure our minus 45 degree phase shift point. We'll call it FH. And then we'll also, again, we'll grab S21 at the send frequency point, and we can use that to compute the emotional resistance. We've already done that, so we'll just carry that measurement over from our previous results. Okay, using that same setup that is zoomed in around the series resonant point, First thing we want to do is take a look at the 0 degree point, which is right about here, sitting at about 0.2 degrees. I think it's as close as I can get. So we measure our series resonant frequency at 18.723200. So next we'll move the markers until we're essentially at plus 45 degrees. 44.7, 45.1, so that's pretty close. So we're at 45.1 degrees, and we can see the frequency is 18.721475. Okay, then we can go back and measure at the minus 45 degree point. Let's see, 42, 3, 4, 44.7, minus 45.1. We can see our frequency is 18.724900. We've just carried over our calculation for the motional resistance that we've done earlier. We calculate R effective, which is just the motional resistance plus 2 times RL, which in this case is 2 times 50, so that's 107.152. We change the delta frequency between FH and FL. In this case is 3.425 kilohertz. We can compute then the motional capacitance, 14.51 femtofarads, and then the motional inductance of 4.98 millihenries. So the 3 dB method is actually pretty similar to the phase shift method. We'll look at the same 5 to 10 kilohertz span around the series resonant frequency. We'll get S21 log magnitude, and also look at phase, but really we're only interested really in this case of the log magnitude. So what we're going to look at is the point where the S21 is 3 dB down from our peak value. So not absolute 3 dB down, but 3 dB down from whatever S21 we measure at this location here. So the first thing we want to do is measure S21 at its highest point, and we already figured out that's about minus 0.6. So we want to measure down to minus 3.6, essentially on either side, and record those two frequencies. And then from that we can compute the results. Okay, again, our resonant point where S21 is at minus 0.6. So we want to look at what frequencies give us minus 3.06 on either side. So see how close we can get. Looks like that's close to minus 3.62. So that low frequency is 18.72135. And then we can go measure on the other side and look for minus 3.6 on the other side here. And let's see, minus 3.62, that's pretty close. And our frequency here is 18.724825. Using the series resonant frequency from the previous measurement and the 3 dB down frequencies on either side, we can compute the delta frequency, the Q, and then the motional inductance of 4.91 millihenries, and the motional capacitance of 14.72 femtofarads. Our final measurement using the VNA is to look at the series parallel method. And here we're going to set up a little bit wider span to show both the series and parallel resonance, both the peak and the dip in the S21. And that'll be typically a 50 to 150 kilohertz span. And we'll look at essentially S21 primarily, but we'll also keep the phase plot there as well. And we'll measure the series and parallel resonant frequency points. And if you don't have a whole lot of points, if you've got only 101 points in your VNA, you might want to span tighter around each of those to get better resolution. And then once we have those measurements, then we can simply compute the motional capacitance and inductance with these two equations here. So using the 100 kilohertz span here, so I can see the series and parallel resonant points. Then we'll move the marker to the peak of the series resonant point here, and that should be right about there. In this case, we're seeing 18.723250. Yeah, it's a little bit different than when we measured when we zoomed in because they don't have resolution, but the difference is down in the tens of hertz here, so I'm not too worried about it. And then we'll scroll down with markers and look at the, let's see, right down here around the parallel resonant frequency point. It looks like that's probably about as close as we're going to get right in here. And so 18.761500. We'll run through the conditions and we wind up with a motional capacitance of 15.31 picofarads and motional inductance of 4.72 millihenries. In this equation, C stray is the stray capacitance of the fixture. Where you measured C0. In our case, we zeroed that out, so essentially didn't need that parameter, but that's the equation you find in the paper. Okay, so here's a summary of what we found. We measured the motional resistance of 7.152, 3 different measures of the holder capacitance, and they're all really darn close, so any one of those will work on. Now, of course, we don't have any way of knowing which of these is really closest to the actual value. The thing that we can see here is that they're all pretty darn close. They all measured in the neighborhood of 4 to a little over 15 femtofarads. Of motional capacitance, and then ranging from about 4.7 to 4.9 or 4.98 millihenries for the motional. And which of these are the closest? I don't really know. But based on Mr. Smith's paper, I think he found that the G3UUR method was actually one of the more accurate ones, as well as the phase shift measurement. So I'd probably put more stock in this two measurements than the other two. But the idea here was just to ensure that even with these very different methods in some cases, that the results are all pretty similar. Okay, I hope you enjoyed this look at several different methods of characterizing crystals using LC meters and homebrew circuits and the Nano VNA. If you liked the video, give me a thumbs up. If you haven't subscribed to the channel already, please do so. And be sure to check the notes down below the video for a link to the paper as well as my notes here. Thanks again as always for watching, and we'll see you next time. In this video, we'll take a look at how to update the firmware on my Nano VNA 8.4. Specifically, we're going to look at how to do it using Windows 10. Of course, if you have a different version of the Nano VNA or you're not using Windows 10, your process may differ, so be sure to do your research online. So the firmware I'm starting from is the one that came on the unit when I got it. And if we go to the config menu and version, We can see that it's the version from 8555, version 0.5.0 from February 2020. The version I'm going to update to is by one of the developers called Dislord, version 1.0.39. It's got some nice features like a 401-point display and a number of other things. Now the firmware files for the Nano VNA are available in a couple of different formats potentially. A hex format or a bin format. I'm going to use something called the DFU format, and most of the versions that you can find online have got a DFU file, and it makes for a real easy update. So let's get started. So in order to do the DFU update, you're going to need this utility from ST, and I'll put the link to this website in the video notes down below. So you go to the site and scroll down and click Get Software. Now, of course, it would be great if you just downloaded the executable, but what it does is you have to actually register with the site, give them your email address, then they send you an email with a download link for you to download the zip file. So once you register and you get your email with the download link, you'll get this, you can download this zip file right here. Inside the zip file is a couple of text files and this setup executable. The setup executable will install the Defuse demo software, which is what you use to install the DFU file into the Nano VNA. Now keep in mind, getting this Defuse demo software, downloading it, and installing it is something you only have to do once. Once it's installed, you can use it to update firmware on the Nano VNA at any time. The next is where you might find the firmware. So if you go to the Nano VNA users group on groups.io, one place to find sources of firmware is go to the wiki. If you go to the wiki page, you'll see there's a sources of firmware here. And I found that this is some of the older releases and things like that. In fact, the original release that I used, I'm from this area here. So we go back to the files location from the groups page and go to this link here, Dislord's Nano VNA H firmware. This is where I found the version that I am going to upgrade to, Nano VNA v1.0.39. And you can download that file from here. It's a .rar file, just similar to zip. You just need a utility to unzip that. So now you should have the DFU file that you want to upload to the Nano VNA. In this case, this is the original version that I had in it, and this version here, 1.039, is the one that I want to install on my unit. So now here's how you actually go ahead and do it. So now that you've downloaded and installed the Defuse demo software, you just go to the ST Microelectronics folder and start up the Defuse demo. So when you run the Defuse demo software, it looks a lot like this. So what we need to do is just configure the Nano VNA to connect to the software. So to put the Nano VNA into DFU mode to be ready to be updated with firmware, you shut it off, push down on the multifunction rocker, and while holding it down, turn it on. Now it looks like the screen is dark, and it is. It will stay dark, and that's how you know it's in DFU mode. Now with it in DFU mode, connect the USB cable to the computer and the USB cable into the Nano VNA, and then the Nano VNA will show up in software. After connecting the Nano VNA in DFU mode, you'll see this screen kind of populate here with some information, and you can go down and click the Choose button here and navigate to the version of firmware that you want to load. Click it and hit Open. Once it's open, then you can click on the Upgrade button. Once you do that, it's going to give you a little warning. Do you really want to do this? And just say yes. And it will go through and erase the current version that's in the firmware and download the new version, and it will tell you when it's done. Once it's done, if I just hit quit, or sometimes I'll just leave DFU mode and just hit quit while it's in process there. It doesn't really matter. The screen on Nano VNA will just light up with a new version of firmware. While getting the Defuse demo software, the unit basically boots up in the new firmware. And if I unplug the USB port, it just restarts one more time. Okay, so let's check the version to be sure. We go to the config menu and hit version, and I can see 1.0.3 on. Now there's a chance after you update firmware that the touchscreen calibration won't be right anymore, in which case it'll look like behaving kind of erratically when you try to use a touchscreen. If that's the case, don't panic. You can very easily recalibrate touchscreen. If you push down on the multifunction to bring up the menu, and scroll down to config, and then scroll to the touch cal at the top, and then it just asks you to touch the upper left. Just do that with your stylus. Touch the lower right, do that with the stylus, and then just hit save. Now touchscreen's calibrated, and you're good to go. I hope this video has taken some of the mystery out of how to update the firmware in your Nano VNA. And again, specifically this was for the Nano VNA 8.4 and Unit 10. Other methods for updating firmware with other operating systems and other versions of the Nano VNA are going to be similar, but you can find those instructions through the wiki page and the groups.io Nano VNA user group. Thanks again for watching. If you liked the video, give me a thumbs up. If you haven't subscribed to my channel already, please do so. And thanks again, as always, for watching.
W1VLF.
Hey everybody, my name is Paul, W1VLF. Welcome back to the lab. Today we're going to talk about notch filters for the AM broadcast band. If you're like me,
you enjoy listening to the broadcast band. Unfortunately, I have a 610 kilohertz transmitter that is less than a mile away from me, and it produces an incredible signal. Plus, excuse me, 70 over S9, and that's just tears up all the receivers. So I could build a high-pass filter, which you've seen me do in the past. I did a video on that, and that works really well. But that negates the rest of the AM broadcast band, and I still enjoy listening to it. I could pad it down by 30 dB or so, get it into the range of the receivers, but then, unfortunately, then all the rest of the signals are padded down. So what we're going to talk today about is a notch filter. And it really is just a very simple device. It's just a parallel resonant circuit that you put in the coax line. I don't know if you can see this very well, but I'll have some much better pictures for you to look at in a minute. This is an old loop stick. Remember the AM loop sticks you used to hear about? And a couple of silver microcapacitors. Just a parallel resonant circuit in on one VNC, through parallel resonant circuit, and out on the other. This is something I just threw together. It works pretty well, but it's not really designed with high performance in mind. It has a pretty deep notch, but it also has some pretty wide shoulders, so most of your adjacent channels are kind of gone, or down quite a bit. And I'll show you that too on the network analyzer over there afterwards. This is exactly the same thing, BNC in and out. This is my little test board, and these two clips here just hold devices that I want to test and put in series with network analyzer. So here you have coil, and then capacitors in parallel, and that's it. I'll see if I can pop this off. Yeah, and again, you'll have pictures of these, but this is just, what's it look like? 3/4 of an inch long of number 61 ferrite rod. If everybody's got to have an old AM receiver antenna around somewhere in your box of junk, and that's what this is. And I just cut it off and sanded the end down, and I glued it. I glued it to a stainless steel bolt. I glued it up to the ferrite, and then just screwed this in. And then I threaded this PVC so that it would act as an adjustment. So essentially, I made my own loop stick, because although I have hundreds of loop sticks, I don't have one that I know has number 61 ferrite rod, and that I also know it has the right amount of turn, give me the right inductance. So I'll give you some close-up shots of this. Let me see what else. So this is not going to be a do this exactly, and here's how you build it. It's going to give you an idea of what you need. A couple of pieces of PVC pipe, some silver microcapacitors. And by the way, why do you use silver microcapacitors? The Q on these capacitors is astronomical, and it really kind of helps with getting the shoulders of this notch circuit to be very sharp, or much sharper than if you used any other kind. This one, kind of design thing here. This one has a lot of inductance in the inductor and not much capacitance. So here I used 2.8 2800 picofarads of capacitance, and only like 20 microhenries, which means that in order for it to be resonant, that's a different ratio. Normally an antenna rod made for the broadcast band maybe has 250 microhenries. This only has 24. So most of it is coming from the capacitors, which are the higher Q element. And that's what counts for the much better performance. You could put, like I said, you could do a high-pass filter, but and that works really well. But unfortunately, you end up with not being able to see any of the broadcast band, and that I didn't want to have happen. So I'm going to show you the concepts behind how this works, how I arrived at these components, and a calculator that you can online calculate your own frequency. By the way, this little coil here is 10 microhenries or so, maybe 12 microhenries without the core in place, and 24 with it. And this stainless steel bolt. And again, remember, it has to be stainless. If you put regular iron or steel in there, it's going to mess things up. The Q, anything magnetic. So I guess let's see what else. Anything else? I guess that's it. I'll zoom in and kind of show you this a little bit better here in person, and then we'll go over look at the graphs. And then we're going to go over to the SDR. Today we're going to be using console 3, and we're going to be using a the RSPDX with its built-in notch filter works really well. Not notch filter. It's built-in broadcast band notch filter. It works really well. Unfortunately, all broadcast band is on. So if you have one big offender like I do, like right out that window, which you can't see. This will get us in the neighborhood of 30 dB of attenuation. So they're running a kilowatt. They have maybe some gain, but anyway, 10 dB down would be 100 watts. 20 dB down would be 1 watt. And so this makes it look like it's running about a 100 milliwatt transmitter. And you won't believe how effective it is. All right, I won't ramble anymore. I'm just going to zoom in and show you these pieces sort of in real time. I'll call them out, and then we'll go over and look at some of the graphs, and then we'll go over to the RSPDX and see the real world how this really works. All right, let me set up. Okay, I'm back, as I like to say. Okay, so here is one of the little Pomona boxes. I already had BNC on it. I threw it in there, made it resonate, and just because that's what I got. Oh, there's a loop stick. I'll try that one and the right capacitor. And to adjust this one, it's a standard loop stick, so you just turn the screw here, and it works okay. You know, if you were only interested in say my frequency I need to delete is on 610, and the ones if you're only interested in 1,000 and above, you know, 1 megahertz above, this would work. This would be fantastic. But this is really a much better way to go. Here I have three 961% microcapacitors. If I pick this stuff up at flea markets, and you never know when you're going to need it. So I'll pop this off. Here's a coil. So this is all not glued together. It takes a little retuning every time you take the cover on and off because you're dipping the coil, the ferrite into the coil more or less. So you just have to be a little bit careful about that until it's done. And once you seal everything and get it all nice and compact, then you just make the adjustment and lock it down with this this lock nut here. So that comes out. Here's just the inductor, and the inductor is 35 turns of this Litz wire. But what's really important is not so much the real size of this coil, but that you end up with about 10 microhenries, 10 to 12. I'll give you the exact values later. And this is just another one of those end caps that's glued down to the board so they could test it for you here. So you just plug that in, this B and C here, this one is the in, this one's the out, really doesn't matter, it's symmetrical, but so you can see coming in, you have a parallel tuned circuit, that's it. So let's look at some of the stuff on a computer, show you some of the graphs and some closer up pictures and whatnot, and then we'll go from there. Look at this. I gotta figure out a way how to show this stuff without having this in the way. Oh well, you can laugh. Okay, so this first slide shows the two notch filters being compared. The black trace number 1 with a marker at the top of the screen that says 610 kilohertz and something like, I can't really read that, it's too small, in the 50 dB downrange. But you can look and see that it does not come out of its notch for, you know, up to a couple of megahertz. This sweeps out to 20 megahertz. So you could get an idea, once the notch goes away, it's still a flat pass band all the way up. So you're not going to see any attenuation anywhere else. Also, the red is about 31 dB down, and you'll see that the 30 dB is plenty. The benefit of this one is look how narrow the notch is, and look at the 6 or 8 or 10 dB, 12 dB of adjacent channel that you're not losing due to the low Q of the other system. So again, this goes out to 20 megahertz from 10 kilohertz to 20 megahertz. This is the sweet spot. The next slide that you see will be close up, so you can get a really good look at what happens to the to these notches up here when you design one properly. All right, so now what we're looking at is a sort of a close-up expanded view, 10 kilohertz up to 2 megahertz, so just above the broadcast band. If you look at the black trace, which is the old prototype, you can see that there is places where it's 10, 15, and almost 20 dB down in the adjacent channels, and look how nice and sharp and narrow, and how fast it returns to being a flat response. You'll see this when you know how effective this is when we go to tune it. I just wanted to show you that close-up view, and now I'll go to the last slide is going to be one that is just for, it goes out 30 megahertz because I thought, geez, I made the first slide at only 20, maybe people are interested all the way up to 10 meters with the single antenna. So that's what we're going to do on that one. Okay, not a whole bunch more to see here. Basically, just wanted to show you that the band pass or the through pass of this filter out to at least 30 megahertz is essentially nothing. So I won't dwell on this, but you can see 2 notches are here, and out 30 megahertz, it's very flat. Real quick, just to show you that the coil itself, without the freight core inserted, is 12.4 microhenries. I'm going to show each one of the components here. The plot shows the value of the inductor when it was tuned to 610 kilohertz. So right at 24 microhenries, you can see, and that's variable all the way from 12 to probably 4 microhenries, but all it really is a 24.2. Okay, well, looks like I blew it. I threw away or deleted the sheriff of the capacitance meter, so, but it's 2828 pico and 20 picofarads. So instead, I'll just leave a few seconds of each one of these close-up shots up here, and then we're going to move on to. All right, so let's look at the resonant frequency calculator that we use to determine the types of values that we need. So we're going to take the resonant. Oh, it's already in there, so let's grab that. I'm not sure the mouse is going to show up exactly. I have 2 screens here, and the mouse, it doesn't seem to be showing up in exactly the right area. So, but I'll have to figure that out later. Just follow along. Resonant frequency calculator, the second one down, works really well. And if you look at what we have here, here's the circuit I was telling you about, just a coil and a capacitor in parallel. Very, very, very basic. So let's add in the values that we saw on the here. So we were around 24.2 microhenries, so that's okay. And here we were at 2820 picofarads. That's micro, so we're going to go down to pico. And then we're going to hit calculate. And this number here, the number down below in red, should come up at around 610. And it did. Okay, so and it shows the values down here in the circuit diagram, 24.2 and 2820. That resonates at 610. So the coil you're going to wind is really around 12 microhenries, but by introducing the core, the piece of 61 ferrite on that threaded screw, you're able to lower or increase the inductance from 12 up to 24 microhenries. So there's an alternative way to do this. I don't know, let's say you had a, 3,000 picofarad capacitor. So we'll just type in 3,000. Okay, and we'll leave we'll say 30 microhenries, just to show you that you can use this calculator in the other direction. So whatever 30,000 PF and 30 microhenries equals is going to show up down below here. So if you hit calculate, it's going to come out to resonate at 530. The highest Q element in this circuit is the capacitors, the silver mica. So you want to make sure that you don't go, because you could go in the other direction. You could say, oh, I have 300 picofarads, and let's see, and I want to be on 610 kilohertz. And do calculate, and now it's going to tell you you need 220 microhenries, which is like typical of an M0ODZ ferrite core antenna you find on the back of an old stereo or something. Unfortunately, coil is the lowest Q in the circuit, and Q equates to shoulders, as you'll see. So we want to minimize that. So if we want to tune to, let's see, where are we? 610. We're going to go with 24 microhenries again, and 2800 or so. Get rid of that 610 in there and ask it to recalculate. And yeah, 613. I didn't put the exact values in, but anyway, so that's how that works. It's a great calculator. Let's see the page here. Wonderful for doing this kind of work. But if you're designing something, go heavy on the silver mica capacitor here and light on the inductance. All right, on to the next part of the video. Okay, guys, W1VLF back. And we're at the Ham Shack computer now. Excuse me, and we're going to the 610 kilohertz signal that I talked to you about up here. Got it muted because it sounds horrible, but if you look over here, you're going to see that there's a S9 plus 71. Now, granted, I'm running a big dipole. It's a 160 meter dipole, and I played around. Let me go back to home with RF gain and IF gain here, AGC on and off. I can't seem to come up with a combination that will allow me to hear adjacent stations. So let's just take a look at this. I'm going to turn the filter on, the notch filter. This is the RSP DX, and this is a ton better than the previous filter. So let's just see what it does. You can see I'm tuned to the 610, which is 70 over. Again, it's a kilowatt, like right outside my door, just about. So here we go. We're going to turn that on, and it drops it from 70 to 20, so about 40 dB. And most of, let's see here, crank this up a little bit. And we'll narrow it up. Most of the AM broadcast band, or actually all of the AM broadcast band, is gone. Okay, there's going to be a few tiny little carriers in here, blah, blah, blah. I'm not sure exactly what these are, but 610 is still 30 over S9. Now, again, I can change the RF gain, but I've got it set to default, and I have this set to with the AGC on. It's much better with the AGC on if I turn it on. All right, so there it's on, and again, I'm going to shut the filter off so we can filter now on. I'm going to turn it off. Okay, you can see the 610 is back up to 70 over, and there's all sorts of products being generated here. But let's go up into the in memory section here, go to number 2, and we're going to go in the middle of 75 meters. And we'll squeeze it up a little bit so we can see a little bit more of 75 meters. Let's see, someone here talking. Let's see here. It looks like there's something right here. I'm going to put in the filter, so we can go back to home, and here we go. Alright, so let's tune somebody. Tune somebody to show you.
This works great. So I'll get a clip of you on
Alright, I'm going to turn the off. And it's essentially just blown away because that signal is so big. Maybe with much smaller antenna system, you would be able to run this, but with that notch filter out, turn it back on again. Brings 75 meters up. Okay, so very, very impressed with how well that filter works. So let's go back to memories. First memory bank, we're going to go to 610. And we're going to squeeze it up. We're up at plus 71. Now, before when you saw me take the ferrite rod out of pulling that little cap off the top, that's how I'm going to sort of disable it. So I'm not going to detune it every single time, but I'm pulling that ferrite bar out, that little cap I had. So I'm going to drop it back in there and adjust it for minimum. Okay, so we went from 71 to 38, so what's that, about 33 dB of attenuation. We'll go up to 60. This is New York City, 190 miles away. Okay, so 10, go up to, I think 7.1 here, 680, 710. Okay, we'll pull that core out, so essentially the filter is coming out of the circuit. Okay, it's just not able to cope with that. Core back in, and of course I got to readjust again. If you look over here, you can see me readjusting it. Okay. I hope I can yell by please. By YouTube, please. This is 90 miles away. This one's 90 miles away. 640 is another. It's a little too close. Let's go up to 1710. There's a station up there, or 1700. And I'm gonna pull that out again. Here we go. So it makes the whole band unusable, or makes it usable, depending on how you want to look at it. So let's go back to the home plate here, and we'll turn on the notch, which again. Oops. Oh, that's because I have the filter in. Let me take my filter out. Okay. And now I'm going to put in that one. We're up at the very edge of the bait, so the filter's starting to roll away a little bit. Let's squeeze this up a little bit. You can see down below here, the filter's starting to come back out again. You know, it's starting back into where 75 meters. I mean, where 160 is. Let me just drop my, let's take that out. And we'll just drop in that one. So basically, with this filter, with this notch in place, you can go anywhere you want in the broadcast band, plus or minus, a bunch of kilohertz from that big 610. So let's go up to 75 meters with this notches off. Let's go up to 75 memories. That's number 2. I think somewhere around here. Let's see if everybody's talking here. No, here's something right here. This is the 9 notch over. Back to, so I'm going to pull my notch out. Now this is only notching at one station, right? This is one big fender in my life. And you can see all the harmonic and all the distortion products, every 10 kilohertz. 320, 330, 340, 350. And I'll drop that back in again.
Yep. Somebody come in. And,
so it really is quite a useful way to be able to still use all the others. If you have one big station that's giving you a lot of problems, that's the way you want to go is with a non-filter. So let's go back down to the A broadcast again, 610.
They are told what comes to coronavirus.
Yeah, see, now I didn't have it tuned completely either. There we go.
But it gets worse.
I'm turning the screw right now.
Are even worse than Fauci. They want to shut the nation down. 100%.
Look at that. Here, watch.
And have the government
9 miles away, right next to a 1 kilowatt, 50 kilowatts away. Unbelievable. So anyway, any questions or anything? By the way, I'm up to 902 subscribers. I'm really trying to get to 1,000. So if you know anybody who's interested in this kind of stuff, please share it with them. I don't want to hear that. If you know anybody who's interested in this sort of stuff, please share it with them, or perhaps my high pass filter video. I'm finally getting into a position now where I can make some more, so that's what I'll be doing. Again, please subscribe, and also I have Instagram, W1VLF, which I'm experimenting with, just sort of showing things that show up that are much easier to put up there than to do a whole video. Thanks again. Press the subscribe button and the notification bell. This is W1VLF signing off from the W1VLF Ham Radio Shack computer 73. Hey everybody, my name is Paul, and a couple little disclaimers here before we actually get the video going. This is not going to be about electronics, not about loops, antennas, SDRs, or anything related to electronics. And also maybe a few choice words sprinkled throughout this story. But I just watched the news a few minutes ago, and it's just depressing as hell. I mean, between the COVID virus that's going on, and the state of the election that's going on, and the state of our cities, and isolating, and all this stuff, it's just terrible. I've been out of work, but I've been working from home for 9 months now, just under 9 months. And makes you kind of think back to when I was a kid, which would be in the 60s and 70s, of just how much easier things were, or how much simpler things were. At least we didn't think they were very complicated. Back when you had television channels, For us, it was Channel 3, Channel 8, and Channel 30, the three networks. And maybe on a really good night, you could do something out of New York City and watch creative features. But anyway, I was thinking back to those days, and I thought about a story that this actually happened to my brother and to myself and my brother. We were both, we're about a little over a year apart. I think we're probably 10 and 11. And it kind of makes me laugh when I think about this story. Anyway, we lived on a dead end street, so you could do all sorts of stuff. You could put a rack out, 2-3 racks out in the middle of the road, or bases, and play baseball, kicker, soccer, whatever you wanted to do. It was dead end. There was only about 6 or 7 houses. Anyway, we lived in a house. There was my dad, Leo, worked 2 jobs to keep us in shoes, just in shoes, and bread. And my mom took on the burden of having 4 kids and raising us in a life that came out to be okay. Tough, but fair. Anyway, in our house, in the backyard, we had this gigantic oak tree. I mean, this thing spanned half of the house. The branches hung right over the house. And my old man, I say my old man, and people go, why do you call him your old man? That's disrespectful. And that's not at all disrespectful. He called his father his old man. I call my father my old man. It's a term of endearment. It really is. It does not mean anything detrimental or not respectful in any way. If I say my old man to my brother, they go, oh yeah, I remember when the old man did this, the old man did that. So anyway, the old man, he was old, and he used to have a little bit of a temper, and he'd get mad, from time to time. And so we're all sitting around the kitchen table, having supper. My mother, father, on one end, and the 4 of us, my brother Chris, Corrine, and myself, having supper. And that limb of that oak tree just hung right out of the kitchen. And God damn it, the old man was sick. There was the chipmunks and squirrels were up in the trees, potting off the acorns, and they come buzzing down on the roof. And he get mad as hell because I'm gonna have to put a goddamn roof on his house. And we all, of course, the 4 of us thought it was funny, was funny as hell. But I guess now that I own the roof and I would have to replace it, not so funny anymore. So anyway, that's a little bit of background that this oak tree was over the house. So my brother Tom and I are out in the front yard, actually playing our usual game of getting to some old models. We put models together in those days. Those were the days when you could get a real glue. That I guess it's okay, but anyway, we would smother a couple of the cars with glue, and we were lucky because we had a driveway hill. So we would light models on fire and let them sail down into the road, and they'd go halfway across the street, and then we'd go some model. And nobody thought anything of it. Oh, there's those fancy little boys making models again. Big deal. Oh God, feels good to think about those simpler days. So anyway, one day, we're out there lighting models. Actually, previous to this, we had noticed that those damn chipmunks get up on the roof, would run up the drain pipe. You have to eat, the water come down, and go all the one end, and come down south, and run out the driveway. Well, the chipmunks had figured out that they could run into that pipe and shimmy their way up, and you'd hear them scratching and scratching and scratching and scratching and scratching. Then finally, they come out the top, run up the roof, jump onto one of the branches there that were pretty close to the roof, and knock the nuts off, right? So we're out there lighting our models on fire. I'm pretty sure my parents were home at the time because I don't think they would have thought that was such a great idea. But we're squeezing the glue out on the models and we light them up and give them a push, roll down the driveway, flame shooting up the back. I mean, what else did it have to do? There weren't any cell phones. There weren't any. You only watch TV once in a while. With restrictions on that. Blah blah. So anyway, we're out there rolling these models down the driveway, and I noticed that a chipmunk goes shooting across the driveway and goes right into the dump. And I could hear him up there scratching. It usually took about 30 seconds or so, maybe more, for him to make it to the top. But they usually would, right? So we're looking at each other, Tom and I said, Tom, quick, go get the hose, go get the hose. Well, the hose was pretty close anyway, because we were smart to have it on hand in case something. So he grabs the hose, he pulls it out, and I said, squirt it up on the roof. So he squirted it up on the roof, right over the hole where the water would come down in the drain pipe. And I was, well, this is going to piss off the junk, and he's going to turn around and come down, or he's going to get a shower, and it'll take him a long time to get over. Anyway, the water started coming out of the downspout, right? And I can start scratching away, scratching, don't look at it, scratching like this, going up the pipe. And keep the water going, and Tom's up there, he's got, he's doing his way where the hole is. And meanwhile, I'm thinking, okay, it sounds like he's coming down. So, now, I'm not a big sports fan at all. But my dad used to watch baseball, and I think he was on with sports once in a while. But here was my chance to be a big league catcher. So picture this: the chipmunk is starting to come down, or I think he is. And I'm sitting down there at the bottom like this, waiting for Johnny. I think I'm Johnny Bench, right? Here it comes, and the thing comes flying. I figured I was just going to catch him in my hand. But what I was going to do with him after that, I don't know. But I'm going to catch him in my hand, right? No. What happens is he jumps over my hands and he goes up my shirt sleeve. Actually, it was kind of cold because it was fall and the acorns were falling off. And that damn chipmunk is going up my shirt sleeve like this. Now he's fattened out. Because what I'm doing is I'm going like this. I got my whole like, somebody tell me, you gotta help me, you gotta help me. And slowly he's going up, over to my shoulder, around the back of my neck. I just he's coming out, he gets to the end, he's gonna bite me. So runs into the, I tell you, my dad was in the wholesale fruit business, so there was no lack of bushel baskets around. He runs into the garage, he's looking for some kind of container, he grabs the bushel basket, he comes running out with it. And then one of those aluminum soul coasters, remember those round, like, gigantic contact lens things? He was running out with one of those, and the basket goes, stick your arm in here! So I stick my arm in there, and it comes down like this, and I don't know, I'm really scared, right? I'm really scared because it's scratching away at the same time. It feels claws, his claws, like, running all the way down the arm. Finally, he gets close, and I go, all right, I'm looking away because I'm afraid he's going to jump out and scratch my eyeballs out or something like that. And finally, I let go, and he shoots right out with his basket. And Tom slams the lid on. the soul coaster, like the bottom of it, right? And he's running around trying to get out. Well, after a couple minutes, he got pretty quick. So, I don't know, we're looking at each other going, what happened? What happened? So, curiosity killed cat, right? Well, now that we've been on this gigantic safari and we caught this wild animal, we wanted to take a look at him. I mean, we're going to hurt him or anything, but what the hell are you going to do? We got, a chipmunk going up one arm, across your shoulders, come out the other, and I guess we could have just let him go, but we seized the opportunity and we let him go into a bushel basket. So we lift the basket cover off right just a little bit, and we both got our heads like head to head looking in that little hole. And sure enough, there he is, running around looking badass. Anyway, after a while, we thought it really wasn't fair to let him stay in there much longer. But, so we took another look, and we were just going to take maybe one or two more looks, and we're going to let him go. We lift the cover up just a little bit, and that son of a gun, he flew out of there at 100 miles an hour and went down the road. Unbelievable. And him and I, my brother and I, although we don't get to see each other because I'm doing more electronic things, you get your families and all, and you kind of separate after a while. So, but we still got the great story to share. What, 10 years ago, 10 years old, so 53 years ago, something like that, 12 years old, 50 years ago. And it was a big excitement. We had 7 houses under me, 10 or 12 kids, and what a great, it was a great time. And watching that depressing news, I thought about that, and I said, it's so much nicer when things were simple. When all the kids were on the street, and a car came down the road, somebody yelled, car, everybody moved off to the side of the street. Car went by, you knew who it was, because there was only so many cars on the street. It wasn't like now you have, 3 cars in a family. It was 1 car in every family, now was it. So you probably had only 6 cars on the street or something like that. So you knew who it was. Then clear, everybody go back up. But anyway, I thought that this might be interesting for some people. I know it has no electronic content, and it's a bit out of character. It's not a storm here. Got the wood stove going. It's only 30 degrees out. Anyway, if you found any humor in it at all, some other stories. Oh my God, we got in a lot of trouble. My brother and I got in a lot, not with the law, but with my parents because they were pretty strict. I wouldn't necessarily subscribe because of this, because most of my stuff is electronics. But if I get enough comments, I might get enough gumption to get up here and maybe tell another story or two like that. If you thought it sucked, you could say that too, and then I'll know end the experiment. Anyway, 73, everybody. Thanks for watching until the end if you did, and here's to happier, calmer, safer times.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. I haven't done a loop video in a while, and I know I've done these before. Seem to be pretty popular, so I thought I would try to take some common materials and make a external loop. Here's the second version, won't show you that for too long. Here's the first version, okay? This is made out of, what the hell is it called? Embroidery loop, okay? Take it apart. All it is, and I'm going to show you close-ups of the turns and windings and everything so that you can windings and come up with a version of your own. This is a 16-inch, I believe it's 16 inches. Let's see. 16-inch embroidery loop. Yep, 16-inch embroidery loop. And it is made by, here's another one. Unfortunately, it's not made in the United States. It's made in Taiwan. The Darice, D-A-R-I-C-E, craft supply. Doesn't really matter who it's made by. What matters is that you can build one of these things yourself very, very easily. And we're going to do a couple experiments here on the Group W bench. Got my trusty Grundig 50, and I'll try to zoom in with the camera here in a minute on that. The other one is that this is not the quietest environment in the world down here in the basement in the lab. So there's a big screen TV running upstairs, and God knows what else. The amazing amount of increased signal strength, especially if you were out, say you're out doing anything in a remote area or something, with just an AM radio, this would be an incredible way to go. And it costs almost nothing. The other thing is, here's my little test jig there. 2 365 capacitors in it and a switch. So we'll be hooking it up to this loop right here. This loop, and all I did was screw it down to a piece of block, sort of a proof of concept. And the nicer one here, this one's made out of walnut. I made this with veneer walnut. You can buy it 1.5 inches wide. I'll show you some close-up pictures of this after, obviously. 1.5 inches wide, and I think like It's a millimeter thick, and wind it on the form, and glue all together through all that. Anyway, you'll see it when I show you some close-up pictures. And I have two windings here with a separator in the middle. If you see this, here's one winding, there's the other winding, you'll see that too close up. But there's this one that jumps over from this side to this side. And the reason for that is so that with both of these, with two windings, I had enough space to put a piece of wood that I carved into that shape so it fit right at the bottom and hold it securely. And then there's two brass screws here. I don't like to use steel or anything near a loop if I can help it. This 365 people fit capacitor obviously has steel, aluminum, and some brass on it. Please zoom in on the radio. You're not going to be able to see my face. Probably a good idea. But I'll be working the controls here between radio and these three loops. It doesn't have to be right on top of the radio. The radio doesn't have to be in the middle of it. You'll see. Let me set up for that shot and I'll be right back. I said I would throw some of these pictures in, so I figured I'd better do it now before I forget. Just a couple close-ups, that's all, of the loops, the winding. You can stop it any time you want and count them if you want, whatever. Anyway, back to the regular program, the VLF. Okay, we're back. So I have my Grundig radio here. It's got a little estimator on it. Unfortunately, you might not be able to see it that well, but we're going to try anyway. Again, this is a embroidery loop. You'll get pictures of the coils up close. And my little test jig here. Oops, I guess I should put it inside where the camera can see it. Just a 2-volt capacitor where I can switch both sections in, and an output that I can connect to anything for experimenting purposes. Okay. The other loop. Ooh, almost slipped over. The other loop here is made out of walnut veneer. It's 1 inch thick, 1 inch wide, and 40 millimeters thick. And I wound that on a core here that you'll put in vise, and then you have of course, glue in between, and it's not all very. And it takes a little bit of time to do that, but it comes out pretty nice, and it's all walnut. So that's it's a piece of 12-inch PVC pipe with a little bearing, kind of a makeshift bearing that I made. Hold it in a vise, and then you wind the material on. Until you get all the 5 or 6 turns here in a loop wound on top of each other, glue it between them all, and then you put either a piece of rope or piece of material around it to snug it in place until it dries. It comes out pretty good. At least for the first experiment I did. So let's fire up the radio here. I'm doing this upside down. That's it. There we go. Where are we? I think we're somewhere near 560 kilohertz. Let's turn it up. Use promo code Curity50. 50% off. That's CurityPrefer.com. Promo code Curity50. Okay, I'll move the loop away. No connection. The energy from this loop is coupling into the ferrite loop that's inside the radio. Okay. And it works even from, I don't know, it's all 6 or 8 inches. Detune it. Probably can't see the tuning, but tuning the capacitor in the front here. Oh, by the way, there's 2 windings here. It's actually all just one big wind, but I made a crossover here in the middle of the loop so that if you look over here, there's 2 separate windings, and I was able to get that piece of walnut in there to hold the loop down to the base. It's just something I threw together, a couple pieces of walnut I had laying around. Nothing really pretty, but it looks a lot better than the one that's made out of the bird. So it gets a little closer. Right. I can do it with hands, and then I'll just take it out of the field. So let's put that one on the shelf, and we'll hook this up. This again is the 16-inch embroidery loop. Let me hook up the little tuning capacitor here. And this is one of those cases where bigger is better. This loop does capture more signal. Let's see, where are we? Okay. Move away. See, we're about a foot away, and it still significantly makes a difference. Alright, let's move up the amp a bit. Let's try, we'll pass 610, that's that big strong station. Here's a good example of using this loop. Here's a 640 that is quite a ways away from here, but I'm going to try and tune the loop to that frequency. Okay. That direction there is where interference. You can see the going out here. If I get this away, the radio is just overloaded. But if I bring it close, this is still comes up, you can actually hear it. Although that 610 is still incredibly strong. So provide a whole bunch of selectivity and all the boxes directionality. Move up. 660 here. Here's a 670. Can't tell if you can see. Those are just nice. Here's a 680 somewhere. And all I'm doing is adjusting this. So now if you're out someplace that's really quiet, like say out in the backyard or doing band skin and quiet motion, these loops will bring signal up incredibly strong. And you don't have to contend with background noise that I have here. 740 is a station down on Long Island. It's about 80 miles away. Let's I don't know if you can hear it, but let's tune that in. There's 7 where that was. Notice the noise flow drops, right? I mean, the signal dropped right off. Alright, so let's move along a little quicker. 40. Let's see. That's pretty around here. Well, let's do 1030 out of Boston. Okay. I don't hear much right now, but I'm going to adjust the loop.
Do so by calling the cell phone key at 144.
Put it over here on the table, and we'll bring the other one, the other loop. Let's see if we can find it in this one.
Window agent wants to be comfortable to enter and information is able to keep the volume working during pandemic.
So incredible field that's generated all around our codes into the antenna that's side rated. You detune it. Let's find another one here. That's pretty strong. Let's go up to 1700. That's about 90 miles away as well. 1700. Yeah, you can hear it. That's a low power skyway. That's skyway coming in there. If I took this outside, it would be just as quiet as a normal station. But right out here with the Alexa and the TV run upstairs, it's not too bad. It's pretty easy to build these loads. 140, 150 microhenries or so, something like that. Maybe as many as much as 200 microhenries in the loop itself. And very build capacitor. This is, if you saw the notch video I did the other day, this is exactly the same thing. This is notch. I mean, this is a parallel tuned circuit. The only difference is that it's huge and it will accept signals. Let's try that again. Let's see if there's anything else.
You are
50, 60. See that and see what happens.
Undifferentiated.
Yep. Kind of tough to tune it, but watch, I'll detune it and move out of the way. So, something you can build up with just a bring back this loop. Okay. It's not tuned, obviously. That's in this direction.
In understanding
5080. Can't have that.
Is the minority meter?
Can't have that either. 1150 is pretty strong here, so you definitely hear the difference. Anyway, that's into that. I'll pull this apart so you can see. Just whatever it is. I'll show you up close so you can figure out. Oh, these dark spots are super glue, just hold windings in place. No big deal. And there's a pin that clamps these. There's usually a pin that clamps these two together. You take that pin out, and then you just screw it in place on board. So quick. This is like a 1 hour maximum project, and then the tuning capacitor goes parallel. So thanks for watching. Oh, we're up to 920 subscribers, I think. 920, and goal is up. So if you enjoyed this or any of the other videos, please hit the subscribe button and let me know or make a comment. Thank you very much for watching. This is W1VLF at WLF from the Group W Bench, signing off.
W1VLF.
So most of you guys have only seen W1VLF as an old man, but I will indeed assure you that in my 20s I was a much different person. This first shot here is a video of me in my 1969 AMX with a 390 4-barrel 266 center spurters, a tunnel ram, 513 roller rockers, and that was where I was testing out down at an abandoned road. Got pinched on the way back home too. That was very, very sad.
Quick shot of myself and Mistress of the Macabre, Elvira, back at the old Channel 20 days. 1,300 feet above the ground itself, here at the Channel 61 tower. I had to shimmy out on a pole and take some close-up video of a broken antenna that needed to be repaired. And this shot is courtesy of Clem Kaczynskis of Channel 20 in Tape It Film Room. Anyway, enough of this stuff. Let's get on with the video. W1VLF, over to you.
Hey, I'm Paul, W1VLF, and welcome back to Storytime Birdo. A couple of things. My pad again, because brains all are in short supply, especially these days. No electronic information in this one. It's story time again, except for a shameless promo for my next loop coming up video. Two loop videos coming up. One is showing some of the problems that you might have with one of these style loops, and also a way to modify it, or not modify it, to use it in a much better capacity with standard AM portable radio. So stay tuned for that. That'll be after this. So the first thing I want to do is I want to kind of dedicate this video to my friend Ray, who Ray was one of the guys that we hung around at McDonald's in 1979, 80, 81, 82. There were only two things on your mind, at least on my mind, and one was cars, the other was radio. And Ray's been a medical professional for how long ago was that? Let's say 4 years. And recently found him again on Facebook a year ago or so. He's having a tough go right now, so if you got a spare minute and you can say a prayer for Ray, let's kind of do that, will you please? Oh yeah, why was I on Facebook? Well, I'm on Facebook for the same reason half of you guys are on Facebook but won't admit it. And we're gonna hold girlfriends. And you know, you look up some of these people, Facebook knows it, and next thing you know, they suggest, hey, do you know Ray? I'm like, I do. Anyway, I didn't realize he had an interest in electronics until just recently. I looked at the statistics on my videos, and I found out that the major group of people watching are between 55 and 65, bunch of old farts. I guess I'm pretty big in the nursing home crowd, retirement home places, but maybe not so much in the mainstream of the world. So, so going back again to a time, the 79, 80, 81, 82, and even before that, probably 74, 75, when, what did you have to do? You had 3 channels. There was no television whatsoever, really three channels, CBS, ABC, NBC, and the occasional independent out of New York City. It was a time when your mom and dad would set up a TV schedule because there's 4 of us in the family. My brother Tom, Chris, my sister, and myself. And from when they would go out on a Saturday night to a movie, they would say between 6:30 and 7 you get to watch this, and from 7 to 8 you get to watch this, and try to equally divide it amongst the stuff my sister wanted to watch. I didn't want to watch, so when it was our turn, I would turn the channel where we were supposed to go and pull the knob off and keep it with me. So there was no way she could, and that really pissed her off. Right? We're good friends, of course, brother and sister now, but oh my god. Anyway, that's not what I want to talk about. What I want to talk about is basically the kind of crap that we got up to in, back in those days when there were only 2 things on your mind. One, cars, and other, girls, right? So there's a place where this courtship routine or matching routine takes place. In those days, it was McDonald's. And there would always be groups of guys with their cars. You know, some people will come in here and say, "Oh, the car is really an extension of your." Maybe it was, because we're always working to make it bigger, better, faster. But brakes weren't a big thing back then. I can remember driving around with only rear brakes for quite a while because I couldn't afford to put the new brake lines on or something. I don't know. But luckily, we didn't get into any accidents. Drinking age was 18. Walked right into a liquor store at 18 years old. Hell, I didn't get my license until 18, but walked into a liquor store buy anything you wanted at 18. Now it's 21, which is quite a bit more reasonable. But I'm going to give some idea of some stuff that we used to do at McDonald's. It was, again, a meeting place, right? All the guys would come there to the cars, they'd back in, all the overlap in the cams and header noise coming out and exhaust notes and or something. And then some guy would come from out of town and it would be a drag strip up at the top of East Main Street in Bakerville. This was in Torrington. But so inside McDonald's provided a couple of things. It provided shelter. It provided a place where you could sit around 4 or 5 of your buddies and eyeball 3 or 4 girls that were over there. The first topic that I want to cover here is what we used to call babe runs. Babe runs were a lot more popular in the summer than they were in the winter because everybody would constantly be outside. And McDonald's that we had a U-shaped driveway come in on the left, and you'd go around the back of McDonald's and out, and 90% of people were just passing through, trying, I guess you'd call that like a meat market or something nowadays. But anyway, they would pass through, and there were a few rules and regulations on babe runs. And what was a babe run? Well, a babe run was if you were hanging out with 3 of your buddies and you saw 3, what you guys thought were attractive girls, you would chase after them. Almost like in caveman days, right? That was part of the mating ritual. So, but there were some rules. Right? You got this one and that. Well, you can't say this crap anymore today. I got one right here. I got one with. You add in whatever you want. But the basic rule was if there were 3 girls in a car, only 3 guys could go. Had to be an even number of guys. And the idea was you would chase them around or drive around, follow them around, and they would be looking out the window and you could see them laughing like hell. And if you were really, really lucky, they'd pull over to a Star's apartment store parking lot, which was, of course, there was nobody there at 7 or 8, 10 o'clock at night. The store's closed at 5. And if you were even luckier, you would pull right up next to them and you'd talk and this and that, and you get kind of meet. And but it never worked out. At least you got an introduction, right? Probably thinking back, that might not have been the best way to approach the situation. I have a better way to approach the situation. I'll tell you in a minute or so here. But I do want to give a shout out to my good friend Pete, nicknamed Doc. I'm not going to use last names here because who knows who's going to see this. But Pete, and there was this absolutely beautiful girl. She was a really nice girl too. I'll just call her. I don't want to call her by first name. Sally. And Sally was really beautiful, and everybody knew it. And Pete, the doc, went on a bay run, and he's the only one of like the 50 guys that have ever attempted this that actually got married to a woman, had a successful family, and to someone that he met on a bay run. So, and I guess it wasn't quite all that effective. So a couple of things. Before I knew anything about cars, I went to Olive Technical School till 1975. And in 1974, the only thing that I really had any interest in whatsoever was electronics. And so a couple of my best friends were already into cars. I just didn't have any interest. One of the graduation years, maybe 74 or so, or maybe 75, I don't know. We went up to this place called People's Force, and there was a big party. All the kids, it was school shanction, buses and whoever was driving at that time. Like I said, I didn't have my license until I was, I think I was like 18 and a half. So anyway, we're up at People's Force, and the same sort of ritual things going on between the guys and the girls and trying to meet girls and all that. And so my friend and I are up there, and of course we're peeling out, right? I mean, nothing impresses girls like squeaking wheels and smoking tires and all that stuff. So what happens? Now, I didn't truly understand how a car worked, how it was rear-wheel drive, how it was, the motor connected. So what happened? The exhaust system fell off, right? God damn it. So it's making a whole crap load of noise. So if you can imagine, I think it's a 68 pallet, big car, right? Not something you should really be beating on, but what the hell. So the exhaust system, the muffler fell off, and one of the guys happened to have some waving wire, and he said, we could just tie it up now and we can fix it. So I'm laying under the car. I can imagine there's like 3 guys laying under the car, and we're all got baling wire, and I'm saying to myself, what the hell's the matter with these 3 guys? They're all debating whether or not where to hold this muffler, what to tie it to so it'll survive the trip, the 10 miles home. I'm going, what the hell is the matter with these guys? There's this long cylindrical pipe that goes all the way from the front of the car all the way to thing connected to the wheels, the rear end. And I said, wait, David, why don't you just tie it around there? Apple couple is perfect. It's all in line and everything. And he says, you dumbass. And again, I knew nothing about cars. And he says, you dumbass. He says, that's the drive shaft. You can't tie it to that. That spins around when you're driving. And I think that was one of those, what do they call it, aha. And from after that, I started to understand a little bit more about cars. And I'll show you, I had a couple of drag cars and that. I'll put some pictures up later on. But get back to McDonald's. One of the things that we used to do, of course, in wintertime when you're hanging out and you're forced to hang out. And there's a manager, and he's going, oh, those damn kids over there hanging out for too long. And one of the things that guys used to do was to bring car parts in under their coat and just leave there. Like an old camshaft, rocker arms, not even brought in a head, a V8 head, and put it under the bench. And then, of course, that night, clean guy there. What the hell is this? Oh my God, that was terrible. There's so many stories from back then. No, I don't know if you guys find this funny or not, but we certainly thought it was. Yeah, it was such a simple time that bring a camshaft in and leave it under the seat and having somebody else have to clean it. That's kind of shitty, actually, right? But it seemed funny as hell at the time. Another thing that we used to do was, now I don't smoke, I never did smoke, but we'd all get what we call cigars, right? And they say, and back in those days, you'd smoke inside McDonald's. And we noticed one night there was some old guy in there smoking away, stinking out the whole joint, right? So we decided that we'd all get cigars, like 5 or 6 of us, and we'd separate into like 3 tables around the different, and we'd start smoking our cigars and really stink up the joint. So that was fun, and we did that a couple times. Of course, we got kicked out a couple of times. That was no big deal. You got kicked out. It was like a one-night event. You could come back the next night. So in order to get more smoke per unit of effort, we used to shotgun the cigar, right? You put the lip part in your mouth and blow backwards, and you just had a jet of smoke coming out of the cigar. Just a long, and it would quick. Between 3 people doing that, it would fill the whole joint up with smoke. And I thought to myself, well, that's not really a good way to do it. So I invented this device. This is supposed to represent a cigar, right? It's red on the end, there's the burning. And I thought, if you light the cigar on both ends, and you puncture a hole in the side of it, okay, and then you blow on it, now you have the potential of 2 people per cigar. So that got us up to, needless to say, we got a lot of trouble for that. I think we got kicked out for more than one night. The manager was Harvey, and you think back to it now, what would you do if you had a bunch of kids doing that stuff and you're a manager of a store? you just couldn't get away with it. But at the time, it seemed like it was okay to. Like it nowadays, I don't think so. The last little story that I want to say about McDonald's. Personally, I like the Dave one the best, but this was an idea that I had. And I used to sit back, way in the back, away from the counter, the service counter. And people would pull out the napkins, from the napkin dispenser where they're all stacked in and they're spring loaded out. People would pull out the napkins, 3 or 4 or whatever, and walk out the door. So I went up and I got a couple of napkins, and one of the guys I can't remember what his name was now, but he was very artistic, and he had incredible handwriting, and I had him write on the napkin that the bearer of this napkin is entitled to 1 Big Mac and a drink of their choice. And then, with a little bit of cover from my buddies, I pulled it back. I counted how many the napkin holder, pulled the napkin holder back. I think it was like 10, right? And I shoved the napkin back in again, right? And I closed it. And we were all line of sight to this, so we could see everything that was going on. And we were literally counting the napkins off. All right, so it's 10 back. That guy took 2 napkins. That lady took 3. No, okay, there's only 4 more to go. And then, of course, that napkin comes out, and the people are like, what's this? Oh, Mr. Manager, look at that. And he looked at it, and he looked back at us, and we figured, we're going to get this phone out. We just better get the hell out of here right now. Jesus, those were good times. I don't really know how to end this, but again, watch later on for actual electronic content. But there's just some of this stuff. When you didn't have anything, you did have 2 things. You had your regular car, your cool car. Mine, in my case, was a 1969 AMX 390, and I'll show you some pictures of that where I had the front wheels up and down at the racetrack and all that. And you had your winter crasher, right? Oh, yeah, the winter crasher. There was rules on a winter crasher. It had to be big, okay? It had to have a bench seat. But you got a girlfriend. Last thing in the world you want is her to be, you to be sitting here and her to be sitting way the hell over here. That's no good. It had to be big because you never know if you might end up, hopefully in the backseat, whatever. And it had to have an automatic entry because you don't want the stick shift or anything in between you and the blow up tummy you were having there. Anyway, so you did have those things. You had your wind crasher. Oh yes, another thing is it had to have good heat. It had to have good heat. Power steering was like a plus or minus, and typically you'd find an old Chrysler or Plymouth Fury or something, 67, 68, for a few $100, and you drive that around all winter long. And big cars like that were better than some. Those front-wheel drive. I think the only front-wheel drive thing was a Tornado back then. But yeah, those were much simpler days. So with that, I'm going to take my fresh shave, my Old Spice aftershave from the 70s and 80s, and my Moxie t-shirt, and go work on my real video. I don't know. I don't know how to close this. There's so many more stories and stuff. Anyway, oh yeah, if you enjoy this because you're between the ages of 55 and 65, brings back some memories of your own particular courtships or mating rituals, throw them in the comments below. Again, if you liked it, say yes, I did or I didn't, and pass this on to your friends if you think they might like it. 930 something subscriber now, and pushing 1,000. It's up quite a bit since my last loop video. You can tell I'm kind of OCD kind of guy because I keep going back and forth, or I have very poor, concentration on any particular object or period of time. Anyway, so thanks a lot for watching. It's been, wow, 20 minutes? Get out of here. Holy crap. Anyway, thanks a lot for watching, and look for these other videos. They're going to be coming up very, very soon. Thanks a lot. Many Grace from W1VLF up here in the northwest corner of Connecticut.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. The last video I did about electronics was about loops, and this one's going to be about loops. Move this guy over. Whoop, not that guy. Move this guy over. And the next one's going to be about loops as well. But so, let me just give you like a preview of the next video. It's like a teaser, right, Paul? It's going to be a PVC. It's going to be a PVC loop, and the reason I'm going to make one of these style loops is the common question is that I get on all these videos is how many turns and how far is the spacing and how big the diameter and what can I use, and lots of questions like that. All the very same question that I had when I was first starting off this a long time ago. And there really weren't any calculators online, and I looked. I don't really see any loop calculators online. I did find 1 or 2, but most weren't available. So assuming that you can't find one of those online, this is what I did. I took PVC pipe and I just experimented, and I found out I'm going to put way more turns than my gut says. My gut's very seldom wrong. But I'm going to put way more turns on than I need, and it's basically relatively far apart because I know if they're bunched together that the hue of the loop drops. So with just some fundamental things, I decided to take a couple dowels, right? This is just your standard, I think it's 5/8 dowel or ½ inch, can't remember. Doesn't matter. But what I did was I got slots. Each one of these slots is 1/4 of an inch apart. And then you drill a hole through the end of a piece of PVC pipe, okay? Just a standard 2-foot piece of PVC pipe. Shove this through, it's a pretty tight fit, and then hot glue it inside. so they have all these the slot quadrant slots. And let's see, there's probably 12 or 15 over here, 12 or 15. There's roughly 30 turns that you can put on here, which is going to be way too much for the broadcast speed. But the whole idea of this loop project, this is coming up next. Not really what I want to talk about today. The whole idea here is that you can take and wind this loop, of course, try to wind it symmetrically. Maybe 5 turns out this way, 5 turns out this way, and then use with one of my other videos to figure out where it resonates. Okay, it resonates at 2,000, well, I need a few more turns. And this way here, you can purely arrive at what works best for you. So I'll show you all these parts up close. And the other thing is, of course, they make these X's. And if you look at this, you think about this X, this is the wrong size, this is for a bigger pipe. You put this in, right? You put the what do you call it, the PVC cement on here. You got about 2 seconds to make a decision which direction this thing is pointed. And that could be a real problem. Or you could drill it after. You put all 4 pieces in and drill it after, and that can be a real challenge. But I've chosen to drill all 4 pieces first, put all 4 of these in, to make this easier, so just about anybody can hold it. And you can make a simple X out of aluminum. This is aluminum angle iron. It looks like it's 1 by 1. I'll show you how to make this. But you can see it's pretty rugged, okay? 1 screw is holding this together with a couple of slots. But what happens then is you connect, you can use tie wraps, or you can use hose clamps, and that allows you to line these up. Let's see, I can't see if this is a picture, but line this up perfectly so that you're not stuck with a T over here, and you got one that, oh Jesus, it froze up before I got it aligned properly. So I'll go into all that. The basic for this video in this one is that I didn't do it by formula. I'm more of an empirical guy. So I wound 10 or 15 turns on each side, and I found out, well, that resonates way too low. So I pulled off 1 turn at a time. Right? The copper wire is relatively inexpensive. So you pull out 2 turns, you check it with the capacitor, and find out where it resonates. So it's really easy to do. The common capacitor is at 0 to 365 pf. The capacitor that everybody seems to have in the jump box. The hardest part of all is cutting these slots with a hacksaw. I did it on radio alarms all night because I used to sell these loops. I would set up about 10 of these in a row and cut them all at the same time because it was just way more cost effective. But can easily be done with a hacksaw. So anyway, that's enough of that. That'll be the next video. And we'll go into how to build that. Today's video is a little bit different. In the last one we talked about this loop here and how it looks kind of nice and everything. How proximity to the radio takes a field that's generated by this loop and puts it into that radio. But there's a kind of big problem with that. And so I'm going to clean off the group W bench here and then come back and I'll show you what my fix for it. All right, I'll be right back. Don't go away. Actually, I'm going to go. I'm going to leave it running. I'm just going to speed up. Let's go in. Okay. So, the last time we were talking about these loops, I didn't show this one last time. This is the Grundig AM200. And we're going to use this one specifically today. I'm going to do this real quick here, and then I'm going to run outside, freeze my ass off, and do this in front of the W1 VLF firing range and designated quiet spot out there. There's 2 in this general vicinity to make this a really effective test. But what is this test going to be? Well, here's the problem. You have your radio, and maybe you have it on a bookshelf or something, and she says there's nowhere to put this loop, right? It's just not convenient. So, well, look how nice this is. The AM200 has an outlet that goes right directly into the radio. But a lot of these older AM radios don't. So you're trying to squeeze this thing in there in some convenient way, and it's not pointed at the proper station and all that crap. So here's something I used to do a long time ago, and it still works out quite well. And that is you take a small coil. I'll take some close-up pictures as I can show you what this is, but I think it's about 20 turns of list wire on a half-inch piece of PVC. And then you stick a ferrite through the middle. Inside here, somewhere, probably here that. Okay, it's kind of noisy, is the loop stick on top. There's normally a loop stick right on top. So if I put this piece of ferrite on, nothing happens. Okay, but if I put this on with the coil attached, and then come over here, resonate this one. On your own way. Now this becomes the antenna back here. Yeah, I probably want to build this so that it was, wouldn't fall off when the train is moving. Now this antenna, through a piece of wire, couples in, makes a fuse on this antenna, this coil over here, and couples in, and now you can place it down anywhere you want, and still tune it. Okay, there you go, tune it. Now I'm going to put it away. Okay, let me grab my favorite one there. That is down the one in Boston. So Boston's that way. You can't see mine. Boston's that way. South is that way. So there it is. It's null. Anyway, I'm going to take all the crap outside. So and enjoy out there. But it's a loop stick. Came off like an old stereo of some sort. Caution, don't hold this this bar to lift the amplifier. So I'm gonna take this off. I'll turn it up. Now let's move this. So I don't have to have the loop close. Here, now this loop is bigger, right? This one's much smaller, so this one's gonna have a big effect.
Any questions you have?
Real rough, but again, here's another little loop stick that I got, in my scrap box. I'll pull this out, plug in this other one, retune out. So if you had a loop this size, Jesus, if you had a loop, you can't really see that, huh? Sorry. If you had a loop this size, you could pick wherever you wanted. Null the station, peak the station. Alright, enough of that. I'm going to go outside, 30 degrees outside, freeze my butt off, and do this in a quiet area where the results are even more impressive. Okay, here we go. Not putting the financial camera for radios. No, 2 for radios. And it's a louder. Nice. 10. Alright, reset. And okay, so we're out here in the relatively quiet woods. Radio frequency wise. Some birds around and stuff like that. So this is the last you're going to see of my face in this segment of the video. Zoom in on the radios and the loops and show you what I'm talking about. Alright, so let me do that and I'll be back. Alright, so see the top of that loop? I guess so. I'll move back to a little bit, yeah. Alright, so we have 3 radios out here. Tiny little channel master or something or other, really small antenna, portable receiver. The one old Radio Shack, kind of general purpose radios. And 2010. Let's start off with the 2010. First test with, now imagine for a minute, you have a place where you want this radio, it's on a shelf, you can't turn it to orientate the signal the best. You can't really put a loop right up against it. It's not practical. You can't really put it in front of it because then you can't really see the radio. So here's the fix for that. The fix for that is just a common loop stick. An everyday loop stick antenna that you pull off your a junk radio before you get rid of it. I'm a big believer in parts, saving stuff. As you can probably see on my bench there, there's all sorts of crap there. Okay, so white and black are typically the wires that are connected to the 200 or 250 millihenry side of the loop pair, and the red and green are typically the ones that go off. That's the coupling loop. So I'll just set that right there. I'm going to move this guy out of the way for the moment. So let's turn this big on. There's a 510 couplets. I can take this gear batteries. Sony failed me, so I'm going to put that off the side. I'm going to start off with the Radio Shack. Alright, we're tuned to 506 kilohertz. It's actually in Springfield. So we'll put the loop on top, no difference. Of course, not plugged in. Put the loop on top. Now we'll go over here.
And there's structural information. I can have healthy inward light that leads to a productive outward light.
Bring wire up.
Hey, there's a rally again.
Put this right on top. Okay, and now it's loop. So
the person next to you again, what are you called?
I can effectively null that station right out.
No, you have
What
great
is important is that this is coupled properly long ways.
How does it go up the hill?
Move away.
No neighbor trolley is cable car.
Okay, and I'm going to
San Francisco and city that.
There it is. Now, first you have this other wooden loop that we're playing with, so I'll remove this out of the way, and I'll put this up against the radio.
Behind the scenes is amazing.
You notice it's much louder.
That pulls.
But that one of the reasons for that is the big circumference.
That's what pulls
about
cars
15 inches and lower. This one here is only
If
about
you
8
are a
inches.
trolley.
So, let me get that out here. Let's take our old surplus loop stick, put it on.
Hear me. As the cable car has no power, electric cable, the Christian has no power unless they're holding on.
And I can detune this loop, or I can take this away. And then this is what you're left with. This is the actual volume of the station coming in.
You've got no engine. You've got no
So
independent
you still
means
have
of power.
the ability of running external.
Where do you get your power?
And the advantage of it by knowing. Alright. I'm going to pull this away. So when you put the slew over on top of that antenna, this takes over coupled so tightly, and this is how you're receiving the antenna.
That's the fact. I'm sorry. This is not surprising.
So let's try something else. Let's say you don't have a loose in your array of in your drum box. Let's say. So took this piece of CPVC pipe. I think there's probably like 25 turns in here. I don't think it's that critical. But what I'm going to do is I'm going to hook it back up here. I'm going to hook it up to the AN200. And we're going to put it on top. It's a little light, and everything getting really brittle up here. Stuff. Not everything. So let me try to tune it without core. Not enough coupling. So let's put the core in. And lay it right there.
Even afford to lose that. So help me at this moment get right for you. Or help me to have the right attitude about this sensation. How do you have it?
It's only a short loop stick like this. So you're going to want to try to figure out how to center this loop on top of your radio.
I'm a trolley. I understand that. I'm holding on to. So if we would not.
Okay. Very little effect over there.
At verse 11 and 12. Or 10, 11, and 12. We'll look closely at these next week. What does Paul say? I know how to obey. I know how to abound. He says, I learned to be content. No matter what.
So who wants to go out there? Range around 20 turns of billy wire. It's going to hold number 61 shot. Stick an old number 61 ferrite rod in there. And yeah, I should have signed.
Now, let's what you focus on. The most important point of what we're sharing today is your crop.
Let's move up to, I mean, this radio has got a pretty good antenna on it to start off with, but nothing like that. So there's a lot of stations. Okay, there's one that's kind of noisy. Put a loop on there.
Whatever your listeners, it's an important ring. So when that's on to seal that ring on anything, the weight and power of the Father, his whole house behind it. Incredible. Incredible. The Father would give this boy this ring because it was only given to those that trust him. My father will forever be looking at me with the side of his hands. They're trusting me again. Right? And suddenly, before his next even proves his word, he's now covered and trusted in the sight of his Father. I'm looking for this kindness.
The whole idea of this video is just to get people away to use an external loop like this, but I don't have to be subject to having it really close or in front. If this was on a bush, I don't know, so what? Grounding beats really nice radios. They don't all have antenna input, either this, but now you can take advantage of the extra signal that you can gain from a loop like this. Okay, and still be able to leave the radio in one position. Now, the difference between this loop and this one is just the resonance circuit, IQ resonance circuit. Okay, lift wire, capacitor. It doesn't have a coupling loop. This could easily have a coupling loop if you wanted to. It would just simply be two more turns wrapped around, and those would come out the back and go to this coil over here. So, I mean, I think I rambled on long enough, but just wanted to kind of get this point across. So keep an eye out for the other video, the one how to build a loop, and that'll answer a lot of questions on how big do I make it, how many turns, and it's going to be a way to do that tricky. And I don't profess to have any unique designs or build it exactly like this. What I'm trying to do is inspire people to build something on their own, trying to give you the root or the avenue you get there. So that, I'm out here. 73W1, always forget this. See, we're up 838 subscribers, and you keep that 1,000. So if you could please subscribe, put a little message in the video. Let's, whoop, we're off residence. It's my first outdoor video. So I'll sign off to you guys who reads the shoot for pictures of power here. 73 for everyone to Alright, we'll take a walk over to the top. Bunch of pole masts, and that's a the old C-band dish mast. Oh, look at this. The targets are still up there, very set up. Hey, we're going over to the tower. Just a quick basic tour here. This is the roll of rope that allows me to lower the 300-foot dipole that's at the top. If I can hold still and zoom in on the antennas. Hard to tell if that's focused or not. Let me move over to one of the anchors because I want to show you another video that I'm going to make coming up. And that video is on how to pull a dipole up to the top of that tower, or close to it, depending on the size of the dipole, without ever climbing that tower. And here's part of that right now. Very simple. I'm going to try to do a video on it before it gets too cold to pull these. Okay,
one rides up down the wire, goes right up the guy wires. The other one, you put a rope through, you pull towards this way, and these hoop is one on this anchor. Where's the other anchor? I don't know, 150 feet away somewhere. I can't see, it's a little bit farther, but do the anchor. And you can hold that pole up, all depending on how far apart your guys are spaced. Alright, speaking of space, I'm done under. 7-3, thanks for watching. This is W1VLF, sending out at anchor 1.
Okay, before we begin today's video, I'd like to know how this, from 1979 December 3rd, turned to this, from 2020. What happened to old stumping grounds? Nothing stays the same. Anyway, I just thought I'd throw that nostalgic picture up there.
Hey everybody, my name is Paul, and welcome to Stories from the Top of the Hill in Torrington, I guess you could say. Well, as usual, stuff in my face. Some kind of protein bar thing that I don't know what yours from, but at least it's not. I'm sorry, I just can't stop laughing when I make these videos. At least it's not 13 cheeseburgers out of day. Well, last night was a pretty wild time on Facebook. Jesus, I don't know what the hell happened to me, but maybe it was drugs? No. All sorts of memories just started popping into my head, and there were about 10 people on there, and we were firing comments back and forth. The big Catholic fire in Torrington at the warehouse there, and where everybody was at that moment. That was kind of interesting. I think I was at the bottom of Hoffman Avenue. And I met my first girlfriend there, much to the despair of my mother. But someday I could go into some stuff there, or my old man. But anyway, I think what else did we talk about? We talked about Tango, a little bit about Bicardi 151. Well, maybe one of these nights I'll go into that or after. But really, what I wanted to talk about was let me get a little better because my notes are getting smaller. Burnouts and smoke shows. You could take burnouts two different ways, right? The one you do with vehicle, or the one, the actual burnout. So there are three really notable burnouts in my time at McDonald's, and one of them, I'll just call this guy Bobby T. Okay, I think Bobby had a Pontiac Tempest or something. 6-cylinder. Wasn't, it was a very nice looking car, but it wasn't really it was kind of an aquamarine, I guess, greenish color or something like that. It really wasn't a powerhouse. But he had the forethought to actually change the right hand tire in the back, the driver's side tire in the back, to an old crappy tire that he had, with full intentions of going up to the top of the hill and lighting that tire up and just seeing what happens. So we're over at Stars, which is where a lot of this crap happened. Oh my God, there was the bottle rocket incident there was the fireworks, there was... Anyway, we were there this night, and the whole idea is Bobby's going to go to the back of Stars. Not all the way back, about halfway back. I mean, hell, that's all he really had to do to get away from the main street of people. It was about, I would say, 10 of us all hanging out, and he rolls that thing, puts the front wheels right up against one of the curves around the outside of the parking lot. And then, a slight touch of the brakes, and then starts revving the engine. And of course, the stick didn't have enough to break the tire free, but... So we helped, right? We get over there, and you grab the wheel well the car, and you pull it up, and next thing you know, the thing's smoking, and people are pouring water on that. And I'm telling you, he generated a cloud of smoke. Pretty soon, the 10 guys that were there were probably a couple girls there too, couldn't see each other anymore. And we were waiting and waiting. I mean, the end result was we knew the tire was going to pop, but I didn't think it was going to be anywhere near as explosive as it was. I think it took probably a good 4 or 5 minutes, maybe more, because the tire was pretty bald to start off with. But anyway, of course, behind me burnout, there's always a big pile of rubber and asphalt laying back there, and it's smoking away. Anyway, this cloud is huge, absolutely huge, and we're all hanging around coughing and barfing our guts out, trying to stay around. And then inside this gigantic cloud of smoke, there's a bright red flash. And I don't know where the hell the red came from, but a bright red flash, and the tire literally exploded with it sounded like an atom bomb going off because we were only 5 feet away. And of course, the car dropped right to the ground. We had to change the tire and everything on it. But thank you, Bobby T, for that wonderful experience. That's one of the best burnouts. And here's burnout number 2. Now, I gotta be honest, I forgot Ed's last name, but Ed had a big station wagon. It wasn't so man station wagon. It's a big white station wagon, and we were all gathered, again, probably 10 or 15 of us, in Stars parking lot, up where the what's that thing, the Dunkin' Donuts is. It was a wide open area there. All of us would park there and get out and bullshit and do all that. So Ed pulls up at the light between 24th Street and East Main. And Ed always liked to light him up. He'd like to light him up. So of course, there's Ed at a light. There's all us guys hanging out. We're going, Ed, come on, light him up, light him up, light him up. So really to oblige, he lights him up. Let's not them up. One up, the passenger side. This wasn't a posse car. And of course, the smoke starts growing, right? Big cloud of smoke. Well, Ed didn't see it. I feel bad. I don't know if he's out in the audience or not, but what Ed didn't see was as soon as the smoke could stir the back of the vehicle, a police car pulled up right behind him.
And we're going, Ed, no, no! And I think you're saying, no, no! And slowly, this cloud comes off the back of the car, totally engulfs the police car, right? And, oh, Jesus Christ. Poor Ed. I don't think he got hitched. I think I talked to him a little while back, but anyway, this big station wagon, clouds, it's like it's slowly engulfing the police car, because he couldn't see it, right? And about 2 seconds after he lets the light turn green, he lets off a brake and pulls away, right? And when you do that, you drag this column of smoke with you. Anybody who's ever been to the races, seen that, you just suck it away. But before that actually happened, the light came on. He couldn't see the police car at all. It was totally encased in this beautiful rubber asphalt generated smoke, which quite honestly smelled pretty good. And the cop turns the lights on, and all you could see was a blue cloud, a red cloud, a blue cloud, a red cloud, a blue cloud. And then as Ed pulled out, thinking, wow, just did the greatest smoke show of my life, and pulled that stream, the cop car became visible. And I think it was down at Leo's. Was it Leo's at the time? Pulled in there, and not really sure what happened after that. The other smoke show I want to think about is more of a personal one. It has nothing to do with cars, but when you're a kid, and there's nothing happening. There's like nothing to do when you're. This was much younger than the car days. This was like when I was probably 14 or 15. We had to live right near A&P, right? Like in Pacific County. And I don't know, I guess it was kind of pyro or something at the time. I used to just go over there, and I would buy Ohio white tip, strike on anything matches. Blue tip or white, I forget. Whatever one they were, you could light them off on anything. And, you'd be able to do with a little knife, cut the heads off, right? Cut the heads off. You could maybe 100 of them or so. And it was funny, the lady over at A&P said, what are you going to do with all these matches? Oh, they're for my mom. So, okay, all right, they're for your mom. So, you take maybe 50 matches or so. Now remember, he said strike on anything matches. And you lay out a sheet of tinfoil. You put 3 or 4 layers of toilet paper on top of it. If you're really devious bastard, put a good sprinkle of sulfur. First thing my parents ever did was buy me a chemistry set when I was little. Powdered sulfur smells like farts, so so then you roll it all up into a ball. You have to be a little cautious here, because you don't want the thing going off in your hand. So you roll up into a nice neat ball. And now, you have this somewhat inert tinfoil ball. It doesn't look like anything. But I'll tell you, you chuck that against a brick wall somewhere, or smash it on the ground, just throw it on the ground, and all the matches grind together, and it will let out a cloud of smoke like you would believe. Not enough to explode, but just a cloud of putrid smoke. Absolutely horrible. So one day, I'm building weeds in my bedroom. Of course, maybe your parents don't know. Maybe they knew. Maybe they said, oh yeah, he'll bring something. This is scientific. But I don't think they know. I think my old man would kick my ass if he ever saw button match heads off in the bedroom. So I just finished it up. Right, I get it all in a nice little ball. And I don't remember what I was doing. I was moving something, but I dropped it on the floor, and something fell right on top of it. I think it was a book or something. It smashed it, right? And it filled up my entire room with smoke. Well, it wasn't my room. It was my room, my brother, and my other brother. We had three of us boys all lived in the same room, because my sister, of course, had her own room. So this was our bedroom. So luckily it had 4 windows. And I opened it up, and it was dissipating. And one of my neighbors called my mother, told her what happened. They were all gone. Most of these stories of pyrotechnics like this were done when my parents were at home. An example, rolling flaming models would revel glue on down the driveway. Anyway, this isn't really a long video, but maybe I'll add in one more story. How about one time when they would plow the snow over at SAR's parking lot, a gigantic pile, right? At least what we thought were gigantic piles. There were a group of guys with Jeeps that would always, drive up one side, go over the top and down. And these were all the short wheelbase Jeeps. But there was one guy, let's call him Wolfgang. Let's just make up a name. He had a long big Jeep, and he went up the side and went over the top, and when he got to the top, the long wheelbase Jeep just ascended itself right on top of the snowbank. And these were high, and so there were like 6 or 8 of some guy pulling down in the front, some guy pushing up on the back, trying to get some tires somewhere to get out from under it. I don't really remember what happened there, but that was an unfortunate incident. He got the short wheelbase ones had no problem whatsoever getting over, but the long wheelbase one he had, which was really cool, it was like the only one around, got stuck on top on that flat. Oh my god. Oh my god. I guess I really don't know how to end these, but do any of you guys know where Alto Terrace is? I'll just leave it at that. So for people, somebody commented that I got a big West thing here. Look at that, it's already starting. So I'm gonna end this before it gets too big. A shout out to Doc, Pete, and Ray, and Brian the tow truck McDonald, who told me to erase this for all those times. Now I find out from on Facebook last night that he had a hangover. Well, we all made it through there. Anyway, I'll try to think of some a little better, but if you have any comments, throw them at the bottom of the screen. And we'll see you later.
Hi, Jim W6LG, your YouTube number 400 Radio Basics. Welcome to my radio room here in Rockland, California. Over the last few months, I've not been able to go anywhere, really. So I've been building a lot of things and repairing a lot of things that I put off in years gone by. One of the things that I built is an antenna switch to place at the bottom of the tower to switch between 1, 5 antennas. And I'd like to show you that it works. It's a really pretty simple device, but it has a whole lot of advantages. And we're going to test it with the Nano VNA, see how much loss is created by my M0ODZ design. And we'll do that right after this break.
Whiskey 6 Lima calling CQ OCQ. Calling CQ OCQ. Whiskey 6 Lima.
The time I'm recording this is December 2020, and the virus is claiming huge numbers of deaths every day. And yesterday was the worst so far, worst loss of life, even greater than 9/11 and other terrible things. Because of the loss, a lot of us are staying home and doing things around the house, and so I get myself pretty busy building things, which is for me a lot of fun. I had a coax switch at the bottom of the tower, and this is what it looked like. Forget what brand it is. This is, I'm not complaining about this particular manufacturer or how I made it. I had two of these. One of them has failed, and what failed was the relay contacts. And it may be that they're just not quite good enough for what I was attempting to do. I'm going to switch to another camera and bring that over here to show you what the relay contacts look like. They are rated at 8 to 10 amps depending on where you read, who you read, and I'll switch to that as soon as the other camera focuses. And we will talk a little bit about Ohm's law and what that entails. So here's, see if we can get a better picture. Here's one of the relays. There is a position switch. Those are six different contacts, switch channels, and there are the Bluetooths are MODs. So if there's a lightning strike in the area, there's a high voltage on the switching line. It takes that ground, which this thing will focus. The relay contacts, as I said, are rated 8 to 10 amps. But here's the catch, and this is maybe where there's a mistake in the design of this device. Maybe the relay contacts are 8 amps. Well, let's say 10 amps. It could be 0. Let's say 10 amps. So if we're going to figure power, we know from Ohm's law that power equals the current squared times S. So it's I squared R. We know from Ohm's law that power equals I squared R. So just simple math, if it's a 10 amp contact, 10 amps squared is 100 times 50 ohms. So is this good for 5,000 watts? Well, maybe not. I tried to source from the manufacturer of the relays what their rating is, and it appears that it's somewhere in the neighborhood of 8 amps at 60 hertz. So it's an 8 amp relay. It's good for switching AC lines. So then I went to another company that makes relays that are good for HF, VHF, and AC. And looked at the rating at AC and the rating at HF. In this case, it was 30 megahertz. They have 60 cycle rating and a 30 megahertz megacycle rating. The contacts were rated at 8 amps electrical current, 60 hertz. They rate at, generally speaking, half that much at HF, 30 megahertz. So does that mean that the relay contacts can handle 2,500 watts instead of 5,000? No, it doesn't, because again, it's I squared R. Now, it's so simple. Let's say the contacts are good for 4 amps at 30 megahertz. So 4 squared is 16 times 50 is 800 watts. It's a far cry from 3,200 watts. What's the big difference? It's current squared. 8 squared, if it were 8 amp contacts, would be 64 times 50 ohms would be 3,200 watts. But if it's half that much, the current is half that much, the power drops by to 1/4 because, again, the number is squared. So what I did was I built actually 2 boxes, and the first one I had it done, and I realized that some of the relays were in glass tubes were broken during the move to the new location. So I had to start the whole thing over again. The control box is the same, but the box that's outside, I trashed and started over again. So here's what I ended up with. And let me show you the outside of this thing first. It's going to mount these brackets, and at my tower there's a horizontal pipe that's 2 inches in diameter. A saddle goes over this, and I don't have it here. So saddle and the pipe in between, and the device will sit like this with the relay with the coax connectors facing down, and also the indicator lights will be facing down. And the reason for that is I wanted to make it watertight. So here's sort of the box with the lid on the top. It's heavy. It weighs 10, 12 pounds. So here's the box, and there are the relay contacts. Sorry, there are coax connectors, and I jammed in the pilot lamps after the fact, and it looked that way. It's sort of like an electrical panel, in that there's a bus bar, there's a conductor. In this case, it's a piece of braid. And then each of the relays contacts that they contact that braid, and it's a single pole, single throw. So it's just basically an on and off switch. These contacts are rated at 10 amps at HF, and so these relays are good for 5 kW. The only reason why I use these is because this is what I had on hand. I had these for years. I've used them. I use these relays in amplifier projects and all kinds of things. So here's what it looks like before I switch over to another camera. Those are the 5 relays, and the bus bar is a braid that runs across. Each of the contacts then is bridged to the coax connector. The reason why I did it this way is to keep the length of the conductor as short as I could. I wanted to try to get as little interaction as I could between one coax connector and another. And the answer to that is, the question is, did it work? And the answer is, I don't know. I'm going to try it. looked up now and measure the loss and see how good or bad that is. The measure the loss on commercial was about a half dB at 10 meters. So it makes it get close up to one of these areas because they're kind of interesting, waiting for the camera to focus, and it's not doing it very good. So there are the relay contacts, and the little door comes up, makes contact with each of those two flat surfaces. There's several in a vacuum. This gizmo on top is a bumper, and basically it's rubber, not just hot glued in place at the top of the tube. These really are vacuum tubes, and so they vacuum out the oxygen, and that allows them to handle a lot of current. Then this little piece of braid over here is the hot glue connector, and again, I wanted to make that as short as possible so there's little interaction between each of these contacts because they are close together. Each of because they are close together. So there's the bus bar that runs along one side, and then the contacts go out to the coax connectors. Coax connectors are I can show you those. They are Teflon silver plated, and they have a gold semiconductor, and they're good quality. The negative on the box is I tried to put 5 relays in the box, and it was probably too much. I probably should have stayed with 4. And then after the fact, after I had it done, I added the lights of the bottom of this thing in a not very pretty or elegant way. And what I figured was, occasionally I've been outside trying to figure out which coax line is and not been able to tell. So let's hook this to the NOVA, and to do that, I want to measure the loss. Is there such loss in this thing? And so I'm looking at it at 10 meters, which is about as high frequency as I go. And I want to measure it in kind of real situations. Get 100 feet coax and hook that up, and then read it with the NOVA, and I'll do that right after I get set up. So stand by. I'll be right back.
Okay, so the loss I'm looking at is half the return loss. That's on return, so it comes out. That's the return loss. In this case, it's 0.2 dB at 20 megahertz, 0.2223 at 29 megahertz, and 0.245 at 30 megahertz. So half of that, the loss is at 30 megahertz, about 0.15 dB. In other words, nothing. So I'm perfectly happy with the box and its gigantic relays. So there you have it, homebrew switch, relay switch, test switch, remote control switch that has virtually no insertion loss at HF.
Well, thanks for watching. I hope you enjoyed the video. I plan to get the switch installed at the bottom of the tower today. If you had not subscribed, please think about doing that. Give me a thumbs up or a thumb down. If you did a thumbs down and want to send a message to let me know why, I would appreciate getting that. 73 for now, Jim, W6LG.
What these have in common: PC pipe, spool of enameled wire, a couple pieces of angle aluminum, and some 5/8 dowels. We're going to use them to build an experimental loop platform. If you want to see that, stick around.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. So I had a choice today between watching Hallmark movies with my wife or doing a video that I wanted to do for a long time. You can pretty much guess which one what I'm going to do. Grab my notes. The most common comment that I get is, hey, can you tell me how many turns and what diameter and what size wire and what capacitor to make a loop for this for range? Or can you tell me where does the computer program like this? And I thought about that. I want to say that. I want to say that because you might not have the exact size wire, you might not have the exact diameter, you might have the same capacitors, it might be wound differently. But so what we're going to do today is sort of one of those teach a man to fish, and or no, give a man a fish and feed him for the day, teach him how to fish, and he'll make loops forever. Now, when I started making loops like this, I had all those same questions. Like how much does a wire make a difference? And, what capacitor should I use? And how many picofarads and all that? And where's it going to resonate? But today what we're going to do is we're going to build a platform very similar to what I started with 20 years ago, and with different things I learned over the years. But before we talk about that, here's all we're really going to need: it's a hacksaw and a drill. This project is going to use PVC pipe, okay, and it's going to use some dowels. All right, these are all common items. These are Home Depot, like half of each. You buy 4 of them, 2 each. No big deal there. And I'll give you all the measurements that I usually build this. But along with that, once it is built, we're going to wind it completely full of wire, and we're going to tell you how many turns we have in here. There's going to be 30 turns from using this dowel here. You'll have close-up pictures of all this stuff. The spacing in here is a quarter of an inch apart for each turn. So we know a few things. That if we make a loop bigger, it's going to pick up more signal, but it'll also resonate lower. If we had more turns, it's going to pick up a little more signal, it will also resonate lower. Different kinds of wire are not so. If we space those turns closer together, it's going to resonate lower because the intercapacitance between the capacitance that's added to the loop itself between each of these turns. So we know a bunch of sort of vague things, but we don't know exactly how many turns it takes. And I'm not going to say how many turns it takes for any given loop. But this video is going to be about how to build a very easy structure. The drill, the hacksaw, dowels, and yeah, I used a glue gun, but even that's not critical to building this. And none of the dimensions are critical. If you want to make these half apart, go ahead and do it. If you want to make them a quarter of an inch apart, fantastic. If you want to make this all have 30 turns, go for it. But using the techniques that we show here, you don't have to use any PVC glue. You won't have to nothing is going to be critical, but it's going to be a baseline starting point. So when we finish this loop, it'll be about 3 feet on a side, roughly 3 feet, so a little bit less than here. They'll probably be around 30 turns. I think that's what's on here. I counted on there's 30 turns. And it'll be a platform to build on. So we'll find out where it resonates, okay? And probably own some sort of shortwave receiver or general coverage receiver, and you're going to use that or your SDR receiver to find out where it resonates. So this is not going to be a build one exactly like this. This is going to be a build one and figure out how many turns you need, and if you decide, well, I'd like to make it go lower in frequency, I can make it bigger. If I want to make it go lower in frequency, I can add more capacitance. All kind of fundamental questions that I had when I was building this. So here we have just a plain dowel, okay? I think it's 10 inches long. I got a picture with the detail on that. And 2 foot pipe. And in the end, 1 inch, 25 millimeters from the end is a hole. Same diameter is where your dowel is. Oh, I don't have a base dowel. Okay, maybe you have 12.5 or 15 millimeter dowels. Whatever it is, not critical. So the dowel will go through here. That one I didn't finish the ends on. And this is going to form the basis. Again, you'll see all this stuff in the pictures. The basis of the loop. There'll be 4 of these arms. Okay. Now, typically, you might want to say, oh, I'll get one of those little X's. In fact, let me just grab one off the shelf here. If I have one, and I do. How's that professional? No cuts or anything there. So here's the easiest thing, right? 2 foot long piece of PVC pipe, and make a decision. 1 foot, 1 inch in, 2 inches in. I don't care what that is. Doesn't matter. Your dowel, after you cut your dowel using the hacksaw, again, my turns a 1/4 inch apart. You can use whatever's convenient for you. You can make this half the size. But what happens is when you push it through a hole in PVC pipe, you want to leave a little room on either side. So when you're winding, so you're going to essentially be winding this whole, and you have a side loop in there as well. Here's the problem: if you use an axle like this, the proper size one, of course, then you have to be very cognizant of where you put this in. Don't get much time with these, with PVC axes like this. You put in, and you say, well, I'll take the whole axe and then I'll drill out these holes later, and that can work too. But what I have is a little bit easier way to do that, and that is you take 2 pieces of angle. I'm using aluminum. They're I think it's 1 inch, so 25 millimeters on each face. This is probably an 1/8 inch thick. Doesn't matter. But those 2 pieces are crossed together like this. You find out if this is a foot long. You drill a hole at 6 inches. You drill another hole at 6 inches here. Okay. Then you cross them, and you put a screw in, and that holds them together. Okay. And it's going to move around a little bit with screws in there. So what you then is you put a couple of little grooves. You bolt it together. Make sure that it's a perfect 90 degrees. Okay. And then what you do is you cut a couple of notches here and here. And then you bolt together later, those notches will lock this thing out solid. We'll see that. I'll put it together here in a minute. So what that's going to allow you to do is to take your spreader and put hose clamps around it like this, and align this with arm going out that way, and align it with the arm coming towards you and one going towards me, so that all of your spreaders up here will all be in the same plane, and you want the thing together and have one spreader that's like that, and one spreader that's perfectly horizontal. Now when we go to one, it's a real pain in the butt, and it doesn't work well. So I'll show you this in a chapter. I'm going to take a quick break, bolt this together, and show you that a little bit more. Be right back. Okay, so once you've drilled your hole, this happens to be 12 inches. If you want to make it 14 inches or 18 inches, it doesn't matter. Just make both pieces the same size, find the center, and drill a hole straight through. Okay, just a simple hole for an 832 screw. And then you take both pieces, put it at 90 degrees, run it through, put your nut on the back. Let me move this up a little bit. Yeah. Put your nut on the back, and now you have a 90 degrees. Okay, this is really hard doing this backwards. So then what you can do is put a small groove here, a small groove here, small groove here, in here with a hacksaw, and this thing will lock together. This is only finger tight now, and it's locked together. So once you tighten this up with a wrench, you're fat city. Okay, it's not gonna move at all. So I'm just gonna leave that there, and let me grab a couple of the pipes, and let me zoom out just a little bit here. Hold on. Okay, so I'm assuming we built 4 of these. I'll show you a little bit more in pictures of what's going on here. But we built 4 of these. Okay, so one is obviously going to go. One's going to go in here with hose clamps. Okay, another one's going to go in here with hose clamps. And I'll show you. I'll do that in advice here. I'll take a shot from farther away. And I'll just show you the whole thing assembled. So I'll be back again. Okay, so we tightened this up, and now it's extremely strong. Okay, it doesn't move at all. So I'm going to drop it in vise. Take a couple of my hose clamps, and I'm going to take one of my spreader bars here, place it inside there, and I don't know if you can see the end of it, probably not. But okay, so there's the end, right? I'm going to have to make sure that this is 90 degrees on every one of my arms going out here. So the easy way to do that is just drop a couple of hose clamps, purely. Drop a couple of hose clamps on there, and tighten those up, making sure that this is at 90 degrees. Then add another one here, here, and here, and now you've got all 4 of them assemble, and you can actually see. You can line them up by eyeball. So you wouldn't be able to do that if you're using one of those PVCTs. That's a real pain in the ass to do. So this thing allows you to line it up any way you want. And again, I said like, this loop will come out. The perimeter of this loop will be about 3 feet or a little less than a meter on each side. But suppose that's way too big for you. So you cut this down. And now you would have only this much. So now your loop would be small. The thing here is, this is a way to build something. That is adaptable to anything that you want to do. When you get on building this and you say, it only resonated to 190 kilohertz, 200 kilohertz, something like that. Well, then how can I make that go higher or lower? Exactly. If you want to make it resonate all the way down at, say, 100 kilohertz, then what would you do? You'd make this a little bit bigger. Or maybe you would add a couple of turns. So this is not exactly how to do it. This is a platform for you to experiment with. And by building one of these, you get a feel for how many turns, how long the wire is going to be needed to be. This one's going to take about 300 feet of wire. I'm using number 22. You can use number 24. You can use 18. Just remember, as you get the higher size you go, the more stress is going to put on these components. So let me build this whole thing, and I'll be back in another shot here. Stand by. Okay, we're back at the device again, and I'm going to try to do this. I'll show you a call, and then maybe see the rest of this not so boring. Here's our first one. We'll just place our hose clamps on here. Okay. Okay, I just tighten it up a way because I want to make sure that I can adjust this. There's one. So now I have a platform that I can wind with wire, and here's another thing that's pretty cool. You might want to try. It's a couple of these things. These are the feet. You can put, that's why I left an intro here, so you can put them on and stand this on the floor and tune. I'll get a close-up shot of that. Okay, so now let's go to the feet here. Do a quick look here. Now it's not quite exactly right, but I have glued anything at all here. And you could also put another couple of inches of pipe underneath this to stand this loop off the ground by a foot or so if you wanted to. So there's one of our winding spreaders. Here's another one of the spreaders. I haven't really tweaked these in, but I will before I take everything else off. So, move back here. So there it is, a loop that stands by itself. We're going to wind this next. Let's look a little close up here. Okay, notice how there's one groove here, and another groove that comes on the other side. And it's on, there's 15 here and 15 here. Hot glued in the center. The other one, I hadn't hot glued yet. But the dowel fits in there. You can see that it isn't caught there. Again, really care that these are spaced. It's nice that they're spaced evenly, but if you only had 12 or 10 turns, you'd still be able to use this process 100% to be able to figure out, where this loop landed. And if it landed when we wind this, where this loop is going to land frequency-wise. So even if it was you can always say, oh, well, that's easy. I'll just build another one of these. Okay, only it's going to be a foot longer. Or it may be 6 inches shorter because this is too big. Maybe this is too big for where you want to place it. Maybe you want to place it on a workbench somewhere. Alright? So now really comes the hardest of all is winding this. Take a little bit of patience to do that. But when you're done, you have a fantastic platform here. I'm going to wind it with this roll of number 20 wire. I'm going to mount on this dowel on the other side of the room so that makes it easy to unroll. And put it in a device here. Hopefully the camera angle will be good enough for you to see. I'll line the whole thing while I'm on the air here, or while I'm live, but that will be boring as hell, so I'll speed it up. Anyway, let me get the last stuff set up, and we're ready to go here in about a minute. We're mounted on the wall here. I have just a piece of threaded on, so that's going to be how we pull the wire off. The loop is over there, ready to go, so let me set up for that. Okay, we're going to start off with one pick point, and I'm going to tie off. We're going to leave a tail of a couple feet, because we're going to need that. And let me put the camera on here and start winding. Our house is on a mount, but we'll give it a shot. Okay, I don't know if you can see that or not, but we're starting the wind process at 135, so you track how long it takes to do it. Here goes. That's one turn. Two turns. everything went okay, you will begin here, right there, and you will end there. And everything will be in line. So that means you haven't missed anything. Here's a gap in the middle. Okay, there's a gap right here. Okay, I'm going to take a quick break here. And we'll come back, put some feet on things on our temp ends there, put our tune capacitor on it, find out where this thing resonates. And then we'll tune it from there. Okay, here's the loop. Got its feet. It's all wound up. And I'm using a little handy little test capacitor here. 2 sections of 365 picofarads. So hopefully 720 to 750 when it's closed, and about 15 picofarads, 10 picofarads when it's open. And you can see I have it. The wire coming from this side of the loop goes to there and to there. So this is the lowest frequency and highest frequency using this capacitor that this loop is going to resonate in. So I just tested it. Let's turn it on. It's 660 kilohertz. Shoot, I'm not using the right hand here. Sorry about that. Okay, that's all they open. So it barely resonates at 660 using the 350 picofarad capacitor all the way open. So let's go down to say 200 kilohertz. We're down at 200 kilohertz now. This is gonna be hard. I might want to put this on a tripod. But before we put it on a tripod, let me just show you one thing here. The loop ends up being, we'll hook to one side there. Alright, it ends up being 34 inches. And what's that? 86 centimeters. Anybody over there across the pond? Hello, folks. That's the diameter, perimeter. So 4 times that. And 30 feet, that times 4 times the amount of turns, which is 30, gives you the amount of water that's in this particular loop. Alright, I'm going to put this back on tripod so you guys don't have a vomit during this test, so stay by. Alright guys, you're going to have to take my word for it. I'm going to play the capacitor now and find out where this resonates at the bottom of the band. This switch is in both sections, can you see that? No, you can't. Alright, anyway, let's see if we can, remember the top was 660 kilohertz, and with a single capacitor here, let's see where it goes. Okay, now down to 200, let's go 250. Okay, you're not going to hear stations, you're going to hear noise and here, so let's tune this. Alright, I'm not connected either. This is just proximity, right? The loop's here, this is here. There's no connection. So it's throwing a pretty big signal over there. Alright, but with one section, it goes down to about 250. Go back to 200. And I'm going to turn on the second section of this capacitor. So now we'll have total capacitance of 700 picofarads. Okay, so let's see what resonates at 200 now. Okay, there's 200 now in trouble. Let's go 180. Okay. Again, you can hear. Oh, I had to turn the gain up. I don't even have this. I don't even have the VR gain. Okay, so you can see peak quite sharply there, 180 kilohertz. Go to 160. Get close to the capacity range. Okay, so it's down to 160. 150 gain? That's as low as I can go with this radio, 150. Yep, so almost at the end. So it'll resonate down to 140 kilohertz. So, what do we know so far? I'm not going to write all this out, but you still could have a pencil and paper and do this. Quarter inch, let me focus here. Okay, so quarter inch spacing on the turns, 30 turns, 34 inches in diameter or on each side, on each left test first. So figure out how much more that is, and then figure out, I'll be giving the numbers that I get in our actual testing here. Let me turn that down. Last time I did a video with that thing was so way too loud. Now I'm going to start removing turns, and I'll do the top and the bottom of the band again. So a study would be really nice, because I don't want to keep down this stuff down. I'm going to take off 2 turns from each side. So what was our bottom again? Our bottom is 150 and 660. So that's 4 times the frequency range. All right, to put you on pause, I'm going to take off 2 turns from each side. I'll show a little bit of that. Okay, I'm going to pull off 2 turns. Oh, by the way, it took 15 minutes to wind this coil. So if you're willing to put in that much time to wind it, you do, it'll be good. So I'm pulling off this turn here. Right, so I'm going to take 2 turns off. So 1 more here. Okay, so let's cut this. Alright. And what I usually do is just make a loop around there and 1 knot in that 20 to tie it off. Okay, there it is. Alright, I'm going to do the other turn and I'll be right back. Okay, we're back again. You can see that I've taken off 2 here and 2 turns here. It'd be better to do this symmetrically. If you only want to take off 2 turns solo instead of 4, you would just take off 1 turn this side, 1 turn this side. So I'm going to go up to camera now, excuse me, the radio now. And let's see where this thing, how far it goes. Let's start off with the top of the band. Let's see what kind of difference that made. We'll see what 660.
Flight from New York City. I don't care if you're leaving from Newark or Champaign.
It keeps quite nicely right there.
That's almost as far as
pretty
you
long.
can go.
Okay, you can see, I'm not even connected. Look at the difference. Okay, so let's go to 710. 710. Okay, 710 is in New York. Okay, well, we made it past 710. And let's try 740. Oh, jeez, I thought it was 730. I caught by the 2 police. Okay, well, then up tops out, we get everything. Okay, so let's go down to the bottom of the band. I am recording this now. So 30 turns from 104 kilohertz up to 660. This is 26 turns, and this makes it up to 730 kilohertz. Let's see where the bottom is now. Let's go back to 200, and we'll put this all in here, and find out if it resonates to 200. Yep, repeat there. 160, probably not gonna make it. Ooh, it just makes it to 160. So 2 turns off, 4 turns off. Next turn gives us 160 to 730 kilohertz. All right, so we're making our way up the band here. Let me get 2 more turns off, and we'll get another set of numbers. All right, so we're down to 2 more turns off each side. Oh, that's didn't hold very good. Oh, okay, that's good enough for now because we're gonna pull more turns off anyway. So that goes right here. Okay, so now there's 4 turns off of each side. So we're down to 22 zeros. Let's go to the high end of the band. We know it's going to be above 730 from our chart here. Let's go here. Let's go up 800 to start off with. Okay. Are you on a radio? You're not on a radio. Okay. Okay, so 800 is fine. How about 880? No. How about 850? No. 830? Alright, that's weird. 800 then. Okay, yeah, that's right up. 820, 820 maybe? Yeah. Okay. So 22 turns gets us up to 830. 830 kilohertz. I think we're going to start gaining a little bit more on the high end here as we start taking turns off. Let's go down to the bottom. Let's start off at 200 kilohertz. 200, enter. And let's see if it resonates on the lowest 200 kilohertz. Yep, so 200. Before we were at 160, so let's put 180 here. Okay, just makes it to 180. I'm going to record that, and I'll be back. I'll take 2 more turns off. Alright, so we're at 18 turns now, and we're going to go up to the top end of the bin. We're going to start at 900 kilohertz. Hey, boys, it might be 900 kilohertz. It resonates at 900 now. We last lift of K Crusaders, it was 830. Okay, so 910 maybe. Wow, huge signal there. Okay, let's see, 940. Nope. 920. Okay, 920 is the high end from 830. So 920. Writing this down with 18 turns. Now, I'm not doing this. I'm not doing this for my health. I'm doing this so that you can see that if you build big, you can make it smaller. If it's too small, you can easily start on one squares and continue mining. But this is like a. Remember those 51 hits to the from Radio Shack? You know, it's an experimental platform. So maybe if it's 2 feet long and you had a place to put a loop that big, you get to the resonate at kilohertz without any problem. So, okay, right, back to test at hand. 18 turns at 920 kilohertz. Let's go to 200 and 6 resonates there. Okay, here we go. The tune. Woo. Doesn't look like it. Let's try 250. It does. There's 250. 200. Oh, just barely makes it to 200 now. So now we're instead of 180, we're at 200 and 920. Alright, it's going to start making a bigger difference as we go now because there's only 18 turns. We're going to go down to 14 turns, and this should move things quite a bit because the percentage of turns we're taking off is much greater. The other question I was just getting something I asked, well, how do I hook this up to the radio itself? I don't have a, I can't do it by proximity. Well, there's an external, oh Jesus, that was nice, huh? There's an external connection on the radio, just like you would be for any microwave receiver or SDR or whatever it is you're dealing with, and we can put a single turn on here. Okay, what I'll do now, let's turn around this loop. Okay, let me pull it back down here a little bit. Put one turn around the center of this loop, and we'll couple that into the radio. So we're no longer going to be doing this by proximity. We're going to couple it into the radio with one turn. So be right back. We've now put a single yellow turn of wire just so you can see it. To show you how uncritical this is, add 2 pieces of wire together to make this. But it goes all around the perimeter, one turn. That's plenty of coupling. You might want more, you might want less. If you want more coupling, you can add another turn. No big deal. Just add the turn. Or if you want less coupling, you can just couple between 3 legs instead of 4. It's all to you. Anyway, it still resonates at 200 kilohertz. Okay, we're down to 14 turns. You can see how far in we are at the edge of the loop. Still using our sync. Now we have, you can see that, yeah. We're coupled directly through the input on the Sony radio here. So, started off at 200 kilohertz. Let's see how low this antenna goes, what perimeter is. Let's zoom in on the radio a little bit more. How's that? Okay. Alright, so, wait, is that up? Oh, I'm getting it. Okay, let's go. It doesn't make it to 200 anymore. How about 250? Yep. 250 kilohertz is right at the bottom of the range. So now let's go up to, let's say 1 megacycle. Alright, let's tune up there and see what happens. Okay, so definitely resonates at 1 megahertz. Let's go 1050 out of York. Okay, I'm off resonance now, obviously. Look at that. Okay, so there's no problem. Try 1080 local here in Connecticut. Turn the gain back down. Turn that down a little bit. Okay, so it makes up to 1090, 1100. Let's see. And this barely makes it to 1100. So I think you get the gist of that. I'm wondering if I should do one more. If I do one more set of turns, last time we were at 920, now we're at 1080. If I do another set of turns, it's going to bring us up probably to 1300, something like that. It's going to bring that bottom end up. Now, I want to show one other thing here. Let's go down to 200. What do we have here? Forgot. 250? Let's see. Yeah, barely, it barely does 850. All the capacitor and everything goes up. I'm going to grab a 960 picofarad fixed capacitor. Why 960? For no reason? No, I happen to have 500,000 of these things. Well, not 500,000. But I'm going to put that in here in parallel. Oh, resonance is on, right? So let's go down to 150 kilohertz now. No, doesn't make it 150. We'll go to 200. So it doesn't make it 200 kilohertz now, and if you take that fix out, you can go all the way back up to the 1080 that we were at before. So don't be afraid to put the switch fixed ones. If you want to go from, say, 250 down to up to 1080, you just do the capacitor, the variable. If you want to get it down to 200 kilohertz, actually it's lower than that, 180. Oh, lost my. Yeah, I'm being sloppy here. 180 and probably 170. Yep, 170. So now with the addition of the one capacitor, try different values. You know if this is 750 picofarad, and where we started off with, that adding another 900 or so, we're going to take it way below. So with a full set of turns, this variable capacitor, and this guy right here, this will probably take you down to roughly 100 kilohertz. So perfectly usable for the long wave bands. If you use more capacitors, you get down even lower. The tuning range capacitor is going to be very limited when you put in a fixed capacitance. So, alright, I'm going to do one more, move two more turns, and I'm going to finish up here. Okay, we're back. This is the last one. We're down to 12 turns. I had to go ahead and take off pretty much. So, start off at 200 kilohertz. Again, not to make that, we know that. So let's try 300 kilohertz. And 3. Okay, so the bottom is 330 kilohertz right now. So with 12 turns, it's 330K. Let's go about to 1360. And I'm turning my up. Which I have to pass around. Yeah. No signal. This is going to that. To scale. Alright, so now 1410 in the local. Oh, what's that noise? I don't know where that comes from. But it resonates 1410. How about 1500? About 1500. Okay, barely makes it 1520. So with 12 turns on the loop, we can make it to from 330 to 1520. So if I take it off 4 turns instead of 2, we would went up to the very top of the right-hand, no question at all. So, I guess what I'm going to do now is put this away, maybe review some of the stuff that we learned, and hopefully somebody will make one of these loops or something like it and make a comment. Because really would be nice to know that somebody out there had some success using a very similar experiment that I have. So I just want it, and we sign out. Okay, that's it. What did we learn today? Besides the whistle, compound of number 22 wire. We learned that we can assemble without the use of PVC cement, without using any fancy tools. Just a few hole clamps and a couple pieces of PVC, and these spreaders, we can build an external blue platform from which we can derive the frequency, the resonant frequency, high and low, based on whatever tuning capacitor we happen to have. Now this one is 750 picofarads with both sections combined. This one is 1500. So with that one, and this was remote control. I used to have this remotely out in the woods. A little flex bearing in here that someone made for me. Anyway, with this, we've got to go. So we learned that with this very easy to build platform, there's no reason in the world to go, not sure how the right amount of turns. It's very simple to do. And like I said, I started doing this 20 years ago when computer programs weren't so good. There wasn't much out there. There were no programs like honey turns and spacing and all that. And even if you find one, chances are it'll get close. But with this, you can build it to whatever frequency you want. Shorten these up. Make only this long, maybe a foot long instead of 2 feet long, and you'll have a much more compact loop. I have it up here on the table, but if you wanted to, you could add 6 inches or so on the bottom of each one of these PVC feet, and have it very, very comfortably at normal waist level to tune the capacitor. So let's see. With this loop being 33 inches, 34 inches outside, and 700 picofarad, 750 picofarad capacitance, and 30 turns, resonant frequency went from 140 up to 260. Minimum to maximum capacitance on this tuning capacitor. You should build a jig like this if you're ever going to experiment. It's really convenient and easy to hold and everything. 26 turns out as 160 to 730 kilohertz. 22 turns out as 180 to 830 kilohertz. 18 turns out as 200 kilohertz to 920. 14 turns out as 250 to 1080. And 13 turns out as 330 up to 1520. I think if you took 2 more turns off, you would probably make it up to 1700. Another thing that's cool about this is, don't take 2 more turns off, take 4 more turns off. Get it to resonate at 2 megahertz. Take 6 more turns off and get it to resonate in 75 meter band. There's so many possibilities. Anyway, I just want to thank everybody who is out there supporting by subscribing to this channel. I'm at 975 right now, so I need like 25 more people subscribe to my goal of 1,000. Plenty more videos are on the whiteboard over there to do. Not all loose, but there's a lot of really weird stuff, like non-line of sight, LED communications, cloud bounce. That's one that I want to do for a long time. I had an 8-color transmitter on the air with a pickle barrel using a loading coil of 20 pounds, no 22 wire. I've got some stuff I want to do on that. Anyway, there's a ton of stuff more coming in. Please subscribe, help me get to 1,000 mark, and thank you everyone who's been out there. 73 W1 fell left from behind Big Blue, saying 73 guys. See you later. I'm out.
And today we look at a family of Simpsons. No, not that cartoon family on TV, but a family of Simpson analog volt-ohm milliammeters, namely the Simpson Model 260. The Simpson Model 260 is arguably probably the most popular kind of industry standard of analog volt-ohm milliammeters, at least here in the US. There have been several variants of Simpson 260 produced over the years. Let's take a brief look at some of the larger differences between the various series of 260s and what to look out for if you want to pick one to buy bed. We'll talk a little bit about why I like having one or two on bed at all time. I find them very, very handy. So let's get started. Simpson introduced the Model 260 in the 1930s and is still producing a few variants of 260 today, meaning that the basic design of the Simpson 260 has been in production for well over 80 years. Now, essentially, all of these 260s will have a lot of things in common. You know, the zero-ohm adjustment putt, the multi-function switch to select the various ranges, and then the polarity and AC-DC control switch. Just about all of them have the most common paired jack down here. Your common and positive jack is used for just about all of the measurements shape, with the exception of some of the higher ranges or some special features. So, for example, there's a special 1-volt range that you would use a separate jack for. You switch it to this range, use the 1-volt jack inside of the positive. On this one, it's over here. Okay, and you use the 10-volt scale in that case. In this case, you use 2.5-volt scale. So, little minor differences. Similarly, on the highest voltage ranges, in this one, you can go up to 500 volts through these jacks, 1,000 volts handled by the 1,000-volt jack here. On Series 8, there's a 250-volt maximum through these jacks, and separate jacks for 100 and 1,000 volts. So, just about all of them include an output jack here on the 6 series, here on the 8 series. Okay, but this is just another AC measurement range that has a DC or series capacitor in series with the meter circuit. This will allow you to do is to measure the AC volt component that's sitting on top of a large DC bias. And this would be common in like audio amplifiers, especially those that are using like bridge drive or maybe a 2-back or something like that. So when you measure AC voltage through the common terminal here, you see the DC component as well. So using the output jack will remove that DC component so you only look this way, because that's what the output jack is. Otherwise, the features are really pretty common, especially from Series 2 pretty much all the way up through today's models of Series 8 through 9. So the Series 1 from 1930 was the original design. It used a D-cell and a 3-volt battery, which many people converted into using a pair of AA in series. It used some pin jacks to connect the probes. It didn't have any calibration capability to it. It relied on the meter movement, resistance value, and full-scale current value, and some resistors to set its accuracy. It looked a little bit different than the rest of the units they have here, but it is the unit that's traditional. Series 2, like the unit I have here, was produced in the 40s and 50s. And you can kind of know that it looked very similar to the other series in terms of bevel design and the kind of thing here. You can look at the Series 2s that it doesn't, generally doesn't have, or at least the early ones did say 260 on the meter face, and they use, again, pin jacks for the probe, not the familiar banana plugs. So really it's only the Series 1 and Series 2 that uses these pin jacks. Now, a brief look at the schematic also indicates what I mentioned earlier, that there's no calibration adjustments. It relied on the fact that the meter movement was precise 50 microamp full-scale meter movement that had exactly 2,000 ohms of winding resistance to it. And it used that fact along with precision resistors, 1% resistors or better, to set the voltage current scales as well as measuring resistance. During the production of Series 2 as well as any of the other series, there were often incremental improvements or changes needed in design, and oftentimes be referred to as a Series and A. Like this case, there was a Series 2, and there was a Series 2A. And the big difference between the Series 2 and the 2A was that 2 had a 1,000 ohm per volt sensitivity for the AC voltage ranges. The 2A went 5,000 ohms per volt like the rest of the series. But then the series come along with the Series 3. Now, like the Series 2, got rid of the 3-volt battery, used a D-cell and 4 triple batteries. It's all the first series to have indicator. It says Series 3 right here on the meter face. The biggest and most important difference in my mind is that went away from using a pin jack for the probes to more common banana jacks. The Series 3 was produced from the late 50s and through about the mid-60s or so. They see a lot of these around. There's a bit of an important change in the schematic when we went to the Series 3. You can take a look at here. Note that the meter movement is still a 50 microwatt full-scale meter movement, but the series resistance is 1800 ohms approximate. So I don't know, maybe they're having trouble kind of meeting both of the requirements. So what they did is they used a meter that had a slightly lower meter resistance and included a series potentiometer that could be calibrated so that the overall resistance of the meter in series hot was calibrated 5,000 ohms. Once had that calibrated 5,000 ohms, that along with the other resistors would make calibrated voltage and current scales. We're also added to trim out the AC voltage readings as well. Series 4 added one more change, which carried through all the way through into the meters we produce a day. The meter movement is actually a 48 microamp, or approximately 48 microamp full-scale meter, and again about 1,800 ohms. So there's still a series trimmer to dial in a calibrated 5,000 ohms to calibrate the meter based on precision resistor, but also there's a shunt resistor in parallel with the meter movement, and what that's designed to do is to shunt a little bit of current away, so that when you put a calibrated 50 microamp through, 2 microamps approximately go through this trimmer, and 48 would make full scale. So the combination of precision or adjustable shunt and an adjustable series value would allow you to get precise resistance in the meter movement at the 50 microamp full scale. This basic calibration method is eventually carried over through all the designs up through the Series 8 and 9. The series was used in the late 60s and through the 70s, early 70s. The Series 6, again, very popular, and that's all over the place. It was introduced in the 70s. All used the banana jacks. In the 6 series, they switched from using the AA and D series batteries to using D series battery and a 9-volt battery. And a more important change on the 6 series, to access the batteries, you no longer had to completely remove the back half of the like you had to do on Series 1 through 5. There's actually battery access to her. So here's the Series 6 example. I'll show you what I mean. Essentially, turn the mirror over and you see there's a split in housing right here. If we listen through up, you can see the source comes off, and the DC battery go here, the 9-volt battery go there, and the fuse access right here. So the 6 series and its variants was produced in the 70s and up through the early 80s. In the 1980s, the introduction of the Series 7. And the big change going from 6 to 7 is that the Pro connector went to a reverse dial net instead of a regular net jack, the Series 3 through 6. And this meant that it was actually harder to actually find pros to plug into the meters. And that same reverse NAT is used on the Series 8, which is still being produced today. So instead of being able to use ordinary NAT jacks for TCs, these would no longer work. You had to use these special reverse NAT plugs that would plug into the jacks. Because recess for D. And unfortunately, these are not very easy to find. In fact, I don't know if anybody else besides Simpson actually makes test leads with their reverse NAT on the far end. While researching this, I actually thought I'd get lucky, as I found M0ODZ makes this little test lead extender, which essentially a reverse NAT. You would plug a test lead into it, you plug a test lead in the other end, and test leads longer. It's like, great. I plug this into the meter. Okay, then I'm plugging my own NAT test leads. Problem solved, instead of having to spend a lot of money on Simpson test leads. The problem is that the Simpson test lead actually a little bit of spring type of connection to it, whereas the bananas have a hard cylinder, and you stick them in there, there's no positive contact with the reverse banana. So unfortunately, these M0ODZ test lead extenders don't solve the problem of having to find these reverse banana test leads. Anybody out there knows good sources of these without spending $50 at Simpson? Well, let me know. Now, the Series 8, which was produced in 2000, up through today, it's still brand new, also has the reverse banana connections, add a mirror scale to help use parallax. And there were a couple of differences in terms of the scales. And there's an off position switch here instead of us having the TC and single AC position. There's a couple rearrangements of some of the jack connectors. But other than that, the Series 7, Series 8, just about all of the series, there were units reduced that had suffix, like Series 2 and Series 2A, Series 4, Series 4M. Those suffixes had meaning. Again, the A, as mentioned earlier, is usually been Series update. Maybe a small change to a spec or an updated meter movement or something like that. The M stood for mirrored scale, and that held true all the way up through the 7M. Again, the Series 8 includes a mirror scale standard, so don't have the M on it. There was also a P suffix that included protection circuitry, and I think that was available from the 5 series on up, maybe a little bit earlier, that would actually really disconnect the meter movement that would overrange. There were a couple other series as well, but not as popular as the ones that you can see here. And I learned all this information from looking at this website here, just Simpson260.com. I'm not associated with the Simpson Instrument Company, but just a ton of information, everything you ever want to know about the Series 260, the variations of them, skins and manuals, schematics, things like that. Just a really great resource for the Simpson 260. If you're looking for one, here's my advice. I'd look for one of the ones from Series 3 through Series 6. Obviously, the later the better, because these are the ones that got banana jacks and commonly available batteries like the D and 9. D-cell batteries, AAAs, or D-cell battery and 9-volt. Particularly because of the D-cell and 9-volt and the battery access door, to me, the best one to look for is the Series 6. They're still going to be pretty old because they're produced in the 70s, but that actually's got its convention features. If you go later, the Series 7 or Series 8, you can get a newer meter. You got battery access door and even a mirror scale, but then you got these troublesome reverse banana connectors that you might have trouble finding for pros. So to me, almost the best one to look for is the Series 6, unless you've got a good source for those reverse banana pros. Note of the common problem to watch out for. The number one problem I've seen with these meters, and I've got a number of them over the years, and still a number of them now, is actually leaking batteries. People often leave a battery or batteries in the units, and sometimes years at a time, the batteries leak, and that can be really difficult to clean because of a lot of corrosion, and especially in the older phenolic PCBs. Once the battery has got into the layers of PCBs, it's virtually impossible to clean it out to remove any leakage paths that were result from that. That will really affect especially the higher voltage scales. So you won't be able to take a look at the meter, open it up, and see it was like battery leakage before you go pick one up. Another common problem was just having mirror movement, so they really overranged it or got physically damaged, something like that. That's something you can check out pretty easily. And the other one that can happen as well, you get a sticky meter, or as the meter moves up or the way and then maybe stops or gets stuck, and then it won't turn all the way. That's also stuff caused by dirt or debris inside the meter movement and stuff. And that can be carefully cleaned out. So if that's the problem, then it might be something you're burning, and then very carefully work on the cleaning out and whatever the use of the meter. A couple of final comments here. I like the analog volt-only meters because they're really great to help you watch for peaks or dips or trends when you're adjusting or tweaking a circuit. So it's a lot easier for me to watch a meter movement move up or down as opposed to watching some number movement down on a DMM, a digital multimeter. Even though I have a bar graph type of thing, the segments of that don't have the resolution that a meter movement has. So I really like analog volt-only meters for that reason. Another thing that I like about analog volt-only meters is they make you think. You have to think about what range you need to be on, because they're not all range. what jack do I need to use, depending on what load you're using, what voltage range you're using, or whatever it might be. You might have to pick different set of jacks to use, so you have to think about that. And you also think about what load is you're creating. Unlike VMM, which gives you like 10 megohm input impedance, the load presented by, especially the voltmeter in a VOM, is dependent on what scale you set. We'll go into that a little bit more in maybe a how to use a VOM video in the future. But you have to think about that, because the load may be just tens or hundreds of kilos that you're going to place in the circuit and how your circuit react to that. So you got to think about that. And to me, thinking, especially working like us, is always a good thing. So this kind of puts you more on your game, I think, using analog VOM. Another thing to remember is that the batteries are only needed in the VOM to measure resistance. So if you're going to use your DMM to measure resistance, you never have the battery in your VOM. The idea is always remove those batteries until, or if you're ever going to use them. Let's keep them out of it. I don't have any batteries in my 760 because I use the 260 generally to measure resistance. The only time I'll typically use that if I have a potentiometer or a trimmer that I suspect is at a dead spot end, I may throw a battery in VOM and then adjust the trimmer and just watch the analog movement, be sure I get a good clean change in resistance of the potentiometer. If I get little dropouts or things like that, I know the body's pretty deep into that. But then I've never put any batteries in my VOMs because I've got other tools for that. I hope you enjoyed this introduction to the 760 family and consider picking up what you find analog voltomilliammeters to use on your bench. I don't think you'll regret it. If you enjoyed the video, please give me a thumbs up. If you haven't subscribed to the channel already, please consider doing so. And if you want, you can ring the little bell that's sitting down below this video on the YouTube page, and that will alert you when I post a new video. And as always, thanks again for watching. See you next time.
Okay guys, made some changes. You want to see what they're all about? Stick around. Oh, that was a terrible intro.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. Well, I know what you're thinking, what the hell is he doing with that fancy shirt on? I want to thank everybody. We got over 1,000 subscribers. It was on Saturday or Sunday, so I was just tickled pink, but tickled blue, I guess. Anyway, this is about the last time you're going to see me in one of these is back to t-shirts. So, I wanted to thank everybody. Really kind of an exciting goal for me. This video is going to be part 2 of the Loop platform, experimental platform, and a bunch of questions. A big one that I got was, why didn't you short out onto the turns instead of making all the turns off like you did in the previous video? Yeah, that's a good question. It's fair enough. It does seem like a pretty easy way to go. Two things. One is that this loop was really sort of an experimental platform. If you want to short the turns out, go right ahead. If that's even that idea is coming into your mind, why don't you try it and see what happens. In my experience, what happens is the Q circuit goes down because of all that metal hanging off the sides. It's not contributing to the actual circuit. The second reason is that I have a much, second reason is it really wasn't to make that loop cover all this frequency band. It really was more about, hey, why don't you try this? This is an interesting experimental way to build a loop and get acquainted with what components are. And certainly today's video is going to be about how to take that same loop and make it cover from 140 kilohertz all the way up to just under 2 megahertz. And do that a couple of ways. I'm going to put a little PowerPoint presentation there so you guys can see this. What exactly it did and how it wired. This is something about 20 years ago when I was making these loops. I had people asking, well, you could still cover from a broadcast band up to 20 megahertz, so, and in a much smaller form factor, but in the larger loop, it doesn't really work that well. But in those days, I figured out a way how to put the windings in parallel and in series. So in series, you have a whole loop, and in parallel, you essentially have half the windings. And the range that we'll get with this is from 140 kilohertz to about 2 megahertz. And that's going to be with about 18 turns on that frame. The other question people ask, oh, hey, why don't you do this on the SDR? And that's a really good question, too. And the problem with SDR is when you're working in really close like this, the computer makes so much noise, it's just not worthwhile to try and sort out all the different noises. I have enough noise here in the shack, down in the lab here from various devices around. As much as I try to mitigate that, it's still quite a bit. So those were really the questions. I had a lot of comments. Well, thanks again. I really appreciate it. I'm going to change things up a little bit. I'll get a close-up of what I did in the PowerPoint slides that I either stick in here separately or just talk over later. Those will pretty much explain what's happening and why I did it. So anyway, I'll be back. Reset up. Thanks, Dan. I really appreciate it. Okay, so got the loop on the W bench. Back a little bit here. You notice that this is something that you might want to do yourself. It's 6-range extensions here. I haven't glued this yet. With these 6-range extensions, it gets the windings of the loop off the floor, or more off the floor, and it also helps with mulling and they seem to go out a little bit. But then both sides, just about 5 inches of space off the ground. Here's a close-up of. I hope it's focusing. I can't tell. Anyway, let me get a little bit of a close-up in on the tuning diagram, and I'll be right back. Okay, so one of the changes I made here in my little jig was to add a couple of switches. There's only one switch before, so maybe they're on it. This is one of the Russian capacitors. This section has 70 picofarads. This section is also about 750 picofarads. So in position with all these switches out of the circuit, you have just one section of this able to loop, and that's how we get up to 2 megahertz. With this one closed, we now have both sections of this capacitor in, so now we're up from about 10 to 750 picofarads. This is a 500, I don't know if you can do this. This is a 500 picofarad capacitor, and this is a 960 picofarad capacitor. Not any specific values, it just happens to be ones that I have in stock. And so with position 3, we switch that one in, you have 750 here and 500, and that gets you down right away in frequency. And then you also, when you switch this one in, it gets you down to 2,100 some picofarads. And your tuning range, because you only have 750 picofarads of tuning range, it doesn't move that much, it only moves the 100 kilohertz or so. But between all three of these and the secret weapon, which is coming out, you can continuous coverage from 140 kilohertz all the way up to 2 megahertz. So let's drop the loop back down to 4, and let's take a look at that. Okay, so now we're looking at the PNS switch here, the parallel series switch. Like I said, there's a PowerPoint coming up, so I'll be able to talk about that a little bit more. Very easy to wind. Instead of winding the entire loop in one piece, you wind one half and wind another half. That gives you 4 wires to deal with. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 turns per side. So when you put in series, you eventually get 18 turns, and whatever the capacitance value that you can come up with here determine where to resonate. But then you can also let these turns in parallel, which gives you something like 4 turns. So you can see how you have double the coverage just by putting the series parallel switch in. Now, if I can get this down to 140 kilohertz with only 9 turns, with the rest of the turns on 9 turns on the side 18, when you get back up to 3 turns, and it was a big capacitor like this, you can get down to 60 kilohertz. And when you start doing this really low frequency like that, you're going to want to change the coupling loop a little bit. Let me just talk about the coupling loop. See if I can do this. The coupling loop, I kept it yellow just so it would be visible so people could see it. But it's now drilled through this bone here, or through this extender arm. One there, there, and all the way around. And it conveniently puts the coupling loop right in the middle of the field here of all these wires. So that's really a nice way to get it out of the way. And the other thing I did is I came off with the BNC connector. You probably want to get rid of as much extraneous wire as you possibly can. So this BNC now feeds the coax that goes off to the radio. So let's see. Let's hook up the capacitor. That's the other thing. When you're doing your experiment, the wires in this thing are strong enough to just hold the twin capacitor and switches in place. You can get a pretty good idea with this little setup here, this little jig that I built, of where this loop. The other thing is, later on, you could put an extension on this and mount two capacitor arrangement right to this, or mount it on the center of the loop, whatever you wanted. But for now, as this is not a finished product, a experimental platform, that's what we're going to do with Steamer. So I'm going to hook the Sony 22 now, and we'll take a look at how this tunes. Yeah, that's it. Let me do that. Okay, we're back. Or at least I am. I just wanted to show this switch. If you look inside here, it takes off parallel and series. All that's in there really is a double pole, double throw switch. Very, very simple. Either wire. I have the diagram. I'll put that up later. We'll go from there. So let's start off at the low end, which means that I'm going to have to engage all these switches. So that's already engaged actually. Okay, we'll do that now. And we'll be tuning here. Let's go down to 150 kilohertz. And now it's not tuning. Why not? Well, because I don't have it in series. A little bit. There's no signals there inside house noise, but you can hear it resonate when I do this. I'll make sure that this is. Okay, there we go. Okay, but this second camera is my son Matt's idea. He said, Dad, can't see what you're doing. So I experimented with the second camera. We know how it works out for you guys. So 150 kilohertz, and actually we'll do more than that. We got quite a bit left, so it'll go down to 130, 140 kilohertz. So let's go to the other end of the spectrum now. We'll shut all our switches. And you'll notice the signal on the way on the Mac cam over here. We'll go to 1500. And let's see. Alright, why? Something's been there. Again. Maybe not. Oh, I got put back in parallel. Get out that high. And let's put down to 1410. This is a local station, and let's see how much passes we need to get that to be. Okay. Let's go on 1080, another local. Okay, so that piece up. So we have around 1600 to down to 950 kilohertz. Okay. About 910. Yep, makes down to 910. So what I've done here is, let me turn that audio down. What I've done here is put these two windings in parallel. So not 9, but the two 9s in parallel equal roughly 4.5 to 5, maybe 6, because they're not bound right on top of each other, but you have doctors in parallel. So, and it's easy to see when I switch. Try to. Ready? Peaks out right here too, and if I switch to series, it drops right off, and I'm going to need a lot less capacitance to that. So let's try something 66. And if I will go down below 6 to 400 kilohertz, I can start bringing in some of the packet capacitance. Okay, so I'm going to go to 400 kilohertz. Okay, you can hear there's a noise in there, but well, with the full engage, you can't quite get there. So let's dump the extra 500 off. Okay, now we can get there. 20. Okay, I don't think we can get to 180 here. No, we can't. So let's bring in the 960 here. Doesn't? There. So again, this is an experimental platform. We turn it down. It's also an experimental video because I have the back panel over here. I'm really hoping this is going to work out because while I'm working over on this camera could be showing you what the end result is. Okay, I think that's it for a camera perspective. I'm going to go over to the computer now and bring some of the PowerPoint slides. Just going to talk over the top of them a little bit. Again, I really want to thank everybody for subscribing. Hit 1,000 was a goal.
I don't know what else to say. But here's a better look at this guy. Okay, 960 puff, 510 puff, and then the 265s. With them all in, you can go down to about 140 kilohertz. With them all out, you can go up about 2 megahertz, and that's with 9 turns per side. If you want to go higher, you take a couple turns off. If you want to go lower, you add a couple turns. Do it symmetrically though. Keep these wires as short as possible, come out a coupling loop. You can always put 2 turns in a coupling loop experiment with it. Well, anyway, and this is just in parallel with the loop, right? It's a series, parallel resonant circuit, and your one's resonating the circuit, and that feels so huge, it acts as the antenna bar. Right, that's all. I'm going to go over to the desktop now and show those other slides. Thanks again.
All right, here is some of the slides that produce the PowerPoint. One thing people did ask about was what are the dial tones, and here's everything that you really need to know. I was kind of hoping that people would come up with their own. Although this is very convenient. It's like a 5/8 dowel with quarter-inch spacings. 17 costs. It's really not 17, it's only 15. But if you want to make your 17 or 20 per side, you could do that too. It's all about being your own loop and way to experiment with it. Okay, so moving on to the series parallel tuning circuit. Right here, this capacitor is the assembly that showed you the switches on it. It's in parallel with these 2 sections. So this is section 1, loop section 2. And this is the beginning of loop section 1, and this is the end of loop section 1. This is the beginning of loop section 2, the end of loop section 2. It's just important that you don't change phasing here. This could just well say A or B. But just know that if you have phasing wrong, it will not resonate, it will not work. If you look at this really quick, you can see that the tuning capacitor is in parallel with this section. It's also in parallel with this section. Half the tuning capacitor is in parallel with this section here, and the other part of it goes to switch and it's in parallel with this section. In series, it's pretty straightforward as well. This tuning capacitor is in parallel with, well, it tries to go this way, there's no connection in this switch. And by the way, this is that double throw switch that I showed earlier. It's a full 12 switch. So again, this side of the capacitor comes down to this part of the coil, through coil, back up the switch, through the contacts of the switch, and a little tiny short wire, back up through the contacts of the switch, and in series with the other side. So pretty simple setup. You guys pause these and whatever stuff, whatever you want to do, but I just thought this was an interesting way to go about it. And this is the capacitor tuning unit. Reality is there's only 3 switches. That's the 4th one. This 4th one wired straight in, so that with all 3 of these switches open, you have this one just wired in straight, and you have minimum to 365 picofarads. You click in this one, now you have 750 to the minimum on capacitance. When you want to go lower frequency, you click in 510, and you still have these 2 in, and they're tuning, and then you click in 960. By doing that, you can get everything you need to get from 140 all the way up to 2 megahertz. Thanks again, everybody, for watching. I really appreciate it. If you haven't subscribed, please do that. And again, thanks to everybody out there who got to the 1,000 mark. Sorry, this is W1 from the computer station here.
When it comes to receiving signals, what's the difference between this inductor and this inductor? They're both 500 microhenries. Stick around.
W1 fell left.
Hey everybody, my name is Paul, W1DLF. This is kind of going to be a video about answering some questions that I got here. What's the difference between this and this? There's a way to do question. I want to clear up something real quick. This is the camera business. Oh, jeez. My sons are debating, came up with the idea for the Mac cam. I have 3 boys, Dan, Matt, and Steve, and this technology piece allows me to keep in contact with them all the time. And quite they give me their asset for that ham, the Mac cam, because I mistakenly thought it was Matt that said it with Dan. One guy just wanted to call it a ham cam, another guy just wanted to change it out of slicky and call it a spiral ham cam. Anyway, another texted me because they know I'm doing this video right now. Anyway, jeez. Anyway, I'm gonna go this way. Anyway, we're gonna address a bunch of questions here. So, but from now on, this is gonna be the ham cam. Okay, so I'm gonna put it over here. Okay. So, what I have here in my hand, we're gonna do a lot close of this, and we're gonna employ ham cam for part of it. Is 500 and something microhenry inductor? So the question came up, well, if this loop is, I can't use a small inductor like this in a resonant parallel circuit and use it as an antenna. And that's a good question, right? I was interesting. And the reason why I can't is, you probably can't even see this thing in my hand. Look at the area here. Let's say this is a meter square. This is about 1 square meter area. This is half a square of, this is about a quarter of an inch, so that's 6 millimeters, 36 millimeters square, I guess. No, that's not right. But it's very small. It's outside the head of a pencil, but they're both 500 microhenries plus or minus. So we're gonna take a look at the series parallel arrangement on this and compare it to this. But to answer the first question, there's just a big difference. I'll get a little bit more clarity. And I want to shout out to Julia, G4UED. Hope I got that right. He was out there during PowerPoint presentation part that the mouse wasn't there, and it was confused. He did that with the physics academy. What I was saying, I got that ironed out. So let's take a look at the individual loops here. We're going to call this side 1, and this one's side 2, and then that'll sort of section 1, section 2, and that'll carry over later. So let's get the LCR meter out here, and we'll close up on that, and I'll show you what happens when we put these 2 sections of coil in series and in parallel, and we'll talk a little bit about that. Let me set the camera up.
Okay, here we are on the bench. Group that bench with the ham hand. And the LCR meter. If you get one of these, it's extremely useful. Okay, so what do we measure? We're going to measure this. We're going to go to L. And here's that tiny little inductor with roughly the same amount of inductance as the receiving oil. So about a half inch, 3/16, 3/8 of an inch in diameter. Let's just measure the inductance real quick.
and it's all half a millihenry or 514 microhenries. So it ends up being very close in inductance to the loop, and we're going to go over there and measure each section of the loop. But look at the size of this thing. It's the size of a pencil eraser, so it doesn't really have any area. So can you make a resonant circuit from a constant long inductor like this? Absolutely. Will it perform for receiving? Absolutely not. And now in that ferrite core here, mixed Q in the 20s and the mid hundreds. So let's take a look at one more thing real quick, and the rest of the numbers now. The tuning variable, show you how we arrive at the high and low frequency at this loop over. So we want to move this little off the side here. And this time we want to go capacitance. And if you remember, put all the switches in and turn our main tune capacitor all the way up. We have roughly 2,150 picofarads of capacitance. So we'll have to remember that 2,150 picofarads of capacitance there, fully meshed, and it goes into the formula for as a frequency after. Now we turn all the additional capacitance out, and the residual is 11 picofarads. So that's going to determine the high frequency of where this loop resonates. So I'm going to pull away this to the other camera and show you the loop inductances. You'll be able to see then that what's really on in there along with PowerPoint afterwards. So I'm going to sign out here for a second and then pick up on the other camera. Okay, so we're back at the loop here now, and again the parallel series capacitor, and I'm going to use the ham cam over there to record the inductance of each one of these windings. Now this is what we're going to refer to as section 1, section 2, and this is N1 and N2. So remember about the phasing when you put in series, just like batteries. You put them in backwards, you get no voltage. You put them in parallel, twice the current, put in series, twice the voltage. Anyway, just remember that polarity has sensitivity here. So let's look at this section 1. I cleaned off a little bit of the enamel so that we get a look at what section 1 is, and let's see what it says on the. I suppose let me see, are we connected? Yes. Okay. So there's section 1. Section 1 shows about 200 micrometers. Let's still look at these two wires. So it's coil right here. Let me grab these. Take a look at that. It should be really close to being named. It might be slightly different. It's 204 microhenries. I should prove that we're on that coil because if I squeeze these together, it starts to go up. If I squeeze these together, it doesn't make any difference. So we're on that coil. So now you would say, two of those series, the 200s roughly, let's call that 200 for purposes, you should have 400 microhenries. Well, that's not really true. The truth of the matter is, the four-letter inductance is the square of the turns ratio. So what's the turns ratio here? Well, we have another one, so it's twice as much. So it's 2 to 1. So 2 to 1 is a 4 times increase in inductance. So when I connect up to these two wires, which are ones that go to a variable capacitor over there, we should see 4 times the inductance. Let's take a look at that. Okay, clearly it's not 4 times the inductance. Why not? Well, because these are not one continuous coil. They're not coupled tightly together. But if it was, twice as many turns would bring you to around 800 microhenries. From 200 times 4, because there's 2 sets, it would give you 100 microhenries. So now let's see how to pass this. We put these two in parallel. Okay, so let's remember these numbers. 580 microhenries in series and 147 in parallel. We're going to take those numbers over to the computer bench there and look at the resonance formula on a calculator and see where this really lands. So in order to make this have resonate at the lowest possible frequency, which we determine to be around 104 kilohertz by testing it with the radio, we're going to have to take the 586 microhenries and 2,100 microfarad here, and we'll enter this into the formula. The other half of this equation is the highest we were able to go was around 2 kilohertz, 2 megahertz. So in that case, we're going to take 147 microhenries, and we're going to take all the capacitance out of this, and it ended up being something like 10 or 11 picofarad. We're going to take those values, put them into the resonant frequency calculator, and see what our determination was. To what's the real world. And variance from what should be the real world is going to be because of the minuscule amounts of capacitance that are between each turn. Because an inductor isn't really just an inductor. It has inductance, it has some series resistance, which is due to wire size and all, it has capacitance between turns. So anyway, let's go over to the bench, choose the computer, and see how these numbers line up and look rather than frequency calculator. Okay, we got back over the computer now. I've seen this slide before. There's a couple others I want to touch on here real quick. I changed this up a little bit for you guys because I wasn't clear last time, but now you know that this is loop section 1, loop section 2 for the parallel configuration, and these are the ends, end number 1 and number 2, and they have to be connected the way you see here. Like I said in the other piece of video, the phasing is important. Otherwise, you'll track this one from this one, and you'll have 0 inductance, and it won't work. So, same over here. I just repeat those the numbers so you could copy this, the phasing information and switching information should you want to do that. Same thing, we'll look at that just a couple minutes ago, we'll pass that out. And here's basically what this thing is. It's an inductor or coil and a capacitor in parallel. Same with the notch filter that we built a couple weeks ago. But in this case, the capacitor is relatively small and the inductor has physically really large area to it. Right? I guess 3 feet or a meter roughly square. So this is a large physical area here and it picks up a lot of signal. But let me lead you down to, but remember this, remember that's the basic configuration of what we made. Now, we do have a 1-turn coupling loop over here for when you want to drive a radio, but purely what we made was a parallel resonant circuit with proximity to radio. That's all that's in this circuit. And here's what it looks like in more simplistic terms. The 2 inductors, the section 1 and section 2 are in parallel. I had drawn the switches for the sake of clarity, and when I switch the button, the switch to series, that's what it looked like itself there, with the 2 series. So this ends up being the 146 microhenries total, and this ends up being the 585 or so microhenry total. That's that. Let me just go over to this page. This is a great place, goodcalculators.com. It's a really cool calculator here, and I like to use these. And here's a resonant circuit. Same thing, now you're looking at it, and you're going to see the resonant frequency here. So let's put a couple of our values in here. Let's start off with the first value of was it 10? No, yeah, picofarads, something like that. We'll start with millihenries, microhenries here. 146 microhenries. Let's put that in. 146, and we got to change this to microhenries. And then picofarads, we're going to put in 10. I called 11 because I think that's really where it was. It's in picofarads already, and calculate. Okay, well, with that much, with 11 picofarads in there from the capacitor, look far off we are. We're almost at 4 megahertz. Well, the reason why we're at 4 megahertz is all the distributed capacitance. So let's put in 20 picofarads instead. And let's put 30. Okay, so it's probably somewhere in the neighborhood of 30 picofarads of distributed capacitance. The 10 that we're adding with our tunable capacitor, and the 30 others to get stuff for to take the circuit resonate. We talked about the interlining capacitance before and what it really is. Okay, so let's take the other end of the spectrum. The other end of the spectrum with the inductors series, we had about 586 microhenries, and the capacitance total was 2150, I believe, picofarads. And our before we hit calculate, I remember our resonant frequency was roughly 140 kilohertz to calculate here, measured with Sony radio. So come out be close, 142 kilohertz. So let's say you wound that coil to 1,000 millihenries instead of the 585. Let's say you fill it the whole coil out like we had originally. That would drop you down to roughly 100 kilohertz. I'm not sure what the value would be. I didn't measure at those extremes. But you could sort of figure out when things cover. But basically, with the let's see, 86 microhenries here, you can go cover from 140 kilohertz all the way up to 2 megahertz. So that's what this is. It's an experiment. Not meant to be a build exactly like this, because a lot of guys have been asking, well, how many turns would it get here or there? Well, could sort of do it here on this page and figure that out. But more importantly, I wanted to make something that people could duplicate, was not critical, and show how to arrive at a good working antenna. So if you have any questions, you can leave them in the comments section. Again, I appreciate everybody who has subscribed in the past and the new subscribers. It's up to 1,035 now. I really appreciate that. Like you see, go back to parts number 2 and part 1 and a lot of other weird videos on stuff that you wouldn't call mainstream. But take a look anyway. Thanks a lot. 73, this is the window left from behind the microphone now. Sign off.
In my previous one, we looked at the various families of the Simpson 260. I recommended against getting one of the later versions of the Series 7 and Series 8 like this one because these two included a reverse banana or a probe raise, and it was difficult to find probes for this. I recommend looking for a Series 6. In that video, I thought I found a solution using the probe extenders from Pomona, but found they didn't engage well enough to make it work. One of the viewers said, well, maybe it's just the extra plastic that's in this adapter that's causing the problem, and then I'll just remove that. So I fell off one of the red in here and gave that a shot. And certainly makes it engaged deeper, but notice there's a little bit of lightness, so it's not making a good solid contact to the plug on the inside. So almost there, but still not quite. But yeah, another viewer recommended another probe adapter, so I'm going to add on here. And the nice thing is that this little raised shoulder here is solid to fit in the hole, and that works. But it still engages the pin, but there's still a little bit of lightness, so it's going to be a little bit intermittent connection. So again, close, but no cigar. Now, the problem with this adapter is hidden just a little bit loose, is that the pin in the meter is not exactly like a typical banana plug. The NAP plug got some kind of loose springs on the side that give a good solid connection when put into a jack. And the pins that are inside the meter are really just from 4mm straight pin, so they don't have this little string engagement on it. That turns out we can solve this main problem pretty easily. So you take the adapter and squeeze it ever so slightly with a pair of pliers. Not too much, doesn't take to distort that cylinder just enough to make a good interference fit to the pin inside the meter. And now you got a good sub connection, and you can ask style plug or jumper and use the 260 Series 7 or Series 8. Well, the word of caution though is that obviously by doing this, we've kind of passed the safety features and the safety reasons why these plugs were used in the first place. So my advice is, if you're going to do this, use this only for the relatively low voltage application. If you're going to be looking at doing any high voltage work, 250 volt scale, 500, 1000 volt scale, etc. I wouldn't recommend using these because they may not provide all the safety protection that the proper leads would using this jack. Another viewer on a previous video pointed out the probe adapter makes a set of test leads that have the reverse snap plug on. And they fit the Series 7 and Series 8 cents a meter, and they're less than $20, so it's less than half the price of the original equipment Simpson leads. So with the availability of some nice leads from ProMaster, or the ability to use some of these banana test lead extenders with a little bit of economic persuasion to tighten them up, you've got some really nice options for using the 260 Series 7, Series 8, and not have to steer away from the meters because of the reverse snap leads. Thanks again to the viewers of the suggestions, that was really super, and thanks again as always for watching. We'll see you next time.
Loop. If you want to see why, stick around.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. Well, here's that loop that we've been messing around with, and I think this is going to be it. This is going to be part number 4 of the loop series. I think you guys are going to get in probably a little sick of this. So, but again, in the comments, I have a couple people ask whether or not you could take this kind of loop or Android with it. And many years ago when I was building loops, sort of somewhat commercially and selling them, I did make a number of them. Not physically as big as this. But still, in different formats. Okay, spiderweb type or cobweb spiderweb type, diamonds, rectangles, whatever people want at the time. But this, of course, is not something that you would sell to somebody. This is your experimental platform. So how did I figure out how to get this work on short way? Well, I cut some of the PVC pipe off. Remember, this being an experimental system, you can make the lengths of these pipes as much as you want. And in this case, I cut off exactly 10 inches. Not 11 and not 9, but exactly 10. And the reason I did that is because I can cut as much off any leg that I want, or make them longer, or make them smaller. That's the platform that I'm playing around with here. Could get about the 2 megahertz, not quite 2 megahertz on loop before. But in the smaller configuration, we can go from about 700 kilohertz or so all the way up to 12.5 megahertz. So what I'm going to do is I'm going to put the camera in here and show you a couple of things, how I did that. I'll make a few notes. Not a few notes, I'll mention how I did it. And then maybe leave the name, I'll just resonate all the way up to 12.5, almost 13, maybe a little over 13 megahertz. I didn't really go to the extremes. I just play around with it a little bit until I got satisfied. Now, again, this is smaller, right? Now, there's nothing magic about it. If you made it a little bit smaller, you maybe get to go higher for switch. You're going to give up something. You have less turns, less aperture, so at those low frequencies, like in broadcast band, you're going to give up some signal strength. But the reality is, most of the time in broadcast band, we're not dealing with super weak signals that are right at noise for. Usually, the ambient noise, at least in this noisy area I'm in here in this house, if I were to put this out in woods from 400 feet out to the woods, I'd definitely go probably up for 50, and I may have several different loops. But for purposes of this, my goal here was to get us to move into the shortwave bands as high as I can go, and I'll show you some of the things you have to really be careful of. The other thing is just the yellow wire. I'm moving that yellow so it can be stick out a little bit there. The yellow wire is the coupling wire, and it's smaller as well. You get down to, what do we have here? 6 turns. 6 turns are going to do exactly the same thing. They're going to do one position and parallel in the other position. But when you get that small number of turns, this coupling loop, if it's put right in the middle over here, is going to limit the high end. So, anyway, let me take camera over because some men say, oh, nothing is purple somehow. Even with lag stitch, it could just go on a desktop somewhere. And it's easy, much easier to handle. So let me zoom in on this. I'm going to set up a what is it, FR 700 DC2, and we'll turn on the band a little bit. Again, you hear it peak up, but it might just be noise. There's quite a few shortwave stations that I heard earlier. So let's do that. I'll be back in a couple minutes after I set up. Okay, we're back. So the first thing you're going to notice is, or the first thing I'm going to show you is, that I mounted a BNC connector here, and if you follow it up, that's for the coupling loop. Okay, and coupling loop is only, I don't know, 10 inches or so arbitrary. If originally, to figure out what I needed for coupling, I just threw a couple of clip leads around the 2 spreaders here, and found out that the big coupling loop was way too big. So anyway, this makes it much more stable, not having a coupling loop flopping around and whatnot. So nice BNC, and here the coupling loop. Again, this is the same pieces of aluminum. If I was going to make this permanent and use a 9 inch or 2 picture, they don't need to be that big. They're only big because the loop is originally 3 feet outside. And let me just grab the measuring tape here, and let's see if we do this all total blowing this out. Okay, so now inside of 33 inches, it's only 19.5 inches on the side. Significantly less wires being used here. Also, there are only 3 total turns. 1, 2, and the top one comes back again. So 3 turns on each side. Let's just throw this over on the LCR meter real quick, and then we'll see what the inductance is of those 2 sections. Okay, let's run the series right now. We only have 21 microhenries instead of 585 microhenries. And then when the loops are in parallel, you have this most square the turns ratio rule. So that's the 2 coils in parallel, and that's the 2 coils in series. Other thing you're going to notice is when you're dealing in frequencies up to, say, 13, 14 megahertz, you can't have a whole bunch of extra wire hanging around. You can't get the same liberties that you did when you were dealing with only in the hundreds of kilohertz. 100 kilohertz is a few picofarads straight capacitance. Doesn't really mean anything. It's not really a problem. So you'll notice over here in 1 second. It came up and drill a hole here. Before, what I was doing was taking wire and wrapping it around 2 or 3 times to hold it in place. But now you can't do that. You have to minimize every bit of capacitance, straight capacitance that you can. So these 2 coils that are in series are significantly shorter than they were. Again, you can't take a lot of liberties when you want to go high in frequency like this. So again, you have the series parallel switch, nothing changed. Even these leads have a lot to do with it. So using that same device, same capacitor arrangement here, and that 10 picofarads is going to be the limit factor on how high in frequency we can go. So I'm going to put this on the phone now and set up the other radio, and I'll be back in a few seconds. After I do that, we'll just take a run through. I'm going to try to keep this one a little shorter than normal because you guys have seen this all before. But this is just to prove out that you can make it go up in frequency into the shortwave bands and still work pretty well. Okay, we're back, and I just threw all the switches here to see how it gets to resonate. That's 707 kilohertz. It does not make it to the bottom of the A broadcast band. You do a little bit more fiddling, maybe add 1 turn, but you're only going to get, in this case, maybe 20-to-1 ratio. So we turn this up, and we'll turn around, we'll enter in the capacitors, and we'll pick it up. Okay, so that's pretty close to the bottom. So 750 kilohertz is about as far as this could be low. So let's go up to let's jump up to 160. Actually, the provided device on 1963. Okay, so let's pump up some of the extra capacitance here. I put it in parallel. Okay, sounds about right. There we go, something was wrong. Okay, it's very, very sharp here. That's what it is. I'm going to tune it just a bit here so you can see how fast it stuff is. Yeah, that's a little stronger. Okay, on resonance. Okay, on resonance. And I'm going to off resonance again. And we'll completely go on. Let's make the next jump up to 75 meters. Okay, I don't hear much. Then again, we're not resonant here, so I don't hear anything. So let's start doing it. Oh, we have to, now we're going to switch from the series to parallel. It's not 72. Oh. I just remember something. On the center of this radio, this goes up to 2 megahertz. So if I switch this over to the other input, now things will be a lot more clear. There's some stuff like that. Okay, there's the resonance, there it's up. You can see it peak up. That's like 20 over on that little, that tiny little. It's not a noise here too. Let's see if I can find that. Okay, that's off resonance. There's resonance. So let's jump up to 6 megahertz, or 5, because there's some pretty short wave stations in there. Go back to AM. Comes like a mid-one there. Volume band. Okay, so that's who's resonant. And we'll tune it up. It's very, very touchy as you go higher frequency. And then as you go up to 12 megahertz, it'll be easier. It's not nearly as sharp. So every time you're still coming, retune. Well, let's try BBB at 5 megahertz. Let's try it on 10 real quick. Anything. So we're a little sharp from there. We'll go down to 40. Well. You can definitely see how it keeps up. Now I'm hitting this time, it's just going right out from east and west. Probably worst fractions for these four frequencies right now. But that's how I have that first up, so that's the way it's good to see the actual influence. Okay, so I'm everything now. Let's go to, here's just for 9 favorite.
That's why Jar Bell with so harshly. Religious belief of crop is a because they believe takes a human life.
So that's true. That's probably easy.
So just like you must follow my brains, get to the end of all figure ahead.
Let's go, you're probably just going to hear noise here, but now we're at 11.6. Hear that. Oh, there's actually a fish in there. Take out right here. Oh, we're fixing roll 5. And 12. Not like that. Let's see if we can keep up on that at 1 megahertz. 1 megahertz. 5. Yep. 12 to 13. Not much there to noise, but at least makes it 13 megahertz. Try 13.4. 13.4 keeps up. 13 tops it up a bit. Yep, that's it. 13.4 or so. That's the end of it. Alright, anyway, like I said, just a real short one here to show you that by changing the size of the loop, which of course this is a experimental system. You do that anytime you want. And I'll review it here a little bit. Wires as short as possible. Series and parallel and loop. Look at it. I banged into it before I messed up. About 3 turns per side. If you make smaller, you could go higher frequency. I made a very small one, about 30 megahertz. The problem was that it didn't go all the way down to broadcast. So what we did, we went from 700 kHz up to 13.5, 14. So it's like a 20-to-1 ratio with the 3 switching capacitors. Hey, somebody else built one of these things. or at least experience making loop. Here, let's see. It's only high as I need. Kind of get in the shoes, I guess. Anyway, that's it from W1VLF. If you enjoyed seeing this, which I can't find any reason why you would have, go back and look at part 3, part 2, part 1, where we actually built this loop, and a couple of baseline for all the rest of the testing that we did. 73, please subscribe if you enjoyed it. This is W1VLF, and Lab signing off. I know it doesn't much, but I'm really excited about this at the time. If you like listening to the broadcast band and having good balls, you should too. You want to find out what it is? Stick around.
W1VLF.
Hey everybody, my name is Paul, W1VLF, and welcome back to the lab. I had a conversation with Yusuf, the Airspot guy, designer and software, and I asked if it would be okay to do a YouTube dual loop video on YouTube. And he said absolutely, and I really thank him for that. That's in the works. But I was thinking about the past 4 videos on the open airframe loop, and I said it seems appropriate right now to do a video on a fairway loop, and just kind of get a feel for what compromises are. Is there a bandwidth compromise? Is there a queue compromise? Is there a signal strength compromise? Is it easier to handle? I think that's pretty much self-explanatory. Can it at the same level of signal as something that's let's say it was roughly a QA meter. Okay, so they're like 33 or 30. It was barely that. Here's the and in 2 dimensions, right? Oh, sorry. Somehow I thought that was one. Anyway, it was huge. This is about 16 inches long overall. You'll remember this form factor from the WWV antennas. So what's inside this magic PC2 here? Now watch. 2 of these rods. These are the ones that I use for the WWV antenna. I think they were $4 a piece to cover Russia. And I put a link to those exact same rods in PC. Oh, if you don't use these rods, they're bigger or smaller. Some of the things are going to change here that I can't guarantee. Oh, it's always the same way. When you don't duplicate one part exactly as, say, an has an arc on antenna, things are going to change. So, but this is more of a user antenna than an experimental platform. Although I can see the next one, this one covers 540 kilohertz up to very a chip that I built over here. Now, I think the few more turns and the same capacitor, we can get this to probably go down to 150 kilohertz, and we can probably get this to go a little bit higher in the HF. But for now, I'm going to concentrate on just how this is made and where to tune 540 kilohertz up to about 3.9 or 4 somewhere in there. And again, remember, when you're going to see this thing on like a little turning arrangement I made, kind of a cheesy turning arrangement. But when you get up to 3-4 megahertz, can't take a lot of things for granted. Like, these links are starting to get important because they're not very passes between. So if I was to hold this for a specific area, I would better get past it or relatively close to this. Minimize these leads. And again, also minimize the leads at the bottom of this. So give you some both shots this after. We're going to also play the cam. Well, again, what's inside this aid? 2 of these ferrite rods. Okay, a couple of collect and gas. And when I put it there, I also put standing glue in and I pour the caps on, and the standing glue holds it in place. If you want to see that, you should go back and look at the WVE series. It might be number 1 or 2, but that shows you exactly how to make it. And this is really the platform for this whole series of videos we're going to do here. By comparison, these ferrite rods out here, like brain white last. By comparison, here's your standard kind uses this handle ferrite rod. So about, I would say, half long, roughly. Take these over to the LCR mirror, look at that. That mirror look at the of this. And this is going to be significantly lower. The reason for that is I make up the other half of the parallel circuit using additional capacitance to get down to 540 kilohertz. If you make it so that way you need 365 kilohertz, get down to 560 kilohertz, they're never going to be able to get to 160. I'm going to do a lot of this now with this, and then I'm going to do some time when 160 and 75 are open. So either that's going to be included in this video, or it's going to be a separate chunk. Anyway, we'll go through some of the, what is it? By the way, this, I'll give the number of turns here after I look at what I so, and I'll be able to count by the, this is lit wire, okay? This is, number 46 is the optimum wire size for the broadcast band, and I think this is 175 number 46 wires. I think this high is 660 wires. I don't know what I have to do. I ride this experimentally. I'm going to buy these. They're on eBay. This is 16 inches long, or the overall antenna is 16 inches long, and I'll pay how many turns. And coupler glue is 4 turns, right? But the yellow wire, the big long yellow wire running around from the other town, the air car. But there's a real advantage to this clip. It's easy. You put it out, you easily build them out to swivel this all over this. Anyway, enough your jabber. I'm going to go over this here. We'll take a look at a couple of the typical antennas to see what ducts they are. Go through with this, and then I'm going to try and hook this up. And I kind of shift the rotary scheme. We'll look at a bunch of the broadcast stations and see just what kind of balls this has on all those stations. Alright, so please stop the camera and I will be back. Okay, we're over at the LCI meter. Right here. And let's take a typical ferrite rod that came off that stereo. And let's see what the dot is. And it's usually around 240, 150 microhenries, something like that. Alright, this will end up being 280 microhenries. Just the fake rod down to the bottom of the broadcast band. If you go online like you see 280 plus 365 will get down around 540 somewhere like that kilohertz. There's another one. These are all just out of junk box. And let's see, 234 microhenries. Let's do a 500. Let's look at here. Let's put more ferrite right. You have to do is the field generator around here. All you have to do is more ferrite here. Okay, so we know that we need less index than that. So here's the antenna with the exciter coil here, and here's the actual lines. Again, I'll get the number of turns if you want to do this. Kind of follow along, follow bumps and ball fuel. Alright, so let's look at this. This is going to be significantly less. Alright, so this is only 82 microhenry, which means if we put 365 picofarads in parallel with this antenna, it's not going to go anywhere near the bottom of the broadcast beam. So we're going to need 750 plus, we're going to need 1200 picofarads. But that's not a problem with that little test jig. Swinging in fixed capacitances, especially used silver makers, is a great way to extend the range of any antenna. Alright, let's go back over on the bench and kind of set things up a little bit. I have two cameras, the ham cam on the radio, and you can see what I'm doing and what I'm doing on the actual antenna itself. Okay, we're over at device. The Sony 2010 is here, ham cam's here, and here's our little dowel. If you take a T-fitting, a standard T-fitting, you cut it in half, okay, it leaves you with a little U-shape, and conveniently will just snap on and can now use as a makeshift rotor, if you will. So, alright. So we're going to do a bunch of different stations top, bottom of the band, and maybe tonight I'll come back and do the 160 and 75 meters. Or I'll just show you the nice floor here. The signals on 75 and 160 last night were fantastic using this little antenna. Okay, and although these were Broadway signals and ones on 160 and 75 are pretty much skywave, it still has a small effect because, you know, come down to the top instead of perpendicular. The next, if I was going to build it as something that's permanent, I would put a hilting mechanism on this. So I could build it to income wave, like this, that could offer good models, except for anything maybe constantly changing. So anyway, I'm going to hook the turbo capacitor here, and I'm going to start off at 540 kilohertz. Let me hook this up and hook the coax. It's a little convenient to do this because this capacitor is such a big item. Right? It's not like a small little capacitor that could put on top very easily. If you want to do this a permanent installation, you can see right, it's going to be tuning it off. We could probably put a little bottom up here with the tuning capacitor itself. So let me turn everything off. All the capacitors are switching off position. So at 540 kilohertz. And I'm going to start the ham cam now. Alright, recordings. Oh, I turned it back to the antenna. I have bad connection here on the free fix. Yeah. Alright, let's see. Let me get the connection right. Nope. The external antenna jack here is pretty bad. Okay, hopefully that will hold. Okay, so there we are at 540. Let's see where that's coming from. That's north, so it should be peaking in that direction. Whoops. Okay, so there's null right there. Goes right into the noise. Goes out of what? Like 708. 560. You see space that this is tested. 560 is Boston, so that should be almost in an L right now. So now we're on 560. Are we recording? Yep, yeah, okay, good. So go up the rate, so take past the way. Okay, tune to resonance. Okay, we're in null. Close to half of that thing. Yeah. We're going to do this. And. That's not going. Yeah. Whoops. Off past that channel. Let's go up to 660 in New York. Tune that in. Yeah. But that's like 8 miles away. 0, we'll try from now. And closer. Get into the noise. Get up. Here, you make a difference. So, a little obvious work. Let's hope to set 10 another one in New York. Okay, we're going to have to tune it faster. Okay, so some of these are not going to know as perfect as other ones because the grain come from and all the different metal and everything that's here, that's stuff we impressed. So let's just sum it up. Here, find some parallel. Okay. And we have to take some passes and knobs with my higher frequency. Okay. Okay. So I put right into the noise. 10 is in here as well. Ready that. Now I'm going to have to take some of my extra capacitance out. Okay. That's pretty weak. So think about how big that other antenna was. Just grab something. Right now will should be your attitude, but sir, I'll let it 30 feet away. So if you want to do some portable, this is really a cool way to go. Alright, let's see, 10 is local. Okay, no signal. Wait. Go higher frequency, so it takes capacitance out. Clear everywhere. 1080? Oh, 10 megahertz. It's very hard to see the screen from here. 1080. Oh. Well, that's about full scale there, right? So let's see how often we can do it. So into the noise, excuse me, some noise in there. Let's try 1320, which is another local strong letter. Can we pick up now? Okay, so it's a 9. So when you talk about nulls, you have to remember that any piece of wire that's not part of this inductor, it's filled in nulls. Because if you see signal, if I put me down here, alright, all goes right by that. Another thing, I have lots of going on here. So let's try 1360, another local. done in that direction, so I know. Yeah, no, this is so great now. About 1410. You can see it keeps out really sharp. Okay, so we're going to go 1 or 2. You can see the skywave in there too because the is changing. And then go back to huge difference. Try 1500. Got to take a lot more capacitance out. Okay. Don't really worry but gets it ready to the noise. Let's see, 1700 is a sideways signal. So, that's nice. It's not lost focus there. Alright, so again, I think you're a little curious when you're trying to do all this in a small area. This is like a 5 kilowatt about maybe away. Something in that direction. This is mostly side. We'll just up to say 160, we'll go to 1900. You'll just at least hear the noise rise on that scope. Of course, there's over there. But you can hear the noise. And we'll go up to 3330. To now. The band is not so good up to hand either. That's CHU. Yeah, right. I'm going to go up to you see if there's anything around. Now we can hear the least come up. Alright, well I guess that's all in there right there. So, sorry to make that so long and tedious, but that's basically we have covered 2.5 gigahertz down to 540 plus. Thanks for watching and putting through all that. So, anyway, it'll be 1 volt out. Okay, a couple final thoughts besides apologies for messing up last part of the video, the camera phone over and everything. On these radios, they have a good fair filter for fairy loop that's inside. Well, you go to the external antenna. I'm not expecting you to put another fairy right there. They're cutting a long wire or something like that. So the fairy, there's not that much gain in the circuitry when you go with the external antenna. So if the signals are not strong enough, you can always put a preamp after this antenna. But I think we proved that it's got really good rejection from the side, and I'll prove there's an easy way to rotate this. And some optimization can be a really nice, medium frequency antenna that you would actually take into the field if you wanted, or use home on top of my desktop. Anyway, thanks for hanging out in here, talking space. If you found anything interesting here, please subscribe, and I don't know, tell your friends. Tell your friends, maybe they want to see somebody mess up like that. Anyway, I think what the next I'll do on this is a wide board turns on it, see if we can dedicate to the long wave band. We'll probably shoot for 150 up to 400. So that's going to be the next video in this series. So I'll take some close-up shots in this week to exactly how you turn the around there. Because I can't really count, but I'll blow it up on my computer and go with that. Anyway, thanks a lot, guys. I really appreciate everybody watching, and please subscribe. And this is M0ODZ signing off. Okay, I'll do a quick overview here, real quick, with the probably put the amount of turns and everything on the screen. So, ENC, clone loop, and master resonance loop. 7-3, do M0ODZ out.
I've done some doing PR, time doing telemetry, measure things like length of class, or measure the velocity factor, or even higher competes. And I use little pulse generators, either a sim generator like this over here, or these little homebrew fast-stitch pulse generators like the one I made here, was a little super from my friend E5GC. And along with your digital scope, you can get like this and use that to determine these errors parameters. But it turns out, you can actually do that with just scope without using any of these alerts, and it's really simple. Let's take a look at it. Here's our super simple PR setup. You got a digital scope, and it's slightly 9 volt battery, a couple of leads, and a resistor, 50 to 100 ohms value is not very, but you just want to be relatively close to the pins of the line you're trying to measure. A little T, you connect to your little 9 volt battery, and then to the unknown length of line on the measure. And this point is set up so it be either a single shot or normal trigger, and just third level set up above baseline. And so you cut the other to the 9 volt battery. That creates a set voltage change, and propagates down the line, reflects off the end, then come back. You can actually see the injection to line and the flagging come back, and use that to measure your parameters. The basic setup of the scope is your DC coupling input, and if you're using a battery, 1 or 2 volts of provision so that your full 9 volts will appear on the screen, and then set position down the bottom set, you start off down here, ground, and then your 9 volt kind of goes up. Your horizontal settings really depend a lot on the length of the line you're trying to measure, so you have to adjust that accordingly, but typically maybe 5 nanoseconds division for the shortest line, a couple of feet long, up to maybe 50 or 100 nanoseconds of provision, maybe longer, really long, so maybe up to 100 feet or more. And the short position, you want to set that 10% being kind of close to the left edge of the display, so you can see the waveform play out toward the end. And the triggering, as I mentioned, you will trigger obviously on the later by using DC coupled, rising edge about the threshold, and again, normal or single move, say you only get a trace when the electric transitions. So here's the simple stuff. We've got our BNC right here, connecting to scopes, so one of them information pins are connected to this one, or go to an unknown line. And here I just have a little BNC to complete it after, and when I connect to the line better, the other one connect to the resistor, and we're simply going to do action like that, and generate our waveforms. So I've got some coax connected at the far end of my BNC here, and all I need to do is hit it, and for the pull out, you can columns appear. The idea in normal trigger would just do it to get a nice clean waveform. So you've got that clean waveform, you can count divisions, you can have cursors in your scope, or you've got cursors, you can actually position those cursors so they're about the same point of waveform, on the initial step and the reflective step. One that you can then measure the LT, in this case, delta T is 57.8 nanoseconds, that's the delta between those two cursors. And once you've got LT, you can then go ahead and compute the length of that line. And so start off, you need to know speed of light, and for measuring the length of line, it's really just need feet meters depending on preference. So speed of light in feet per nanosecond is 0.9836 feet per nanosecond, or 0.2980 meters per nanosecond. Then we also have the velocity factor for the particular cable or coax traditional line, whatever that we're measuring. Typical glass coax runs from 86% like RG58 up to 85% or even sometimes a bit faster for some other types of coax. And we can even take a look at using the measuring twisted pair like Ethernet cable. I'll show you that here in a moment. You can usually look up the velocity factor online just by the model number of the cable, or you can estimate it, or if you got a chunk of cable, you can physically measure and then back calculate to what the velocity factor is. I've got a video on that as well. I'll link them in this video down below. I'll express these values in distance per nanosecond for a reason, because most cases you're measuring delta t in nanoseconds, so this makes it convenient. Okay, so take that delta t in nanoseconds. Remember that's the round trip time. So I take this signal, go down the line, the end, and then come back to the code. So it's really twice the delay through the cable. Again, we get that value in nanoseconds, and simply multiply it by our speed, in feet per meter per nanosecond, multiplied by the velocity factor. So it's 66%, that would be 0.66. And because the round trip divided by 2, and that quite simply give me the length of the line. So we measure a delta t 37.8 nanoseconds, and we multiply that by, let's say, 0.9836. That's the feet per nanosecond. Multiplied by 0.66, which is the velocity factor of the RG58, and divide that by 2, I get 15.5 feet, and measured about just a little over 15 feet on this cable, so that's pretty darn close. I've got the Cat 5 Ethernet cable that I used to wire my house here about 10-12 years ago. I got unknown link left the box. Also, I didn't measure to figure out how much cable I got left in here. Of course, the class I was measuring here played with a nest of VNC clip leads. I'm just going to measure the blue twisted barrier, so just connect up to those two leads right there. We'll hit with the 9-volt step. There we go. Looks like I don't have the time skips up long enough to see the other cable, so it's funny how much division will in. Let's slow down. We're right here at 100 nanoseconds division. I can actually see that return cut. So let's move our cursor here to in the solid bit. Quick turn back. And it's the T 265.8 nanoseconds. Okay, let's take our 265.8 nanoseconds and multiply by compute in meter again, 0.9836. And then I've seen velocity factors for twisted cable lights, even the cable ranging from about 64% to 74%. So let's go midway between those two, 0.69 or 69%, and then divide by 2. That tells me I got just a little over 9 feet of this Cat 5V cable. And it turned out the cable actually had a couple feet remaining distance left, and you can see from this end I've got 90 feet and back to the box, so just a little over 90 feet. One more of an experiment. I wasn't sure this was going to work right. This is an old school heavy-duty screwdriver or just typical zipper. I thought that because this is all neatly wound that it must line this would work. It turns out it actually works just like that. So sweet. Looks like a disc a little bit of resolution here. Let's have another one. And let's position our cursor here kind of in about 10 times that rising edge. Go grab the other edge here. And we'd see my delta is 62 nanoseconds. I've done some experiments and found that the velocity factor of this cord like this is typically pretty slow, about 6% or so. But if we run those numbers, I'm getting a length of about 18.5 feet. That's all about right. I'm kind of slow a little bit, that's fair, but that looks usable. You have noticed that both the Ethernet cable and this cable here, that step is because first, and that's because I didn't change the value of the resistor. I'm using a 15 resistor. So because the impedance of these other lines was larger, I wasn't getting as much of a voltage division during that initial surge. So I could increase that resistor value to 100 ohms and these two sets equal, but it really is necessary in order to make amendments. In my case, I use the same measure the length of just a single conductor, like I got a spool wire here. The answer accordingly is now. In order to detect torque, you need to essentially have pair conductors, not a single copper. And that pair conductor needs to have a constant physical relationship to establish a constant distributed capacitance leading to it also constant impedance. So same with coax, we've got still line and shield, and that establishes the impedance of that line with the twisted pair wire that we're using here. Twisted between the wires keeps a constant distance between those wires and a constant coupling between the wires to get relative constant impedance, let's say south on ohms. And even like the zip wire that we're using here, the physical relationship between two conductors is consistent. So we need to leave that pair conductor by all work to stay single conductor of the spool. So I hope you enjoyed this video. Really super simple and quick way of doing the video measurement through a digital scope on 9-volt battery pair clip leads on a resistor. The notes that I've shown in this video will be available in the link down below. I'll also link in a couple of the previous videos on the theory of TR so you can get a little more background on that. If you like the video, give me a thumbs up. If you haven't subscribed to the channel already, please consider doing so. And thanks as always for watching. See you next time.
Hi, I'm Jim W6LG, your YouTube Elmer with Happy Basic. Welcome to my radio room here in Auckland, California. We're putting a video on station branding. I went to the X-Class exam questions and found one that had that dealt with station branding. Seemed like he's dead, but I found a question that covered that, and that was the one I could find. So here's the question, and I'll read 4 answers. It's group EOA, I think is what this is. Safety. RF radiation hazards materials, and grounding. The first question, EOA 01. And here's the question. What is the primary function of external earth connection or ground rod? What's the primary function of an external earth connection or ground rod? 4 answers are A. Reduce perceived noise. B. Lightning protection. C. Reduce current flow between pieces of equipment. Or D. Reduce RFI, radio frequency interference, telephones and home entertainment systems. So which of those is the primary function of external earth connection or ground rod? We'll find out the answer right after this in my crossed. Interdiction in it says, what is the primary function of an external earth connection or ground rod? And 4 answers are receive noise, light protection, current flow between equipment boxes, and interference, telephones, home entertainment. And the correct answer is B, lighting protection. The primary function of an external ground rod, they say, is lighting protection. I think that'd be a misunderstood question. Look at the definition of primary. It means the first or most important. So the most important function, according to the question, an external earth connection or ground rod is lighting protection. No, not even close. And the reason for that is a ground rod isn't going to protect you from lighting. Lighting's going to strike, and it's going to go pretty much where it wants to go. You can direct some of it away from equipment, but lighting, a ground rod is not going to form a dome over your equipment and protect it from lightning strikes. It's not called lighting protection. You can divert some of the massive current voltage to the ground away from equipment, but it's not going to protect from lightning strikes. So that either receive noise, see air from between pieces of equipment. In a way that's true, there's an RF current, and it's a bit of a maybe closest answer that's correct. Reduce our interference to telephones. The ground's not going to do that. The idea here is to perpetuate for it is that you drive outside, run around while you're 6, and you drive the equipment, and any RF from the radio room is going to capture and take the ground, RF is going to flow into the ground. The primary function of a ground rod is electricity. And if you have a relatively new house, you look at the electrical panel, usually on the outside, if you got a basement, you may have an external electric socket and a panel, electric panel inside the basement. And that's tied to a ground conductor, a ground conductor. If on the outside, conductor comes out, usually at the bottom of the electrical panel, and connects to a common point ground. So that telephone is grounded to that, you have a cable TV is connected to that. If you would have satellite TV, you see it here, they ground that too. So everything's tied to that ground, including your station. So that's part of the national electric code that many jurisdictions have adopted. Yours may have a variation of that, it may have something that's very different. But the national electric code wants everything to go back to the main panel. By everything I mean hot, the neutral, and the ground wires, all the back to the main panel. If it's a 2-point outlet or a sub-panel, there is an exception. If the sub-panel is not separate built, if it's on the main building, their 4 wires will go back to the main panel from the sub-panel. It'll be neutral, and each side will get 240 volts, and the ground, they all go back to my panels that way. They all go back to the electrical panel. The most important function of a ground rod is to provide that grounding for the electric system, because there's a pole out from your house, which there was at all location, or you got a transformer in your front yard, so we have here, it has a ground rod, so that there is a connection between that electric panel and the ground rod at the transformer, sometimes called pole big or big, because so big. That's the primary function of a ground rod, or external earth connection. The whole question I find fault with because it says external earth connection. Is there an internal earth connection? No, I think so. Ground rod. Many houses do not have a driven ground rod. Of houses I'm familiar with, very few have a driven ground rod. They were built, I think, in the last city, from the 80s to the year 2000. They have an Uber ground, and what that is an earth rebar, bent in the shape of an L. The top of the L, side, and the top of the L comes out of the stem wall or out of the slide foundation. That rotary or larger rebar is tied back to the rebar that makes the foundation. It could be a couple in the footing, a couple stem wall. It could be a grid header in the concrete slab, maybe 2 feet on center, and that Uber ground can exude that. Part sticks out then is where the concrete ground comes in. So the Uber sticks out of the stem wall, and there's a box usually below the electrical panel, and everything is connected to that. How do you know that? Well, I was a building inspector. It is a quick summary of my background. A lot changed, and I don't consider myself an expert anymore, but I was employed in Kansas County and Vic County. I worked as a real estate operator, P-Taxes certificate building inspector. I went on the fire code board, the building code board, build code board appeals. I was a plan commissioner at General Lands. I had a general contractor's license. I had an answer appraiser certificate from the state of California. And I did expert testimony in Superior Court. Also held a real estate broker's license. So I've, in fact, I have with the Uber ground rods, the common ground. Today's a little different. The national code I is going to ground rods. It could be over ground and ground rod, or it could be 2 ground rods that are at least 6 feet apart. Here's the point that I'm going to do, and we won't have to get this point. Should you drive a ground rod, and run usually video recommends, or even a lot of locations, and 6 wire from your station, we'll talk about where we connect, to that ground rod? And my answer is no, because it is probably too far from the main path. The electrical wants everything back to that common ground. If you are a ground rod outside, you provide a different background, and the electrical code doesn't want that. If that driven rod is relatively close to the panel, and you go from that rod with a conductor to that driven rod, and now it's connected to the main electrical panel, or in a relatively short distance, say 6, 8, 10 feet, connected to the main panel, that would be fine. But if it's on the opposite side of the house and you drive a ground rod, technically you're violation of the national electrical code. In some jurisdictions have adopted more strict regulations than the NEC. Some are real extreme. Even in California, there's some jurisdictions where the connection outlets are tightly regulated, and in many cases, it's a good thing. For example, in some jurisdictions, you can't take out outlet and open never 14 wire on 15 service they want to go through. So, this is typical of you can see maybe on a computer or the first slide where you have video. Sometimes these are called sabs. What do you call it? We'll call it wrong if you want. This wrong is ground. It's the longer of the 3. The one on the left is the neutral. It can be vertical for a stand outlet, can be horizontal for 25 outlet, 120 volts. The one on the right is the hot, and that one's usually smaller. It's usually smaller than the neutral one. So you got hot, neutral, and ground is green wire, hot is the white wire, and neutral is the white wire, and the hot is the black wire. And if I do an outlet, those 2 wires wouldn't necessarily be green. Probably both not at all. Goes back to the main panel for your receptor. The reason for the 2 line back to the main panel is the redundancy in the ground system. So grounding system, if there's a failure, they want to make sure they get misgrounded. Real quick, in building my station here, I went through the extreme test what I really already do because I've been here for 56 years, and my prior station I had no connection to ground other than electrical ground. So for safety purposes, this is test. There is aluminum foil on 3 walls. On 3 walls, there's 2 strips of this copper, and this copper then runs around the room. One top of it, I have about 6 inches of this stuff. Comes out of the wall and connects to a copper pipe that's underneath that, the current copper pipe.
Here's the underside of my desk. There's a copper pipe that runs under the desk to the 3 legs. It's an LJ desk, and
That copper pipe is in turn connected to grounding straps. There's one there that leads to a 1-inch copper pipe. Then each piece of equipment, there's one side connected or hooked up to that kind of a braiding. The braid is attached mechanically to the pipe with a clamp. So I put everything on that pipe I could. This is an 80 switch to choose between two receivers. There's a strip with 12 volts on it and a mirror to read 12 volt. The AC terminal strip got on it. That box is, it's hard to see, but that's the one relay box, so I can select various antennas and head outside. The cluster is a watt meter and other devices that sense RF or other. Again, it's going to do the frame of the using that top pipe. It's pretty much aware, but that's a SQ, I guess. So everything is connected to the copper pipe, and that connects to the copper strips that lead to the copper pipe that goes to the main electric panel. So each piece of equipment has this next to the back of it, goes to that pipe. What I'm trying to accomplish is keeping each box at the same potential. Could be half volt right above ground, could be 1 volt above ground, but each box is going to be the same potential so that I do it intermittently at a shot. We'll continue the discussion in the next video, and we'll talk about RF grounding. In particular, when questions come about RF audio, what causes that, and the answer is pretty simple. Oh, or again, in one of the videos for an expert, he recommends that like this plug to stop ground loops, you cut off this end so that you don't have that ground connection. That video I should build code, and this is safe, so no matter what that does, don't do that. Keep everything grounded. Stay deep. Alright, this generates some questions and privacy emails. Go or let me know what you think. If you have questions, post that below. If you like this video, I put a thumbs up, do a thumbs down, what you'd like to see done differently. Okay, thanks for watching. Please subscribe to M0ODZ from Rockland, California. 73. Stay safe. Hi, Alex, your YouTube Elmer with Radio 6. Welcome to my radio again here in Rockland, California. After reviewing a few questions on the exam, discussed the grounding, I decided to look at another one that I have a bit of experience in it, and that is linear amplifiers or RF power amplifiers. I quickly came across this question, and I can highlight it. The question is E7B09, and they say the answer is D. The question is, which of the following describes how loading and tuning capacitors are to be adjusted to loading a vacuum tube RF power amplifier that employs a network output circuit? So what's asking is, sitting here for load and tune controls, you're tuning in our power amplifier like an American LED or LED to one of those that has high network, and most linear amplifiers have either pi or pi. Pi is just an extra coil at the end of the pi circuit. So it's which of the following describe how loading tune capacitors are to be adjusted. And the answer is D. E is wrong. D says the tune capacitor is adjusted for minimum plug current. The loading capacitor is adjusted for maximum permissible plug current. E. I'll read it again. The tune capacitor is adjusted for a minimum peak current. Okay, so that's tune control. The load control is on below tune controller to the right side of it. Load capacitor is adjusted for maximum permissible plug current. So you're tuning for this. So you tune for the minimum current you did, and then load control is adjusted for maximum permissible plug current. That's not an answer. The reason it's not an answer is if you tune that way, there's going to be times when the amplifier will go into distortion and produce a slider. Also, you can run tune pretty quickly if you tune for the dip. For maximum output, there's additional step. You rotate the tune control and the load control for max out at a certain level drive, then you increase the drive again until you reach the maximum drive the manufacturer comes, and we can look at that on one of the original frame, and it's really pretty well written. You get to the maximum amount of drive step by step, so you might start out 20 watts, 30 watts, maybe it takes a maximum of 50 watt drive. When you get there, each time you step the drive, you adjust the linear amplifier, the RF power amplifier, for maximum output. Keep one amplifier current, one eye current, and your third eye on the power output. It's a little bit juggling act, but once you get used to doing it, it's not so hard. So you tune for max out, and that may or may not, like it won't, occur at the minimum play current depth, the IP. Just okay, let's look at the instrumental that have downloaded some time ago, help you out tune and apply for the AL8, and I'll get to that just a second. The need to point out is, in addition to the video that Sneaks discussed in the question and that I discussed, it's specified, but it relates to typical procedure for a ground grid amplifier, which would usually have sometimes tried. Could be 572Ds, could be 11As in a ground grid configuration, could be 3500Zs, any number of tubes, in particular, or such cursors strapped at are combined as a product and grounded. So, and this is dealing with a typical ground grid amplifier. It's not specified in the question, and I meant to point out in the original recording, that is a little addendum to the audio. The instructions for American amplifiers are pretty well written. Everybody has a little hesitancy on tuning amplifier because they've done before. And let's scroll down to tuning procedure. First, just status for load control. Those again are just where you might start. It's probably at a different point. Here they talk about with drive at 0, you turn on the load meter to the IP, the current position, so your IHV, power output ALC, or ALC fan, power output IP, and the grid current. And the grid current meter just mirror grid current is really important. Talk about tuning the amplifier with its standby position and being with it in transmitted load drive, and it indicates the limit of 75 milliamps and the 150 depending on play voltage. Let's just get down to the last step. It says apply current indicate either 1500 watts of output or 300 milliamps of grid current. I think tubes have a maximum grid current of slightly greater than that, like maybe 350 tubes. Repeat the load and controls. The final grid current should be around 250 milliamps and 9 milliamps for play current. By peak, they're seeing advanced, they're out to 215 of grid current. Adjust the load application controls for maximum power output. It does give the instructions to create a dip, but again, step 10 is advanced direct to a few lanes. Adjust the load plate control for max power output of the That's what they're doing when they go peak. You're just for maximum power output. The question on the astronaut exam, so get that out of the way, describes how loading and tuning capacitors are adjusted when tuning a vacuum tube or amplifier. The tuning capacitors adjusted for minimum current and load control is adjusted for maximum current. No, that's not how I do. Interview other questions on the exam. If you desire amplifiers that you guys have, if you agree with me, I'd be really happy to do that. But then, if you've got a lean amplifier, do not tune for the dip. You tune for max output at full drive when you get there, you pure wave drive. And then by the advanced load control, you still get so the output starts to drop. And that way, sharp linear to no matter how much drive goes into the linear amplifier. Just a reference, I built maybe 10 amplifiers, some really big ones and some really small ones over the last 50 years, more than that. Yeah, I'm kind of white noise there. In fact, me building amplifiers is a lot of fun. It's one of the few things I can do. But anyway, there you go. There's another question on the astronaut exam that has a poor answer. The question is written okay. Again, the word is kind of weird. For example, they say the parallel amplifier employs a pi network output circuit. 73, if you haven't subscribed, please I'm trying to grow the subscription number to 50 down. If you have a question, comment, either give a thumbs up or a thumbs down. If you have this, let me know why. I'll hear about it. 73 in Brooklyn, California. It's late at night. I'm calling this is Jim. The YouTube elder with Henry Basics. Thanks for watching. Letting go.
So we'll either watch my wife make Christmas cookies or come down here and do a video. Guess which one I chose. Hey everybody, my name is Paul, W1VLF, and welcome to the lab. I'm my lecture here. I'm coffee over there. And Facebook, my armrest over here.